Space is filled with mysteries that challenge our understanding of the universe. Despite centuries of scientific progress, the cosmos continues to surprise us. How do supermassive black holes influence entire galaxies? And what is the true nature of dark matter and dark energy? Join us as we journey through the universe and look for answers to some of the biggest mysteries we know. The WOW signal remains one of the most intriguing and mysterious radio signals ever detected by astronomers. Discovered by Dr. Jerry Amon on August 15, 1977, this powerful unmodulated narrowband radio signal was picked up by the Big Ear radio telescope at Ohio State University. The moment stood out due to the signal's intensity and origin, which seemed to emanate from the constellation Sagittarius. The signal lasted 72 seconds, which was the duration the Big Ear telescope could observe any given point in the sky due to the Earth's rotation. During this time, it exhibited a strength and pattern that caught the attention of Dr. Ehrman, who famously circled the signal on the printout and wrote, "Wow," beside it, giving the phenomenon its enduring name. Despite extensive follow-up searches, no repeat of the signal has ever been detected. This absence of repetition led scientists to several speculations. Possible explanations have ranged from a naturally occurring astrophysical event or a signal reflected off space debris to a highly focused transmission from an intelligent extraterrestrial source. However, none of these theories have been conclusive. The lack of more data and the inability to replicate the detection make the WOW signal a unique and elusive piece of the puzzle as humanity searches the cosmos for signs of other intelligent beings. Its origin remains unexplained, capturing the imagination of astronomers and enthusiasts alike, and continues to be a compelling mystery in the field of radio astronomy. The discovery of ultramassive black holes in the early universe presents an exciting challenge for cosmologists and astrophysicists. These behemoths, some possessing the mass of billions of suns, existed when the universe was less than 1 billion years old. Their presence raises profound questions about how such enormous objects could form so quickly after the Big Bang. One leading hypothesis involves the direct collapse of massive gas clouds. Instead of forming stars and then collapsing into a black hole, a massive gas cloud might bypass the star phase and collapse directly into a black hole. These direct collapse black holes could rapidly accumulate mass, offering a potential pathway for the creation of ultramassive black holes in the youthful universe. Another intriguing possibility concerns the mergers of primordial black holes. These would be black holes formed very early in the universe's history, possibly moments after the Big Bang due to extremely dense regions of space. As the universe evolved, these primordial black holes could have merged to form more massive ones relatively quickly. Furthermore, massive accretion rates could play a role. In the dense environments of the early universe, black holes could rapidly attract and consume surrounding gas and dust at rates much faster than what we typically observe today. This rapid feeding process could accelerate their growth, helping them reach ultramassive sizes in a short cosmic time frame. Each of these theories contributes to our understanding, yet the true mechanism likely involves a combination of many factors, fueled by the dynamic and complex nature of the early universe. The mysterious dimming of Boyajian's star, also known as KIC 8462852, has puzzled astronomers since its discovery. This star, located roughly 1,400 light-years away in the constellation Cygnus, exhibits irregular and significant dips in brightness. The phenomenon was first brought to wide attention by astronomer Tabitha Boyajian, after whom the star is named. Several hypotheses have been proposed to explain these curious fluctuations. One of the most compelling theories involves a large cloud of dust or unevenly distributed objects in orbit around the star. These objects could create irregular shadows as they pass between the star and Earth, causing the observed dimming. The presence of dust is supported by the star's infrared light, which indicates that some material may be absorbing and re-radiating its light, though not in a uniform manner. Another intriguing yet speculative possibility considered was the existence of an advanced extraterrestrial civilization. Some scientists and enthusiasts proposed that a so-called megastructure, like a Dyson sphere partially surrounding the star, could account for the irregular dimming. However, further observations, including searches for accompanying radio signals, have found no evidence of alien technology. A more recent and plausible explanation points to a family of comets or debris from a disintegrated planet. These fragments and their associated dust clouds could be on highly elliptical orbits, intermittently blocking the star's light. Despite various theories, no single explanation fully accounts for all observed characteristics, making Boyajian's star one of the most intriguing and actively studied objects in modern astronomy. As technology and observational techniques improve, future findings may eventually unravel this fascinating celestial mystery. The apparent scarcity of antimatter in the universe is one of the most profound puzzles in physics. According to our understanding of the Big Bang, matter and antimatter should have been produced in nearly equal amounts. However, our universe is overwhelmingly composed of matter, with incredibly little antimatter to be found. One potential explanation lies in a phenomenon known as baryon asymmetry. This hypothesis suggests that during the early moments of the universe, there were slight differences in the behaviors or decays of matter and antimatter particles. These differences would have led to an imbalance, resulting in a slight excess of matter over antimatter. When matter and antimatter later annihilated each other, the small surplus of matter remained to form the stars, planets, and galaxies we observe today. Another avenue of investigation involves exploring the properties of subatomic particles known as neutrinos. Some theories propose that neutrinos might be their own antiparticles, a property known as being Majorana particles. If this is the case, it could help explain why we observe more matter than antimatter. Researchers are conducting numerous experiments to test these ideas, including studying neutrino interactions in sophisticated underground detectors. Scientists are also examining the role of symmetry violations in fundamental physics processes. Specifically, they are investigating how the laws of physics might differ slightly for matter and antimatter, a concept known as charge parity violation. These subtle violations could be key to understanding why matter triumphed over antimatter. Despite the mystery's depth, the quest to comprehend the universe's imbalance continues to drive advances in both theoretical and experimental physics. Unveiling the reasons behind this asymmetry promises to deliver profound insights into the very fabric of our cosmos. Ultra-high-energy cosmic rays, some of the most energetic particles ever observed, present a significant conundrum for modern astrophysics. These particles possess energies that are millions of times greater than those produced by the most powerful particle accelerators on Earth. Their sources, however, remain shrouded in mystery, challenging our understanding of both cosmic mechanisms and fundamental physics. One leading candidate for the origin of these cosmic rays is active galactic nuclei. AGNs are supermassive black holes at the center of some galaxies, surrounded by extremely energetic accretion disks. As matter spirals into these black holes, it heats up and emits powerful jets of particles. These jets could potentially accelerate cosmic rays to the extraordinary energies observed, propelling them across vast distances in space. Gamma-ray bursts are another potential source. These are brief yet immensely powerful explosions, thought to result from the collapse of massive stars or the merging of neutron stars. The immense energy released during a GRB could accelerate particles to ultra-high energies, launching them into the cosmos at nearly the speed of light. The brief but intense nature of GRBs makes them a compelling candidate for these enigmatic cosmic rays. There is also the possibility that some ultra-high-energy cosmic rays originate from as yet unobserved astrophysical phenomena. These could include exotic processes like the decay of massive particles from the early universe or interactions involving dark matter. Such speculative sources would not only explain the immense energy of these cosmic rays, but also provide new insights into the fundamental workings of the universe. Determining the precise origins of ultra-high-energy cosmic rays involves sophisticated detection methods, such as ground-based observatories and space-based detectors. As researchers continue to gather and analyze data, the hope is that new evidence will eventually pinpoint the mechanisms behind these awe-inspiring particles, revealing deeper truths about the energetic processes that shape our universe. The so-called axis of evil is an intriguing anomaly found in the cosmic microwave background, the afterglow of the Big Bang that permeates the universe. This term refers to a peculiar alignment of temperature fluctuations in the CMB that seems strangely consistent over large angular scales, challenging the expected isotropy and homogeneity of the universe on these scales. One hypothesis is that this anomaly could be the result of residual foreground contamination. Galactic radiation or cosmic dust within our own Milky Way might be interfering with the measurements of the CMB. Despite extensive efforts to clean the data from these and other potential sources of interference, some researchers suggest that remnants of foreground distortions might still be subtly influencing the observations. Another possibility is that this alignment is simply a statistical fluke. Given the vast amount of data involved, some patterns are bound to emerge by chance. Proponents of this view argue that, while the alignment is unusual, it does not necessarily imply a fundamental problem with our understanding of the universe's structure. Advanced statistical tests continue to probe this theory, weighing the likelihood of such an alignment occurring randomly. Some more radical theories suggest new physics at play. For instance, modifications to the standard cosmological model or previously unknown physical phenomena might be influencing the CMB. Ideas range from the influence of primordial magnetic fields to alternative theories of gravity. These concepts push the boundaries of established physics but remain speculative until further evidence is discovered. Researching the axis of evil involves analyzing ever more precise measurements of the CMB, gathered by missions like the Planck satellite. These efforts aim to confirm or refute the anomaly's significance and origin. As our observational techniques and theoretical frameworks advance, the enigma of the axis of evil continues to drive a deeper exploration into the very fabric of our universe. Recurring nova explosions in binary star systems are a fascinating phenomenon resulting from the complex dynamics of stellar interactions. Unlike supernovae, which are catastrophic explosions marking the end of a star's life, recurring novae occur in systems where one of the stars is a white dwarf and the other is often a main sequence star or a red giant. The key to understanding these recurring outbursts lies in the process of matter transfer between the two stars. In a typical recurring nova system, the white dwarf, a remnant of a star that has exhausted its nuclear fuel, gravitationally attracts material from its companion star. This material, primarily hydrogen, accretes onto the white dwarf surface, forming an ever-growing layer. Over time, as more matter accumulates, the increasing pressure and temperature conditions on the white dwarf's surface ignite the hydrogen in a runaway fusion reaction. This explosive fusion process heats up the accreted layer dramatically, resulting in a sudden brightening that we observe as a nova. The explosion ejects a portion of the accreted material into space, causing a temporary increase in the system's brightness. However, unlike supernovae, this event does not destroy the white dwarf, allowing the process to repeat. After the eruption subsides, the system returns to its pre-nova state, and the cycle of matter transfer starts anew. Depending on the rate at which the companion star donates material and the specific conditions of the white dwarf's accretion, this process can repeat on timescales ranging from a few years to several decades. Each nova event is similar to the previous one, but no two events are exactly alike due to variations in the amount and rate of material accretion. Studying recurring novae helps astronomers understand the nature of binary star evolution, as well as the complex physics governing accretion processes and nuclear fusion under extreme conditions. These insights contribute to our broader comprehension of stellar life cycles and the diverse phenomena that populate our universe. Galaxies like NGC 1052 DF2, which seem to lack significant amounts of dark matter, present a compelling enigma in our understanding of the universe. Dark matter, which does not emit or absorb light, is thought to make up about 85% of the universe's total mass. It plays a crucial role in the formation and dynamics of galaxies, acting as the gravitational glue that helps hold galaxies together. The apparent scarcity of dark matter in NGC 1052 DF2 challenges this conventional framework. One potential explanation for the dearth of dark matter in NGC 1052 DF2 is the galaxy's unique formation history. This galaxy might have formed through tidal interactions or mergers that stripped it of its dark matter content. If NGC 1052 DF2 experienced a close encounter with another massive galaxy, gravitational forces could have displaced much of its dark matter, leaving behind a galaxy predominantly composed of baryonic or ordinary matter. Another possibility is that NGC 1052 DF2 is not an isolated case but part of a larger population of ultra-diffuse galaxies. These galaxies have extended structures with low luminosity, making them challenging to detect. Their diffuse nature might result from initial conditions that prevented significant dark matter accumulation. In such scenarios, the processes that led to their formation might inherently result in lower dark matter content. Some researchers also consider modifications to our understanding of dark matter itself, or even to the laws of gravity. For instance, alternative gravity theories, such as modified Newtonian dynamics, propose that observed gravitational effects without dark matter could be explained by adjustments to Newton's laws of gravity at low accelerations. However, these theories require more evidence and refinement to be widely accepted. The study of NGC 1052 DF2 and similar galaxies is still in its early stages. As astronomers gather more data and refine their theoretical models, they hope to uncover the true reasons behind such anomalies. These efforts not only advance our knowledge of dark matter and galaxy formation, but also test the limits of existing cosmological theories, potentially leading to groundbreaking discoveries about the universe's fundamental nature. Mirror matter is a fascinating concept that arises from the idea of symmetry in physics, specifically a type known as parity symmetry. In our universe, the laws of physics as we know them exhibit certain asymmetries. Mirror matter theorizes the existence of a parallel type of matter that behaves as a mirror image of ordinary matter, exhibiting opposite parity. This means if you have a right-handed particle in our universe, its mirror matter counterpart would be left-handed. One intriguing aspect of mirror matter is that it would interact with regular matter primarily through gravity. This means it would be virtually invisible to our standard electromagnetic detectors, as its interaction via the electromagnetic force would be extremely weak or non-existent. Despite this elusive nature, mirror matter could exert gravitational influence, potentially contributing to phenomena we currently attribute to dark matter. If mirror matter exists, it might form structures similar to those of ordinary matter, such as mirror stars, mirror planets, and even mirror galaxies. These mirror structures would emit mirror photons rather than ordinary photons, rendering them invisible to conventional observation techniques. Nevertheless, their gravitational effects could be detectable, and they might influence the dynamics of galaxies and large-scale cosmic structures in ways that we could observe indirectly. Experimental detection of mirror matter is challenging due to its weak interaction with ordinary matter. However, scientists have proposed several potential methods for detection. One approach involves looking for deviations in gravitational experiments that cannot be accounted for by regular matter alone. Another possibility is searching for rare interactions between mirror matter and ordinary matter, which might occur in sensitive detectors designed for ultra-low background noise, like those used in dark matter searches. The existence of mirror matter would revolutionize our understanding of the universe, potentially offering explanations for unresolved mysteries, such as the nature of dark matter and certain unexplained gravitational phenomena. As experimental techniques advance, the pursuit of evidence for mirror matter continues to be an exciting and contentious frontier in the realm of theoretical physics and cosmology. The Great Attractor is one of the most compelling enigmas in cosmology, exerting a significant gravitational pull on our galaxy, the Milky Way, and many surrounding galaxies in our local supercluster. Discovered in the 1980s through observations of the peculiar velocities of galaxies, the Great Attractor appears to influence the motion of galaxies over a region stretching hundreds of millions of light-years. This immense gravitational anomaly is located in the direction of the constellation Centaurus. Despite its strong pull, direct observation has been challenging due to its position behind the dense, dusty plain of the Milky Way, a region astronomers refer to as the zone of avoidance. However, advancements in X-ray and infrared astronomy, which can penetrate this cosmic veil, have provided clues about what might be lurking there. One prominent explanation posits that the Great Attractor is part of a massive, dense supercluster of galaxies, known as the Norma Cluster or Abell 3627, located roughly 200 million light-years away. This dense region of space teems with large galaxy clusters and vast amounts of dark matter, which collectively create a gravitational well powerful enough to affect the motion of entire galaxy clusters over enormous distances. Another hypothesis involves the concept of a yet larger structure, the Laniakea supercluster, of which the Great Attractor is thought to be a prominent part. Laniakea, meaning immense heaven in Hawaiian, is a vast supercluster complex stretching over 500 million light-years. The collective gravitational influence of this interconnected web of galaxies and dark matter could be the driving force behind the observed peculiar velocities. While much has been learned, the full extent and exact nature of the Great Attractor remain subjects of ongoing research. Continued improvements in observational technology, especially those capable of seeing through the plane of the Milky Way, promise to deepen our understanding of this colossal gravitational anomaly, illuminating how large-scale structures in the cosmos shape the movement and evolution of galaxies. At the center of a neutron star, matter is compressed to densities so extreme that it challenges our understanding of physics. Neutron stars are the remnants of massive stars that have undergone supernova explosions. These remnants pack more mass than the Sun into a sphere only about 10 miles in diameter, creating conditions that are unparalleled anywhere else in the universe. At these incredible densities, exceeding several times that of an atomic nucleus, the protons and electrons in the star are crushed together to form neutrons. This process results in a star predominantly composed of closely packed neutrons, hence the name neutron star. The density near the center of a neutron star can reach up to hundreds of millions of tons per cubic centimeter. The innermost core of a neutron star, however, presents even more extreme conditions. Here, the state of matter could move beyond the formation of neutrons. Several theoretical models suggest that these central regions might host exotic forms of matter, such as hyperons, which are particles containing strange quarks, or even deconfined quark matter, in which the neutrons themselves break down into their constituent quarks, creating a possible quark-gluon plasma. Another fascinating possibility involves the presence of what's termed nuclear pasta, a phase of matter where neutrons and protons arrange themselves in shapes reminiscent of spaghetti, lasagna, or even gnocchi at the inner crust. This phase is hypothesized to result from the competition between nuclear attractions and Coulomb repulsions at extremely high densities. Our current knowledge of the physics governing neutron star cores is still incomplete, primarily because the conditions there cannot be replicated in terrestrial laboratories. However, observations of neutron star mergers, gravitational waves, and advances in particle physics continue to provide valuable insights. These findings drive us closer to understanding the behavior of matter under such extraordinary conditions, potentially revealing profound new aspects of quantum mechanics and general relativity. Quark stars, if they exist, would represent an even more exotic and extreme state of matter than neutron stars. Both types of stars are born from the cataclysmic collapse of a massive star in a supernova, but quark stars would take this process a step further. While neutron stars are composed mostly of densely packed neutrons, quark stars are believed to be composed of quark matter, a state in which the neutrons have broken down into their constituent quarks. In a neutron star, gravity compresses the matter to densities so high that electrons combine with protons to form neutrons. If this gravitational pressure continues unabated, it could theoretically overcome the strong nuclear force that keeps quarks confined within neutrons and protons. This would result in a phase transition where the neutrons themselves disintegrate into a soup of up and down quarks and potentially strange quarks, forming what is known as quark-gluon plasma. The density and pressure inside a quark star would be even greater than those in a neutron star. This quark matter would be in a deconfined state, meaning the quarks are no longer bound into individual protons and neutrons, but instead move freely in a sea of quark-gluon plasma. If strange quarks are present, these hypothetical stars are sometimes referred to as strange stars. The presence of strange quarks could make the star more stable and lead to even more unusual characteristics. Quark stars would differ from neutron stars not just in their internal composition, but also potentially in their observable properties. They might exhibit different thermal and radiation profiles due to the distinct nature of quark matter. Moreover, the transition from neutron star to quark star might produce unique gravitational wave signatures or bursts of radiation. These differences make quark stars, if they exist, exciting potential candidates for study, but direct observational evidence of such stars remains elusive. The search for quark stars involves a combination of theoretical modeling, astrophysical observations, and experiments in particle physics. Advances in detectors and observatories, like those for gravitational waves and high-energy cosmic phenomena, might eventually provide the clues needed to confirm the existence of these extraordinary objects. As it stands, quark stars remain a tantalizing possibility, pushing the boundaries of what we know about matter under the most extreme conditions in the universe. The solar corona, the outermost layer of the Sun's atmosphere, presents a captivating enigma in solar physics due to its extraordinarily high temperatures. While the Sun's surface, or photosphere, has a temperature of about 6,000 degrees Celsius, the corona can reach temperatures of 1 to 2 million degrees Celsius. This counterintuitive phenomenon raises questions about how the corona becomes and remains so hot. One key process thought to contribute to the heating of the corona is magnetic reconnection. The Sun's magnetic field lines, which are generated by the dynamo effect in its interior, become twisted and tangled due to the differential rotation and convective motions of the Sun's plasma. When these field lines reconfigure themselves, they release stored magnetic energy in the form of heat and kinetic energy, which then heats the surrounding plasma. This process can manifest as solar flares, which are sudden, intense bursts of radiation that contribute to the heating of the corona. Another significant mechanism likely involves waves and oscillations generated in the Sun's interior. These waves, particularly alpha waves, travel along magnetic field lines from the Sun's surface up into the corona. As they propagate, they carry energy that can be dissipated in the corona, converting wave energy into thermal energy. This dissipation process helps to sustain the high temperatures observed in the corona. Nanoflares, smaller and more frequent versions of solar flares, also add to the puzzle. Proposed by solar physicist Eugene Parker, nanoflares are tiny yet numerous magnetic reconnection events that occur throughout the corona. Individually, each nanoflare releases only a small amount of energy, but their cumulative effect could contribute significantly to the overall heating of the corona. By combining data from these missions with sophisticated computer models, scientists hope to unravel the mechanisms behind the solar corona's mysterious heat, shedding light on one of the most perplexing aspects of our closest star. Magnetars are a type of neutron star distinguished by their incredibly powerful magnetic fields, which are the most intense known in the universe. To understand how magnetars generate such immense magnetic fields, we must delve into the dynamics of a star's life and death, particularly focusing on the processes that occur during and after a supernova collapse. When a massive star exhausts its nuclear fuel, it can no longer support itself against gravitational collapse, leading to a supernova explosion. The core of the star, collapsing under immense gravitational pressure, forms a neutron star. For magnetars, this core collapse is coupled with rapid rotation and a highly dynamo process during the formation phase. If the proto-neutron star spins very quickly, on the order of milliseconds, it can enhance its magnetic field through a process called the alpha-omega dynamo mechanism. In this mechanism, differential rotation and convection in the nascent neutron star can amplify any pre-existing magnetic fields exponentially, reaching values of around 1,000 trillion Gauss or even more. This dynamo action would cease within a few seconds due to strong magnetic braking, but by then, the magnetic field would be deeply entrenched in the star. Another contributing factor to the extreme magnetic fields of magnetars is the flux freezing principle. During the collapse of the core, the magnetic flux is conserved. As the core's radius shrinks dramatically, the magnetic field lines are compressed, significantly increasing the magnetic field's strength. This compression, combined with the dynamo mechanisms, could lead to the ultra-strong magnetic fields observed. Finally, the intense magnetic fields of magnetars can generate surface phenomena like starquakes. These magnetic stresses can fracture the crust of the neutron star, releasing a burst of X-rays or gamma rays. Such events, known as soft gamma repeaters or anomalous X-ray pulsars, are characteristic features of magnetars and underscore the dynamic nature of their magnetic fields. The study of magnetars is an actively evolving field. Observations from X-ray and gamma-ray telescopes, combined with theoretical models and simulations, continue to deepen our understanding of how these extraordinary cosmic engines generate and sustain their immense magnetic fields. These insights not only illuminate the nature of magnetars, but also enrich our broader understanding of magnetic phenomena in the cosmos. The Crab Nebula, one of the most studied objects in the sky, has baffled astronomers with its sudden bursts of gamma-ray flares. These high-energy explosions originate from the nebula's central pulsar, a spinning neutron star left behind after a supernova explosion. The pulsar is only about 12 miles in diameter, yet it has a mass greater than that of our Sun. It spins 30 times per second, creating intense magnetic fields and accelerating particles to near the speed of light. The key to the gamma-ray flares lies in the dynamic and highly energetic environment created by this rapidly spinning pulsar. As the pulsar rotates, it generates a powerful wind composed of charged particles. These particles spiral along the pulsar's magnetic field lines, creating a shockwave where the wind interacts with the surrounding nebula material. This environment is known as the pulsar wind nebula. Within this chaotic region, pockets of magnetic fields can suddenly reconnect, a process known as magnetic reconnection. When these field lines snap and reattach in a more stable configuration, they release tremendous amounts of energy. This energy propels particles to extreme velocities, causing them to emit gamma rays, the highest energy form of electromagnetic radiation we know of. These gamma-ray flares from the Crab Nebula are fleeting, lasting just a few days, but during that time, they can be 1,000 times more intense than the Sun's total energy output in the same period. Understanding these flares not only illuminates the behavior of pulsars and their wind nebulae, but also offers insights into fundamental processes that occur throughout the universe, making the Crab Nebula a natural laboratory for high-energy astrophysics. Supermassive black holes, which can range from millions to billions of times the mass of our Sun, reside at the centers of most large galaxies. Their influence on their host galaxies is profound, far-reaching, and multifaceted. The gravitational pull of these cosmic giants affects the motion of stars and interstellar gas within the galaxy. However, their impact goes beyond mere gravitational attraction. One primary way supermassive black holes shape their galaxies is through the release of immense amounts of energy as matter falls into them. This process occurs in the accretion disk, where gas and dust spiral inward, heating up to extreme temperatures due to friction and gravitational forces. This hot, glowing material emits powerful radiation, which can trigger or suppress star formation in the surrounding galaxy. When the black hole is actively feeding, it can produce jets of charged particles that shoot out at nearly the speed of light, extending thousands of light years into space. So, these jets and outflows inject vast amounts of energy into the interstellar medium, creating shock waves and turbulence. This can either compress gas, fostering new star formation, or heat the gas, preventing it from cooling and condensing into new stars. This regulation of star formation activity has significant implications for the overall growth and morphology of the host galaxy, contributing to phenomena like the quenching of star formation in massive galaxies. Moreover, the interactions between supermassive black holes and their host galaxies are believed to be crucial in regulating the size and growth of both. Observations suggest a tight correlation between the mass of the black hole and the properties of the galaxy's central bulge, such as its velocity dispersion. This relationship hints at a co-evolutionary process where the growth of the black hole and the development of the galaxy are intimately linked, indicating a dynamic interplay that shapes the cosmos on the grandest of scales. Strange matter is a hypothesized type of matter that may exist in the form of quark-gluon plasma, an exotic state where quarks, the fundamental building blocks of protons and neutrons, and gluons, which mediate the strong force holding quarks together, are no longer confined within particles. In this state, quarks are free to move independently in a kind of fluid. Specifically, strange matter would include not just the up and down quarks found in ordinary matter, but also strange quarks, giving it unique properties. Strange stars, sometimes called quark stars, are potential astrophysical objects composed primarily of strange matter. These stars are theorized to form when neutron stars, dense remnants of supernova explosions, implode under the force of their own gravity. If the conditions are extreme enough, the immense pressure could crush the neutrons into their constituent quarks, resulting in a star made entirely of quark matter, particularly strange quarks. The characteristics of strange stars set them apart from neutron stars. Strange stars could be more stable than neutron stars because strange matter is hypothesized to be the most stable form of matter in the universe. These stars might be denser and more compact, and their surfaces could be incredibly unique, possibly smooth and nearly frictionless, unlike the hardened crust of neutron stars. This difference in composition could affect the way they emit radiation, potentially explaining certain observed cosmic phenomena that do not match the signatures of known neutron stars or black holes. Detecting strange stars or confirming the existence of strange matter remains a significant scientific challenge. Observatories that detect gravitational waves and those that observe high-energy cosmic events are critical in this quest. If strange matter or strange stars are found, they could revolutionize our understanding of fundamental particle physics and the extreme conditions in the universe, offering profound insights into what happens inside the densest objects known. Superpuff planets, also known as cotton candy planets, are intriguing celestial objects characterized by their remarkably low densities. These planets, despite being similar in size to gas giants like Jupiter, have masses so small that their densities resemble those of cotton candy. The formation and nature of these superpuff planets challenge conventional planet formation theories and spark scientific curiosity. Several hypotheses attempt to explain their unusually low densities. One leading idea is that superpuffs have incredibly thick atmospheres composed largely of hydrogen and helium surrounding a relatively small core. During the early stages of planet formation, they may have accreted substantial amounts of gas from the protoplanetary disk, significantly inflating their atmospheres. This process could result in a planet with a large radius but a surprisingly low overall mass. Another theory suggests that these planets might have high-altitude layers of hazes or clouds that contribute to their bloated appearances. These hazes or clouds could be made up of complex molecules or fine dust particles, which scatter and absorb sunlight, making the planet's atmosphere appear more expansive and less dense than it actually is. Such features could dramatically alter the observed size and, consequently, our calculations of their density. Orbital dynamics could also play a role in the formation of superpuff planets. If these planets formed farther out in a star system and later migrated inward, they would maintain their low-density characteristics if the inward migration occurred without substantial mass loss. Additionally, the relatively mild radiation environments in certain orbits might prevent the atmosphere from being stripped away, preserving their puffed-up nature over long periods. By studying the unique properties of these superpuff planets using space telescopes such as the Hubble Space Telescope and the upcoming James Webb Space Telescope, astronomers hope to gain a deeper understanding of how these fascinating worlds form and evolve. The discovery of superpuffs challenges our understanding of planetary formation and encourages the scientific community to explore new models and scenarios within exoplanetary science. The colossal jets emitted by some active galactic nuclei, or AGNs, have captivated astronomers for decades. These jets, which can extend millions of light-years into space, are among the most energetic phenomena in the universe. They originate from the regions around supermassive black holes at the centers of certain galaxies, particularly those classified as quasars and blazars. At the heart of an AGN lies a supermassive black hole consuming vast quantities of gas and dust from its surroundings. This matter forms an accretion disk as it spirals inward, heating up and emitting intense radiation due to friction and gravitational forces. This environment creates a powerful, hyperaccelerated outflow of particles. The key to the formation of jets lies in the magnetic fields generated around the black hole. As matter in the accretion disk moves, it generates strong magnetic fields that thread through the disk and around the black hole. These magnetic fields can twist and coil up due to the rotation of the accretion disk and the black hole's spin. The intense magnetic energy channels particles along the poles of the black hole away from the disk, forming tightly collimated jets. These particles include electrons, protons, and other subatomic particles accelerated to near-light speeds. The jets emit radiation across the entire electromagnetic spectrum, from radio waves to gamma rays, as the particles interact with the surrounding medium and magnetic fields. This synchrotron radiation results from high-speed particles spiraling along magnetic field lines. Additionally, inverse Compton scattering occurs when these fast-moving particles transfer energy to low-energy photons, boosting them to higher energies. These jets can have a profound impact on their host galaxies and intergalactic environments. They inject energy and momentum into the surrounding gas, potentially triggering or quenching star formation and shaping the large-scale structure of the galaxy. Understanding these extraordinary jets not only illuminates the extreme physics near supermassive black holes, but also provides insight into the coevolution of black holes and their host galaxies. Stars like R136A1, currently the most massive star known, pose fascinating questions about stellar formation and evolution. Weighing in at over 300 times the mass of our Sun, R136A1 is part of the dense star cluster R136 in the Tarantula Nebula, located within the Large Magellanic Cloud. Understanding how such colossal stars form requires delving into the unique conditions of their birth environments and the intricate processes of stellar accretion. These massive stars likely form in regions of space where the concentration of gas and dust is exceptionally high, providing the raw material necessary for star formation. In star-forming regions like the Tarantula Nebula, clouds of hydrogen and other elements collapse under gravity, fragmenting into clumps that eventually give rise to protostars. For a star to grow as massive as R136A1, it must be born in a particularly dense clump, where the gravitational forces and available material are sufficient to support rapid and sustained accretion. During its formation, R136A1 likely underwent a period of hyperacceleration, where the protostar rapidly accumulated mass from its surrounding environment. The intense gravitational pull of such a massive protostar would draw in vast amounts of gas from its vicinity, feeding its growth. Additionally, interactions within the dense star cluster could funnel material towards the forming star, boosting its mass even further. Radiation pressure, which typically opposes accretion in massive stars, would be temporarily overcome by the sheer gravitational power. Once formed, these stars burn through their nuclear fuel at an astonishing rate due to the tremendous pressure and temperatures in their cores. The intense radiation and stellar winds from such massive stars can significantly impact their surroundings, blowing away remaining gas and dust and potentially limiting further growth. These processes highlight the delicate balance between accretion and feedback mechanisms that ultimately determine the final mass of these stellar giants. Observing and studying stars like R136A1 provide crucial insights into the extreme limits of stellar physics and the dynamics of star formation in our universe. They serve as natural laboratories for understanding how the most massive stars live, shine, and eventually die, shedding light on the complex interplay of forces that shape the cosmos. The cosmic web is a vast, intricate structure of interconnected filaments of dark matter, gas, and galaxies weaving through the universe. This colossal network forms the backbone of the cosmos, dictating the large-scale distribution of matter and the organization of galaxies. Understanding its true nature provides profound insights into the formation and evolution of the universe itself. The cosmic web emerged from the slight density variations in the early universe, imprinted soon after the Big Bang. Under the influence of gravity, these minute fluctuations grew over billions of years, gradually pulling matter into filamentary structures. Dark matter, an invisible but dominant component of the universe's mass, played a crucial role in this process. It acted as a scaffolding, its gravitational pull drawing in ordinary matter to form the observable structures we see today. Within the cosmic web, galaxies and galaxy clusters are found at the intersections of these filaments, known as nodes. These regions are rich in matter due to the gravitational attraction of converging filaments, leading to the formation of vast clusters of galaxies. The filaments themselves, stretching across millions of light years, are less dense but crucial pathways along which galaxies migrate and interact. Telescopic observations and simulations of the cosmic web have revealed fascinating details. For instance, gas within the filaments can trace the movement and interaction of galaxies, shedding light on the processes of galaxy formation and evolution. Furthermore, these gas filaments serve as reservoirs of material that fuel star formation within galaxies and impact the dynamics of galaxy clusters at the nodes of the web. Understanding the cosmic web helps astronomers decipher the complex interplay between dark matter, gravity, and visible matter in shaping the universe. It also provides a context for studying the growth of cosmic structures from the smallest dwarf galaxies to the largest galaxy clusters, revealing the interconnected nature of the universe. By mapping and analyzing the cosmic web, scientists continue to uncover the hidden symmetries and forces that govern the cosmos, bringing us closer to comprehending the grand design of everything that exists. The apparent periodicity in the distribution of galaxies, often described as the cosmic oscillations or baryon acoustic oscillations, traces back to the early universe. BAOs provide crucial clues about how galaxies are distributed on large scales and offer a powerful standard ruler for measuring cosmic distances. In the early universe, the interplay between gravity and pressure created sound waves or acoustic waves within the hot plasma of protons, electrons, and photons. These waves propagated outward from overdense regions, creating regions of alternating compression and rarefaction. As the universe cooled and expanded, about 380,000 years after the Big Bang, it became transparent, and these sound waves were essentially frozen into place, imprinting their characteristic scale onto the cosmic matter distribution. This imprint manifests as a subtle but measurable periodicity in the spatial distribution of galaxies. Chains of galaxies, separated by a preferred scale of about 500 million light-years, reflect the length of these primordial sound waves. When we observe large-scale structures in the universe, these patterns in the galaxy distribution emerge, corresponding to peaks and troughs from the acoustic oscillations. To detect and measure BAOs, astronomers employ large-scale galaxy surveys, mapping the positions of millions of galaxies. Analyzing these maps reveals the characteristic scales of the oscillations, providing details about the universe's expansion history and the nature of dark energy. Importantly, BAOs serve as cosmic yardsticks, allowing precise measurements of distances in the universe and shedding light on the rate of its expansion. Understanding the periodicity in galaxy distribution through BAOs not only confirms fundamental aspects of cosmological models, but also offers practical tools for investigating the evolution of the cosmos. From the models that describe the universe's initial conditions to the dark matter and dark energy driving its expansion today, BAOs provide a vital link between theory and observation, revealing the deep-seated regularities woven into the fabric of the universe. The Fingers of God effect observed in galaxy surveys is an intriguing phenomenon that has its roots in the peculiar velocities of galaxies within clusters. When examining large-scale maps of the universe, This effect creates elongated, finger-like extensions of galaxy distributions pointing toward the observer, distorting the true positions of the galaxies in three-dimensional space. To understand this effect, one must consider how we measure galaxy distances using redshift. Redshift occurs when the light from galaxies is stretched to longer wavelengths due to the expansion of the universe. By measuring this redshift, astronomers can estimate the distance to galaxies, translating their observed positions into a coherent map of the universe. However, galaxies also possess individual motions relative to their local environment known as peculiar velocities. These velocities can be caused by interactions and gravitational pulls from nearby galaxies within a cluster. When galaxies within a cluster move, they have additional components to their velocities above those caused by cosmic expansion. This adds complexity to redshift measurements, leading to distortions. When plotting galaxies along the line of sight, their peculiar velocities cause apparent shifts in their redshifts. In relatively dense galaxy clusters, galaxies have significant peculiar motions toward and away from the observer due to mutual gravitational influences. These motions stretch the redshift data, artificially elongating the cluster along the line of sight and creating the fingers of God effect in redshift space. The true three-dimensional shape of the cluster gets smeared into elongated features, despite these galaxies being much closer together spatially. This effect highlights the importance of interpreting redshift data carefully, considering both cosmic expansion and individual galaxy motions. Correcting for the fingers of God requires sophisticated models and simulations that account for the dynamics within galaxy clusters. By doing so, astronomers can refine our maps of the universe and better understand the underlying structures and forces that shape the cosmos. Cosmic voids and supervoids are vast, empty regions in the universe where very few galaxies exist. These immense voids, ranging from tens to hundreds of millions of light-years across, form a striking contrast to the dense, bustling regions of the cosmic web where galaxies and clusters are found. Understanding the formation and significance of these voids sheds light on the large-scale structure of the universe and the forces shaping it. The formation of cosmic voids begins in the early universe, shortly after the Big Bang. Initially, the universe was nearly uniform, with tiny fluctuations in density. Over time, gravity amplified these fluctuations, causing matter to clump together in some regions while leaving others increasingly empty. Cosmic voids are essentially the leftover spaces where gravitational attraction was insufficient to pull significant amounts of matter together. As matter collapsed into sheets, filaments, and nodes forming the cosmic web, the areas in between became increasingly devoid of material. These underdense regions expanded relative to the denser areas, pushing galaxies and gas outwards. This self-reinforcing process continued, leading to the formation of the large, empty spaces known as voids and supervoids. While these voids can contain some matter, including dark matter, and even sparse galaxy populations, they are significantly less dense than surrounding regions. Cosmic voids are scientifically significant for several reasons. Firstly, they offer a unique environment to study cosmological principles and the behavior of dark energy, which drives the accelerated expansion of the universe. Because these voids expand more rapidly than denser regions, they provide a clean laboratory to observe the effects of dark energy and test cosmological models. Secondly, cosmic voids help refine our understanding of galaxy formation and evolution. By comparing the few galaxies within voids to their counterparts in more crowded areas, astronomers can investigate how different environments influence galaxy properties such as star formation rates, morphology, and chemical composition. This comparative analysis enhances our knowledge of the universal processes driving galaxy growth and transformation. Lastly, voids serve as crucial elements in the cosmic web, influencing the distribution and movement of matter across the universe. Studying the spatial and dynamic relationships between voids, filaments, and clusters help scientists form a more comprehensive picture of how gravitational and dark matter interactions sculpt the universe's large-scale structure. Thus, cosmic voids are vital to unraveling the grand tapestry of the cosmos. Cosmic strings are hypothetical, one-dimensional topological defects theorized to form during the early universe, particularly during symmetry-breaking phase transitions in the moments following the Big Bang. These cosmic strings would be incredibly thin but immensely massive, stretching across vast distances and potentially extending across the entire observable universe. To understand their nature, we need to delve into the theories of particle physics and cosmology. In the early universe, temperatures were extraordinarily high, and the fundamental forces of nature, gravitational, electromagnetic, weak nuclear, and strong nuclear forces, were unified. As the universe cooled, these forces began to separate or break symmetry through a series of phase transitions, much like how water freezes into ice. These phase transitions could leave behind defects, with cosmic strings being one possibility. Cosmic strings can be visualized as ultra-thin tubes of energy or mass where this symmetry breaking did not occur uniformly. They would have an enormous mass per unit length, leading to significant gravitational effects. Despite their immense energy, cosmic strings would be incredibly narrow, much thinner than a proton, but their lengths would be astronomical, potentially spanning millions of light years. If cosmic strings exist, they would have profound implications for our understanding of the universe. They could seed the formation of large-scale structures such as galaxies and clusters by acting as gravitational attractors. As they move and interact, cosmic strings might also produce gravitational waves, ripples in space-time, detectable by instruments like the Laser Interferometer Gravitational Wave Observatory and the Laser Interferometer Space Antenna. Astronomers have yet to find definitive evidence for cosmic strings, but ongoing searches involve looking for their potential gravitational lensing effects, where the string's immense gravitational pull bends light from background objects, creating characteristic line-like distortions. Additionally, cosmic strings should produce specific patterns in the cosmic microwave background, the afterglow of the Big Bang, which researchers continue to scrutinize. If confirmed, cosmic strings would offer incredible insights into the early universe's conditions and the unification of fundamental forces, bridging the gap between cosmology and particle physics. Their discovery would be a monumental step toward understanding the underlying laws governing the universe's birth and subsequent evolution. Galactic filaments, the colossal threads weaving through the cosmos, are among the largest known structures in the universe. These immense formations, stretching hundreds of millions of light years, are key components of the cosmic web, intertwining galaxies, clusters, and dark matter. Understanding their formation and evolution provides insight into the grand architecture of the universe and the processes that govern its growth. The origin of galactic filaments can be traced back to the early universe following the Big Bang. Initially, the universe was nearly uniform, but tiny quantum fluctuations introduced slight variations in density. These fluctuations were amplified by gravitational forces over time, causing matter to coalesce in some regions while other areas became less dense. This process set the stage for the cosmic web's filamentary structure. As the universe expanded and cooled, dark matter, which does not interact with light but exerts gravitational influence, played a critical role in shaping these filaments. Dark matter clumped together under gravity, forming a scaffold around which ordinary matter, composed of atoms, could gather. As gas and dust followed the gravitational pull of dark matter, they streamed along these scaffolding paths, creating the filaments. Galactic filaments act as highways of matter, channeling material toward denser nodes where galaxy clusters form. Within these filaments, galaxies and clusters move, interact and merge, influenced by the gravitational forces at play. The flow of gas through these structures also feeds the growth of galaxies within them, providing the raw material for star formation. Over billions of years, these interactions lead to a dynamic and ever-evolving cosmic web. Observing galactic filaments requires advanced techniques and powerful telescopes. By mapping the distribution of galaxies and detecting the slight distortions in the cosmic microwave background, scientists can trace the large-scale structure of the universe. Computer simulations of the universe's evolution from the Big Bang to the present also help visualize how these filaments form and evolve, offering a virtual laboratory to study their properties. Understanding galactic filaments is crucial for unraveling the universe's large-scale structure and the processes that govern its development. These vast cosmic threads not only illustrate the interconnected nature of the cosmos, but also provide a framework for studying the formation and growth of galaxies, the influence of dark matter, and the role of cosmic forces in shaping the grand tapestry of the universe. The Great Wall of Sloan, also known as the Sloan Great Wall, is an extraordinary large-scale structure in the universe, spanning about 1.37 billion light-years. It is composed of a vast array of galaxy clusters and superclusters appearing in a seemingly ring-like formation. Understanding the formation of such colossal structures involves delving into the intricate dynamics of cosmic evolution and the role of gravity over billions of years. The formation of the Sloan Great Wall, like other large-scale structures, is rooted in the early universe's density fluctuations. After the Big Bang, minute variations in the density of matter and energy existed. These fluctuations were amplified by gravitational forces over time, resulting in the clumping of matter into filaments, walls, and voids, forming the cosmic web. Gravitational attraction, acting over billions of years, caused matter to accumulate along these filaments and at their intersections, creating dense regions or superclusters. The Sloan Great Wall is essentially a collection of such superclusters interconnected by filaments of galaxies and dark matter. Its apparent ring-like structure is likely a projection effect, as we observe it from our position in the universe rather than a perfectly symmetrical ring. When mapped in 3 dimensions, these structures reveal more complex, network-like patterns that weave throughout the cosmos. The Sloan Great Wall's discovery was made possible through the Sloan Digital Sky Survey, which systematically mapped the positions of millions of galaxies. This large-scale survey provided an unprecedented view of the universe's structure, revealing the existence of these enormous cosmic formations. The detailed data from SDSS allowed astronomers to identify and measure the sizes and scales of such vast structures, confirming the predictions made by cosmological models about the distribution of galaxies. The significance of the Sloan Great Wall extends beyond its sheer size. It provides essential clues about the universe's composition and the forces that shape its architecture. Studying such structures helps astronomers refine theories of cosmic evolution, including the role of dark matter and dark energy. These immense walls and filaments serve as natural laboratories for understanding how galaxies form and evolve within the larger context of the cosmic web, enhancing our comprehension of the universe's grand design and intricate interconnections. The apparent alignment of quasars over vast cosmic distances has puzzled astronomers and stirred considerable excitement in the scientific community. Quasars are intensely luminous and energetic active galactic nuclei powered by supermassive black holes. Observations suggest that the spin axes of these distant quasars show a surprising degree of alignment across billions of light-years. Explaining this phenomenon requires examining both the large-scale structure of the universe and potential subtle interactions that extend over cosmic distances. One leading hypothesis for this alignment involves the influence of large-scale cosmic structures. Quasars reside within galaxies that are part of the cosmic web, connected by filaments of dark matter and gas stretching across the universe. These filaments form a known large-scale structure, with quasars located at the intersections of these filaments, where matter has collapsed to form galaxies and clusters. The alignment might stem from the orientation of these filaments themselves. If the spin axes of galaxies and their central quasars preferentially align with the direction of the cosmic filaments, this alignment could extend across vast distances. The filament's gravitational fields could induce a specific orientation during the process of galaxy formation, influencing how gas and dark matter collapse and spin, leading to a coherent alignment over large scales. Another possibility involves the influence of primordial magnetic fields or cosmic torsion at the time of the universe's formation. Such fields could have imprinted a specific orientation on the matter in the early universe, which carried through to the formation of quasars and their host galaxies. This hypothesis suggests that the initial conditions of the universe might have set the stage for the observed alignments, preserved as the universe expanded. Lastly, it's worth noting the potential role of observational biases or selection effects. The observed alignment might be influenced by the limitations and methods of our surveys. As astronomical instruments become more advanced and surveys grow more comprehensive, the statistical significance and interpretation of these alignments will be further refined. Ongoing and future observations, particularly by advanced telescopes like the James Webb Space Telescope and forthcoming large surveys, will deepen our understanding of quasar alignments. These studies will help uncover whether these alignments are indeed rooted in fundamental cosmological processes, or if they might be an artifact of observational techniques. Regardless, the phenomenon underscores the complexity and interconnectedness of cosmic evolution, driving our quest to unravel the mysteries of the universe at its grandest scales. The cold spot in the cosmic microwave background is an intriguing and anomalous feature that stands out in the otherwise uniform radiation left over from the Big Bang. Discovered through observations by the Wilkinson Microwave Anisotropy Probe and later confirmed by the Planck satellite, the cold spot spans a region of the sky with a temperature significantly lower than the average CMB temperature. The nature and origin of the cold spot have sparked considerable debate and fascination among cosmologists because it could potentially challenge our current understanding of the universe or hint at new physics. Here are several leading theories to explain its significance. One hypothesis suggests that the cold spot is a statistical fluke, a rare but possible deviation in the random fluctuations of the CMB, while these slight variations in temperature are expected due to quantum fluctuations in the early universe. The size and extent of the cold spot make it difficult to attribute solely to chance. Another compelling theory involves the phenomenon known as the integrated Sachs-Wolf effect. This effect occurs when CMB photons pass through large-scale structures like supervoids, the vast, underdense regions of space. As CMB photons travel through a supervoid, they lose energy and are redshifted, resulting in a lower observed temperature. Some researchers suggest that the cold spot could be aligned with a particularly extensive supervoid in the universe, lending credence to this explanation. There are also more speculative ideas proposing exotic physics. For instance, the cold spot might be a signature of a cosmic bubble collision, or evidence of interactions with another universe in the context of multiverse theories. These hypotheses are far-reaching and require significant evidence to substantiate, but they remain subjects of active investigation. Finally, the cold spot could point to unknown systematic errors in our data or instrumentation. Astronomers continue to scrutinize the methodologies and technologies used to capture and analyze the CMB to ensure the cold spot represents a genuine physical phenomenon. The significance of the cold spot extends beyond cosmic microwave background studies. By offering a unique feature to probe, it challenges existing cosmological models and prompts the search for more data and refined observational techniques. Understanding its underlying cause has the potential to reveal new insights about the early universe, the large-scale structure of the cosmos, and even fundamental physics itself. As research continues, the cold spot remains a focal point for uncovering deeper truths about our universe. The Bouteille's void is one of the most intriguing and mysterious features in the universe. Discovered in 1981, it is an enormous, nearly spherical region located in the constellation Bootes. Remarkably, this void spans roughly 330 million light-years in diameter, Imagine a place so vast that if our Milky Way galaxy were situated at its center, only a handful of galaxies would populate its expanse. Cosmologists believe such voids are a natural part of the large-scale structure of the universe. They think these voids formed as a consequence of the gravitational interaction between galaxies. In the early universe, the distribution of matter was not entirely uniform. Regions with slightly more mass than average began to attract more matter due to gravity, causing these areas to become denser over time. Meanwhile, regions with less mass lost out, leaving behind vast empty spaces. This process of matter redistribution eventually gave us the cosmic web structure we observe today, with dense clusters and strands of galaxies interspersed with enormous voids like buttes. What's particularly fascinating about the Bootes void is its contrast to other regions of the universe. While voids of various sizes are relatively common, the Bootes void stands out because of its immense size and the stark scarcity of galaxies within it. Initially, scientists thought such a large empty region should not exist. But subsequent studies have revealed that the universe indeed harbors these vast cosmic deserts. The existence of the Bootes void challenges our understanding and prompts new questions about the formation and evolution of the universe. What other hidden features might still be out there? Every discovery brings us closer to piecing together the cosmic puzzle, enhancing our comprehension of the universe's intricate tapestry. One of the great mysteries in cosmology revolves around identifying the elusive dark matter particles. Although dark matter does not emit, absorb, or reflect light, its presence is inferred from its gravitational effects on galaxies and clusters. Among the most compelling candidates for dark matter are WIMPs, axions, and sterile neutrinos, each offering intriguing possibilities. WIMPs, or weakly interacting massive particles, are among the frontrunners. These theoretical particles are thought to interact with normal matter only through gravity and the weak nuclear force, evading direct detection. WIMPs are hypothesized to be much heavier than protons or neutrons, which means they could contribute significantly to the overall mass of galaxies without emitting electromagnetic radiation. Axions present a different picture. These ultralight particles were originally proposed to solve a problem in particle physics known as the strong charge parity problem. If they exist, axions would have incredibly low mass and might interact very weakly with light. Researchers are exploring ways to detect axions by looking for their conversion into photons in the presence of strong magnetic fields, a process predicted by some theories. Lastly, sterile neutrinos offer another tantalizing possibility. Unlike their cousins, the regular neutrinos, sterile neutrinos do not interact via the weak nuclear force. Their existence is proposed based on certain extensions of the standard model of particle physics. If present, these sterile neutrinos could decay into ordinary neutrinos and photons, producing detectable signals in X-ray observations. Each of these candidates comes with its own set of challenges and requirements for detection. Experiments around the world, both underground and in space, are dedicated to hunting these elusive particles. Whether it is WIMPs, axions, or sterile neutrinos, solving the dark matter mystery will revolutionize our understanding of the cosmos. Dark energy plays a pivotal role in driving the accelerated expansion of the universe. First identified in the late 20th century, this mysterious form of energy counteracts the force of gravity, leading to an ever-increasing rate of expansion. Observations of distant supernovae provided the first compelling evidence, revealing that galaxies were not merely moving apart, but doing so at an accelerating pace. To comprehend how dark energy contributes to cosmic expansion, we need to delve into the concept of the cosmological constant, introduced by Albert Einstein. Einstein originally added this term to his equations of general relativity to support a static universe. However, once the universe was discovered to be expanding, he discarded it, calling it his biggest blunder. Ironically, the cosmological constant came back into relevance when dark energy was discovered, acting as a kind of repulsive force spread uniformly throughout space. Dark energy is believed to make up approximately 70% of the total energy content of the universe. Unlike matter and radiation, which become diluted as the universe expands, dark energy's density remains constant. This implies that as the universe grows, the influence of dark energy grows stronger relative to the other components. Therefore, the repulsive effect increases over time, leading to the observed acceleration in the universe's expansion. As researchers delve deeper into the nature of dark energy, alternative theories are also being explored. Some suggest it might be a property of space itself, while others propose it could be a dynamic field that evolves over time. Despite its mysterious nature, one thing is certain: understanding dark energy is fundamental to grasping both the past and future trajectory of our universe. Yes, dark energy could indeed be related to the vacuum energy of space, a concept rooted in quantum mechanics. The vacuum energy pertains to the idea that even in the seemingly empty void of space, there is a residual energy due to the constant fluctuations of virtual particles popping in and out of existence. This notion ties into the concept of the cosmological constant, which is one way scientists model dark energy in the context of space-time. In quantum field theory, the vacuum is not truly empty, but instead teeming with activity at the smallest scales. These quantum fluctuations give rise to a form of energy that permeates all of space. If this vacuum energy exerts a uniform, repulsive pressure, it could explain how the universe's expansion is accelerating. The cosmological constant, which Einstein initially introduced, can be thought of as a form of vacuum energy contributing to this accelerating expansion. The calculations involving vacuum energy are tricky, though. When theorists try to estimate the energy density of these quantum fluctuations, they come up with numbers that are many orders of magnitude larger than what we observe as dark energy. This discrepancy, known as the cosmological constant problem, remains one of the most significant puzzles in theoretical physics. Despite this, the connection between vacuum energy and dark energy is compelling because both concepts inherently involve the fabric of space itself. Some scientists are exploring whether what we term as dark energy is merely an observable manifestation of deeper quantum mechanical processes. Others postulate new fields or modifications to our understanding of gravity that could elucidate the nature of dark energy. While vacuum energy provides a promising clue, solving this mystery will require a synthesis of observational data and breakthroughs in theoretical physics, potentially reshaping our understanding of the universe's most fundamental properties. Scientists employ a range of sophisticated techniques and technologies to directly detect dark matter. One approach involves using ultra-sensitive detectors located deep underground, primarily in abandoned mines or beneath mountains. These locations help shield the detectors from cosmic rays and other background radiation that could obscure potential dark matter signals. The underlying idea is to capture the rare and extremely faint interactions between dark matter particles and regular matter. One prominent method focuses on detecting WIMPs. Detectors filled with noble gases like xenon or argon are carefully monitored for signs of these elusive particles. As WIMPs pass through the detector, they may collide with atomic nuclei, causing a flash of light or an ionization signal that can be recorded. These interactions are exceedingly rare, so experiments must be incredibly sensitive to distinguish genuine signals from noise. Another technique involves cryogenic detectors, which operate at temperatures close to absolute zero. These detectors rely on specific materials that can detect slight vibrations when a dark matter particle impacts the atomic lattice. By measuring minute temperature changes or phonons, which are quantized sound waves, scientists hope to identify the fleeting influence of dark matter particles. This method also requires shielding and precise calibration to minimize false positives. Recently, some scientists have turned to innovative technologies like quantum sensors and materials with unique properties that could interact with dark matter in novel ways. For example, researchers are exploring materials with low-level excitations known as magnons to detect specific types of dark matter particle interactions. Whether focusing on direct collisions or leveraging the latest advancements in quantum technologies, scientists constantly refine their strategies and instruments to catch the tiniest whisper of dark matter, gradually edging closer to one of the universe's most profound secrets. Dark matter plays a crucial role in the formation and evolution of galaxies. While it remains invisible and elusive, its gravitational influence is fundamental to the cosmic scaffolding upon which galaxies are built. In the early universe, dark matter's clumping under gravity created the initial seeds for galaxy formation, long before ordinary matter could cool and form stars and galaxies. Shortly after the Big Bang, the universe was a hot, dense plasma where regular matter was mostly ionized and could not easily clump together due to radiation pressure. However, dark matter, unaffected by electromagnetic forces, began to coalesce under its own gravity. These clumps, known as dark matter halos, provided gravitational wells that attracted ordinary matter. As the universe expanded and cooled, ordinary matter began to fall into these dark matter halos. The increased density led to the cooling and subsequent formation of stars, ultimately birthing galaxies. Without this dark matter scaffolding, the process would have been far slower and less efficient, possibly leaving the universe with vastly different structures, or perhaps even none at all. In present-day galaxies, dark matter continues to play an essential role. It forms an extensive, invisible halo around them, stabilizing their structure and affecting their rotation. Observations show that stars in the outer regions of galaxies rotate faster than they would if only visible matter were present. This discrepancy can be explained by the gravitational influence of dark matter, which outweighs visible matter by a significant margin. Thus, dark matter is not just a relic of the past, but remains an active and integral component of galaxies, underlining its enduring importance in the cosmos. The nature of dark energy holds profound implications for the ultimate fate of the universe. Understanding what dark energy is and how it behaves over time could reshape our predictions about cosmic destiny. If dark energy remains constant, increases, or diminishes, each scenario leads to a vastly different future for the universe. If dark energy is indeed a cosmological constant, as current observations often suggest, it implies that the universe will continue to expand at an accelerating rate indefinitely. This scenario, sometimes referred to as the Big Freeze or heat death, envisions a future where galaxies drift further apart, stars eventually burn out, and the universe becomes a cold, dark, and desolate expanse. In such a universe, matter would thin out as space expands, making it increasingly challenging for new stars and galaxies to form. However, if dark energy's properties change over time, we might witness different outcomes. One possibility is that dark energy could increase, causing an ever-accelerating expansion known as the Big Rip. In this dramatic scenario, the accelerating expansion would eventually overcome all gravitational and atomic forces, tearing apart galaxies, stars, planets, and even atoms themselves. The cosmic fabric would become so stretched that everything disintegrates at a fundamental level. Conversely, if dark energy were to weaken or dissipate, the universe's expansion might eventually halt and reverse. This could lead to a big crunch, where gravitational forces pull everything back together, culminating in a violent collapse. Some theories even propose a cyclical model, where the universe undergoes repeated cycles of expansion and contraction, potentially leading to successive Big Bangs and crunches. Determining the true nature of dark energy is one of the most significant pursuits in cosmology. Observations through telescopes and experiments studying cosmic microwave background radiation, supernovae, and large-scale structure aim to uncover clues. Whatever the outcome, the nature of dark energy will profoundly shape our understanding of the universe's future, guiding us toward a deeper grasp of cosmic evolution. Galaxy rotation curves are plots that show how the orbital velocity of stars and gas in a galaxy varies with their distance from the galaxy's center. When astronomers first mapped these curves, They expected orbital speeds to drop off with increasing distance from the center, similar to how planets in the solar system slow down the further they are from the sun. To their surprise, they found that the outer regions of galaxies rotate at nearly the same speed as regions closer to the center, defying expectations based solely on visible matter. This discrepancy provided some of the earliest and most compelling evidence for dark matter. According to Newtonian mechanics, the visible mass of a galaxy concentrated in stars and gas should dominate its gravitational behavior. Therefore, objects farther from the galactic center should exhibit slower rotational speeds. However, these flat rotation curves indicated that the gravitational pull remains strong even in regions with sparse visible matter. The most logical explanation for this phenomenon is the presence of an unseen mass, dark matter, creating additional gravitational forces. This unseen matter forms a halo around galaxies, extending far beyond the visible edge and interacting through gravity. By accounting for this extra mass, the observed rotation curves can be accurately explained. Without invoking dark matter, there is no way to reconcile the high velocities observed in the outskirts of galaxies with the amount of luminous mass present. Further studies have reinforced these findings across countless galaxies, making galaxy rotation curves a cornerstone of evidence for dark matter. Whether it is dwarf galaxies or giant spiral galaxies, the same flat rotation curves are observed, suggesting a universal presence of dark matter. This realization has led to a deeper exploration into the nature of dark matter, driving forward experiments and observations aimed at uncovering its elusive properties. Gravitational lensing offers a powerful tool for studying the distribution of dark matter in the universe. This phenomenon occurs when a massive object, like a galaxy cluster, bends the light of more distant objects behind it, such as galaxies or quasars. The bending of light acts like a cosmic magnifying glass, distorting and amplifying the images of background objects. By observing these distortions, scientists can map out the mass distribution of the lensing object, revealing the presence of dark matter. Gravitational lensing comes in two main forms: strong lensing and weak lensing. In strong lensing, the effects are dramatic and can produce multiple images, arcs, or even rings, known as Einstein rings, of the background source. These distinct, exaggerated distortions make it easier to model the mass distribution of the lensing object. Using these models, scientists can infer the presence and distribution of dark matter, which does not emit light but contributes significantly to the overall gravitational field. Weak lensing, on the other hand, involves subtler, more widespread distortions of background galaxies. Individual distortions are minute, but by statistically analyzing the shapes and orientations of many background galaxies, researchers can detect a coherent pattern caused by dark matter. This pattern allows them to create detailed maps of dark matter distribution across large areas of the sky. Such maps are instrumental in understanding the large-scale structure of the universe and how dark matter clumps and influences the formation of galaxies and clusters. One of the key advantages of gravitational lensing is its ability to provide direct information about the distribution of dark matter, independent of the visible matter. This method has produced some of the most compelling evidence for dark matter. For instance, observations of the Bullet cluster, a collision between two galaxy clusters, show a separation between the location of the visible matter and the dark matter, as inferred from lensing. These observations underscore dark matter's role and reinforce our understanding of its behavior and distribution on cosmic scales. The core cusp problem is a significant discrepancy between observations of dark matter distribution in galaxies and predictions derived from simulations. According to our best models using cold dark matter should form dense, cuspy centers or peaks in the middle of galaxies, particularly in dwarf and low-mass galaxies. These peaks are characterized by a steep rise in density toward the center. However, observations suggest that many galaxies, especially small satellite galaxies orbiting larger ones, have flatter, chord distributions, where the dark matter density remains relatively constant within the central region. The core cusp problem first came to light through measurements of the rotation curves of dwarf and low-surface brightness galaxies. These rotation curves indicated that the gravitational pull at the centers of these galaxies is weaker than what a cuspy dark matter profile would predict. In other words, the actual mass distribution appeared to be more spread out or chord rather than sharply peaked. Addressing this issue has spurred several theoretical and computational efforts. One possible explanation involves baryonic processes, which are the activities related to ordinary matter like stars and gas. For instance, interactions such as supernova explosions can blow out gas from the central region of a galaxy, redistributing energy and potentially flattening the dark matter cusp into a core. These feedback processes might explain why the observed dark matter profiles are less steep than anticipated. Another intriguing angle considers modifications to the nature of dark matter itself. Alternatives to cold dark matter, such as warm dark matter, could naturally create core structures due to their different behavior on smaller scales. Warm dark matter particles have higher velocities than cold dark matter, which could prevent them from clumping as tightly in the centers of galaxies, leading to flatter density profiles. The core cusp problem remains an area of active research and debate. Solving it could not only refine our understanding of dark matter, but also illuminate the complex interplay between dark matter and baryonic matter. This pursuit is crucial for piecing together a more accurate and comprehensive picture of galaxy formation and evolution. The interaction between dark matter and dark energy, if it exists, remains one of the most profound mysteries in cosmology. While dark matter and dark energy profoundly influence the universe, operating on different scales and through different mechanisms, current theories largely treat them as separate phenomena with minimal to no direct interaction. Dark matter, which accounts for about 27% of the universe's total energy content, primarily affects the universe through its gravitational pull. In contrast, dark energy, making up about 70%, acts as a repulsive force driving the accelerated expansion of space. One intriguing possibility is that dark matter and dark energy could be manifestations of a deeper underlying field or interaction. Some theoretical models propose that dark energy might slowly change over time and interact with dark matter, altering its properties or distribution. These models, known as coupled dark energy models, suggest that the equation of state of dark energy, which describes its pressure relative to its energy density, could evolve differently if there is an interaction with dark matter. Cosmologists explore these interactions by examining deviations from the standard cosmological model, which assumes no direct interaction between dark matter and dark energy. They look for signatures in the cosmic microwave background radiation, the large-scale structure of galaxies, and the precise measurement of the Hubble constant, the rate at which the universe expands. Any unexpected anomalies might hint at an interplay between dark matter and dark energy. As we acquire more data from sophisticated telescopes and experiments, our understanding of these mysterious components could evolve. If dark matter and dark energy do interact, it might lead to new physics that could revolutionize our understanding of the cosmos. For now, while intriguing theories abound, empirical evidence remains crucial to unraveling how these enigmatic forces in the universe might interplay, if at all. Quantum vacuum fluctuations are a fundamental aspect of quantum field theory, and their nature in intergalactic space is both fascinating and essential for understanding the vacuum's true nature. Unlike a classical vacuum, which is perceived as empty, a quantum vacuum is teeming with activity. It is a dynamic field where virtual particles continually pop in and out of existence, even in the seemingly empty expanses of intergalactic space. These fluctuations arise from the Heisenberg uncertainty principle, which states that there are limits to how precisely we can know certain pairs of physical properties, like position and momentum, or energy and time. Because of this inherent uncertainty, the vacuum cannot be completely static. Instead, It is a fluctuating sea of energy, with virtual particles appearing and disappearing on incredibly short timescales. In intergalactic space, these quantum vacuum fluctuations have subtle but significant effects. Although they are invisible to the naked eye, they contribute to phenomena such as the Casimir effect, where two uncharged parallel plates placed very close together in a vacuum experience an attractive force due to the suppression of certain vacuum fluctuations between them. This demonstrates that the vacuum has tangible properties and influences, even in the absence of traditional matter. Another profound implication involves dark energy, the mysterious force accelerating the universe's expansion. Some theories propose that dark energy might be related to this vacuum energy. If these quantum fluctuations contribute to a constant energy density throughout space, they could help explain the observed acceleration. This connection is speculative, yet it remains a compelling area of research, linking the microcosm of quantum physics to the cosmos's vast scale. Delving deeper into quantum vacuum fluctuations might unlock new understanding of fundamental physics, influencing everything from particle interactions to the nature of the universe's expansion. As our experimental techniques become more refined, we edge closer to unveiling the profound mysteries initiated by these seemingly ephemeral phenomena. Quantum tunneling plays a vital role in the processes occurring within the cores of stars, fundamentally impacting stellar evolution and energy production. At its core, quantum tunneling allows particles to pass through energy barriers that, according to classical physics, should be impenetrable. This seemingly magical process is crucial for nuclear fusion, the powerhouse behind stars. In stellar cores, temperatures and pressures are incredibly high, but not high enough to overcome the electrostatic repulsion between positively charged atomic nuclei when relying solely on classical mechanics. Specifically, the positively charged protons in hydrogen nuclei repel each other due to their similar charge. According to classical physics, the energy required for protons to collide and fuse is prohibitively high. However, quantum physics introduces a probabilistic nature that allows these particles to tunnel through the energy barrier. This quantum tunneling enables protons to come close enough to each other to overcome their electrostatic repulsion and initiate nuclear fusion. Once tunneling occurs and two protons come within short range, the strong nuclear force takes over and binds them together, forming a new element, generally beginning with deuterium in the sun's core. This process releases an enormous amount of energy, which is then radiated outward, powering the star and providing the heat and light that support life on planets like Earth. Quantum tunneling's role extends beyond just the fusion of protons. It is a key principle in various nuclear reactions within stars, including the fusion of heavier elements in more massive stars. As the star evolves and the core temperature rises, quantum tunneling facilitates the fusion of helium and other elements, forming the varied nuclei found throughout the universe. Ultimately, the seemingly improbable sequences of quantum tunneling ensure that stars can shine and forge new elements, driving the cosmos's chemical and energetic evolution. Quantum entanglement, one of the most intriguing and non-intuitive phenomena in quantum mechanics, might play a subtle yet profound role in the evolution of the universe. When two or more particles become entangled, their properties become linked, such that the state of one particle instantly influences the state of the other, no matter the distance separating them. This interconnectedness challenges our classical understanding of space and time and hints at deeper underlying principles that govern the universe's fabric. In the early universe, quantum entanglement could have influenced the distribution of matter and energy. During the inflationary period, a rapid exponential expansion immediately after the Big Bang, quantum fluctuations were stretched to cosmic scales. These fluctuations became the seeds for the formation of galaxies and large-scale structures. Quantum entanglement amongst these particles might have contributed to the coherence of these fluctuations, impacting the resulting pattern of cosmic microwave background radiation and the subsequent structuring of matter in the universe. Another potential area where quantum entanglement could play a role is in black holes and the information paradox. Entangled particles near the event horizon of a black hole might hold clues to resolving the paradox, whether information that falls into a black hole is lost forever or somehow preserved. Some theories suggest that entanglement might help preserve information at the event horizon, thus maintaining the principles of quantum mechanics even in the extreme conditions of a black hole. At a more speculative level, quantum entanglement might help elucidate the nature of space-time itself. The interconnectedness of entangled particles could be indicative of a fundamental, information-based substrate underlying the classical fabric of the universe. Some theories propose that space-time could emerge from a more profound entangled state, leading to new insights into the nature of gravity and unifying it with quantum mechanics. While these ideas remain at the frontier of theoretical physics, they open up exciting possibilities. As observational techniques and experimental methods improve, we might uncover deeper connections between quantum entanglement and the universe's evolution, potentially leading to groundbreaking advances in our understanding of the cosmos. Quantum effects are fundamental in shaping the extreme and unique properties of neutron stars. These remnants of massive stars after supernova explosions are incredibly dense, containing a mass comparable to our Sun, but compressed into a sphere only about 10 kilometers in diameter. At such densities, quantum mechanics takes center stage, dictating the behavior of matter in ways that defy our everyday experience. One of the most crucial quantum effects in neutron stars is the phenomenon governed by the Pauli exclusion principle. This principle states that no two fermions particles like neutrons, protons, and electrons can occupy the same quantum state simultaneously. In the context of a neutron star, where densities are extraordinarily high, the Pauli exclusion principle results in a state known as degeneracy pressure. For electrons and neutrons, this degeneracy pressure provides a force that counters gravitational collapse, effectively preventing the star from imploding further despite its immense mass. Additionally, neutron stars exhibit superfluidity and superconductivity within their cores, thanks to quantum effects. Superfluidity occurs when neutrons pair up in a manner similar to electrons in superconductors, forming Cooper pairs. Once paired, these neutrons can flow without any friction, an extraordinary state of matter unattainable under less extreme conditions. This superfluidity impacts the star's thermal properties and its rotation, including phenomena like glitches, which are sudden changes in the star's spin rate due to shifts in the superfluid interior. Magnetic fields in neutron stars can also reach staggering intensities, a testament to quantum electrodynamics. Surface magnetic fields can be trillions of times stronger than Earth's, influenced by quantum processes that compress the magnetic flux remaining from the original star. These intense fields lead to fascinating emissions and the formation of magnetars, a particular class of neutron stars with exceptionally powerful magnetic fields that cause extraordinary bursts of X-rays and gamma rays. Quantum effects not only prevent neutron stars from collapsing, but also create exotic states of matter and remarkable physical phenomena. Studying these stars offers a unique laboratory for exploring the laws of quantum mechanics under conditions that cannot be replicated on Earth, providing insights that enhance our understanding of both the micro and macroscopic realms of the universe. Quantum decoherence plays a crucial role in our understanding of cosmological observations by bridging the gap between the quantum and classical worlds. When we look at the universe on a quantum level, particles exist in a superposition state, where they can be in multiple states or places at the same time. However, what we observe on a macroscopic scale, like stars, galaxies, and cosmic events, is described by classical physics, where objects have definite positions and states. Decoherence happens when quantum systems interact with their environment, causing these superpositions to collapse into distinct outcomes. This interaction effectively washes out the quantum properties, making them appear more classical. For example, a single particle might be in a superposition of different locations, but when it interacts with other particles, these superpositions lose coherence, and it behaves as though it has a single, well-defined location. In cosmology, Quantum decoherence addresses why the universe behaves classically on large scales, despite being governed by quantum mechanics on the smallest scales. It explains how the early fluctuations in the quantum field eventually grew into the vast structures we see today, such as galaxies and clusters. These tiny quantum fluctuations were magnified during a period known as cosmic inflation. Then decoherence caused them to manifest in a classical manner, leading to the formation of the cosmic web. Furthermore, understanding quantum decoherence helps cosmologists predict and interpret phenomena such as the cosmic microwave background radiation. This ancient light carries imprints of the early universe, where decoherence processes would have determined how quantum fluctuations evolved to shape the large-scale structure of the cosmos. By bridging these two worlds, quantum decoherence not only deepens our understanding of the universe's origins, but also enhances our ability to make precise cosmological predictions and observations, giving us a richer and more complete picture of the cosmos. Quantum gravity, the as-yet unified theory merging quantum mechanics with general relativity, offers a potential resolution to the perplexing issue of singularities in black holes. Singularities represent points within black holes where densities become infinitely large and the laws of physics break down, creating a major theoretical conundrum. Current classical theories like general relativity predict these singularities, but they fail to describe what occurs at such extreme conditions. The quest for quantum gravity involves frameworks such as string theory and loop quantum gravity. These theories attempt to describe the fabric of spacetime on the smallest scales, where quantum effects cannot be ignored. Instead of singularities, quantum gravity posits that spacetime itself is quantized, forming a discrete structure much like the atoms in a crystal. One approach within quantum gravity, proposed by loop quantum gravity, suggests that the core of a black hole might not collapse into a singularity. Instead, spacetime could reach a minimum volume and then undergo a bounce. This quantum bounce implies that the extremely high densities never reach infinity. They only reach a maximum threshold before rebounding. It implies that what we consider a singularity might be a portal to another region of space or even another universe. String theory offers another intriguing possibility by introducing the concept of extra dimensions and fundamental strings rather than point particles. It suggests that the gravitational collapse leading to a black hole might spread out over additional dimensions, preventing the formation of a singularity. The extra dimensions provide the necessary space to diffuse the gravitational collapse, ensuring that physical laws remain consistent and finite. These quantum gravity approaches are still under development and not yet experimentally verified. However, they provide a compelling possibility that black hole singularities might be smoothed out by the underlying quantum structure of spacetime. If verified, such theories could redefine our understanding of black holes, shedding light on the deepest mysteries of the universe. In the extreme environments near black holes, the nature of virtual particles becomes particularly fascinating and crucial for understanding phenomena such as Hawking radiation. Virtual particles are transient fluctuations that spontaneously appear and disappear in the vacuum of space, a phenomenon predicted by quantum field theory. These pairs of particles and antiparticles exist for only an incredibly brief moment before annihilating each other. Near the event horizon of a black hole, the intense gravitational field adds an intriguing twist to the behavior of these virtual particles. According to Stephen Hawking, these pairs of particles can be separated by the black hole's immense gravitational pull. In some instances, one particle might fall into the black hole while the other escapes, thus becoming a real particle rather than remaining a virtual one. This process leads to what is known as Hawking radiation. The particle that escapes can be detected as radiation, while its counterpart, absorbed by the black hole, effectively reduces the black hole's mass. This means black holes can lose mass over time through this radiation, providing a potential mechanism for black hole evaporation. The concept of black holes radiating energy challenges the notion that nothing can escape a black hole, offering profound insights into the interplay between quantum mechanics and gravity. Moreover, the presence of virtual particles near black holes also stirs deeper questions about the nature of information and its preservation in the universe. If particles falling into a black hole carry information, and these particles interact with virtual particles near the event horizon, it raises inquiries about what happens to that information. This leads us to the black hole information paradox, a major unresolved issue in theoretical physics. Therefore, the study of virtual particles near black holes not only sheds light on how black holes emit Hawking radiation, but also nudges us closer to resolving some of the most profound questions in physics, highlighting the necessity of a unified theory that encompasses both quantum mechanics and general relativity. Quantum effects played a pivotal role in the early stages of galaxy formation by seeding the initial conditions that later grew into the vast structures we observe in the universe today. The story begins with the quantum fluctuations in the very early universe during a period known as cosmic inflation. This epoch, occurring just fractions of a second after the Big Bang, saw the universe expand exponentially, stretching out these infinitesimally small quantum fluctuations to macroscopic scales. These quantum fluctuations were variations in the density of the primordial quantum field, leading to slightly over-dense and under-dense regions in the early universe's distribution of matter. When cosmic inflation ended, the universe continued to expand at a slower rate, but those initial quantum perturbations had already set the stage for the gravitational pull needed to form structures. As the universe cooled and particles began to combine into atoms, these slight density variations allowed gravity to amplify the overdense regions, pulling in more matter and forming the early scaffolds of what would become galaxies. Essentially, quantum effects provided the seeds, and gravity acted as the gardener, nurturing these seeds into the cosmic structures spanning millions of light years. Moreover, evidence of these initial quantum fluctuations can be seen in the cosmic microwave background radiation. This ancient light, a relic from about 380,000 years after the Big Bang, carries imprints of the density variations caused by quantum effects. By studying these imprints with telescopes like the Wilkinson Microwave Anisotropy Probe and Planck, scientists can reconstruct the conditions of the early universe and understand better how galaxies, clusters, and eventually the complex structure of the cosmos formed. Therefore, quantum effects were not just a precursor, but a fundamental factor influencing the early stages of galaxy formation. By setting the initial conditions, quantum mechanics helped script the grand cosmic narrative, sculpting the universe from its uniform beginnings into the richly structured tapestry we observe today. Quantum fluctuations could potentially play a significant role in generating cosmic magnetic fields, which remain one of the more enigmatic features of the universe. The origin of these magnetic fields observed in galaxies, galaxy clusters, and even in intergalactic space has puzzled scientists for decades. One intriguing hypothesis links their genesis to the quantum fluctuations during the early universe, particularly during the inflationary period. During cosmic inflation, quantum fluctuations produced minor variations in the density of the primordial plasma. These tiny fluctuations became stretched to astronomical scales due to the rapid expansion of space. The dynamics of these fluctuations, influenced by the fundamental forces, could have created regions with tiny electric fields. According to Faraday's law of induction, changing electric fields can give rise to magnetic fields. Thus, the same quantum processes that seeded density variations might also have initiated primordial magnetic fields. As the universe continued to expand and cool, these initial quantum-generated magnetic fields could have served as the seed fields. Later astrophysical processes, such as the movement of ionized gases and astrophysical dynamos in stars and galaxies, would have amplified these seed magnetic fields to the strengths we observe today. This amplification is essential because the original quantum-generated fields would have been incredibly weak, but laid the groundwork for much larger magnetic fields. Further evidence comes from electromagnetic waves and relic fields detected in the cosmic microwave background radiation. These relics can contain information about electromagnetic processes from the early universe, providing clues about the initial conditions under which cosmic magnetic fields could have formed. While the exact mechanisms remain a topic of active research, the contribution of quantum fluctuations appears to be a promising avenue for explaining the initial generation of cosmic magnetic fields. Thus, quantum fluctuations not only help us understand the formation of large-scale structures, but also offer a plausible pathway for the emergence of the pervasive and powerful cosmic magnetic fields that weave through the fabric of the universe. By studying these relics and theoretical models, scientists hope to unravel yet another layer of the complex and captivating story of our cosmos. Quantum uncertainty profoundly impacts our understanding of the universe's initial conditions by introducing an intrinsic unpredictability into the early cosmos. At the heart of this concept lies Heisenberg's uncertainty principle, which states that it is impossible to simultaneously know both the exact position and momentum of a particle. This inherent uncertainty means that the universe's earliest moments were governed by probabilistic rather than deterministic laws. During the fleeting epoch known as cosmic inflation, quantum uncertainty played a critical role in shaping the foundational landscape of the universe. The rapid expansion stretched out quantum fluctuations, essentially magnifying the tiny uncertainties at the quantum scale to macroscopic scales. These fluctuations manifest as variations in density, temperature, and other physical properties throughout the cosmos. The regions with slightly higher density due to these fluctuations eventually gravitationally coalesced to form the galaxies, stars, and other structures we observe today. Furthermore, this quantum-induced variability extends to the cosmic microwave background radiation, an ancient light from roughly 380,000 years after the Big Bang. The minute temperature differences we detect in this background radiation are direct imprints of the quantum fluctuations. By studying these variations, scientists can backtrack to understand the initial conditions of the universe, despite their inherent uncertainty. Quantum uncertainty also challenges our ability to obtain a perfectly detailed and exact initial state of the universe. Instead, what we have is a probabilistic description informed by quantum mechanics. This brings a philosophical as well as a scientific conundrum. While we can predict the general evolution and structure of the cosmos, the exact blueprint will always remain just beyond our precise grasp. Quantum uncertainty introduces a fundamental probabilistic framework to the initial conditions of the universe. This perspective not only shapes our understanding of how the cosmos evolved from its early moments, but also signals a profound shift from determinism to a probabilistic nature at fundamental levels. The impact of quantum uncertainty continues to be a critical area of study, driving both theoretical research and observational efforts to peel back the layers of the universe's earliest moments. The nature of time in regions of extreme gravity, such as near black holes, behaves in ways that challenge our everyday intuition. In the framework of general relativity, gravity is not merely a force, but a curvature of space-time caused by massive objects. Near a black hole, this curvature becomes so intense that it dramatically affects the passage of time. As you approach a black hole, the gravitational pull grows stronger, warping space-time more severely. This warping causes time to slow down relative to regions of weaker gravity, a phenomenon known as time dilation. If an observer were to approach the event horizon, the boundary beyond which nothing can escape, their experience of time would differ starkly from that of an observer far away. To the distant observer, it would seem as though the individual near the black hole slows down, almost coming to a halt as they near the event horizon. Meanwhile, the person falling into the black hole would experience time normally according to their own clock. oblivious to the time dilation unfolding. This effect reaches its zenith at the event horizon. For an external observer, any object falling toward a black hole would appear to freeze in time and slowly fade away due to gravitational redshift, where light loses energy and shifts to longer wavelengths. However, for the falling object, the journey would continue, and from their perspective, they would cross the event horizon without noticing anything peculiar, albeit encountering extreme tidal forces. Once past the event horizon, the concept of time undergoes another profound transformation. In the dark heart of the black hole, known as the singularity, general relativity suggests that space-time curvature becomes infinite, creating a breakdown of known physical laws. Here, time and space could effectively switch roles. Instead of moving through space over time, it might be that moving through time becomes analogous to moving through space. Understanding the nature of time near black holes not only stretches the limits of general relativity, but also beckons for a unifying theory of quantum gravity. Such a theory might reconcile the strange temporal behavior near black holes with the laws of quantum mechanics, offering deeper insights into the true nature of time in the most extreme environments. The black hole information paradox presents a significant challenge in theoretical physics because it questions some of our most fundamental principles. This paradox arises from the apparent contradiction between quantum mechanics, which states that information is never lost, and our understanding of black holes, which suggests that anything falling into a black hole becomes irretrievably lost once the black hole evaporates via Hawking radiation. Stephen Hawking's theory of black hole radiation posits that black holes gradually lose mass and ultimately vanish, dispersing their energy back into the universe. However, if a black hole completely evaporates, what happens to the information about the physical state of everything it once absorbed? Quantum theory insists that information cannot be destroyed, leading to a collision with the idea that black holes obliterate information about their contents. One proposed resolution involves the concept of information recovery via Hawking radiation itself. Some theorists suggest that the subtle correlations in the emitted radiation could carry the scrambled information about the black hole's interior. While originally the radiation was thought to be purely random, it may encode these pieces of the puzzle in a way that, with a complete theory of quantum gravity, could be deciphered. Another intriguing approach comes from the holographic principle, posited independently by Gerard 't Hooft and Leonard Susskind. This principle suggests that all the information contained within a three-dimensional space, such as the interior of a black hole, can be represented on a two-dimensional boundary surface. In the context of black holes, this means that all the information about what falls into a black hole could be encoded on its event horizon, effectively a hologram of the black hole's entire interior. Furthermore, advances in string theory propose that black holes may have fuzzball structures, where information is preserved in a highly complex extended object without the need for singularities. This idea avoids the traditional singularity and ensures that information remains encoded within these intricate structures, albeit in forms we are still striving to understand fully. Ultimately, while several compelling theories exist, none have yet been universally accepted or empirically validated. Resolving the black hole information paradox remains one of the foremost quests in theoretical physics, bridging the gap between our understanding of quantum mechanics and general relativity, and will likely lead to groundbreaking revelations about the true nature of space, time, and information. If closed time-like curves exist in the universe, they would represent paths through spacetime that loop back on themselves, allowing for the possibility of time travel to the past. This concept, grounded in the equations of general relativity, opens a Pandora's box of paradoxes and profound implications. The most intriguing feature of CTCs is their potential to enable time travel, theoretically allowing an object or person to revisit earlier points in its own history. However, this possibility introduces several paradoxes. The most famous is the grandfather paradox, where a time traveler could potentially prevent their own existence by altering events in the past, such as preventing their grandparents from meeting. Logical contradictions like this challenge our current understanding of causality, which maintains that cause precedes effect. Physicists have proposed various ways to deal with these paradoxes. One idea is the self-consistency principle, suggesting that actions taken by a time traveler were always part of history. Hence, anything they do in the past cannot result in a paradox. This principle leads to a deterministic view where time travelers' actions contribute to the events they already know, ensuring no contradictions arise. Another compelling resolution involves the concept of alternate histories or parallel universes. In this framework, traveling back in time could create a new separate timeline where the time traveler's actions do not affect the original universe. This way, any changes in the past occur in a parallel universe, sidestepping paradoxes and preserving the causality in the traveler's original timeline. Moreover, closed time-like curves would have profound implications for our understanding of the universe's structure and the nature of time itself. Their existence could hint at regions of space-time with extraordinary properties, such as the interiors of certain spinning black holes, also known as Kerr black holes, or hypothetical exotic objects like wormholes. However, the creation of CTCs often requires conditions or materials with negative energy density, like those described by exotic matter, which remain speculative and unverified by experiments. While the existence of closed time-like curves remains a topic of intense theoretical inquiry and debate, their potential presence would radically alter our understanding of physics, causality, and the unfathomable complexity of space-time. Unraveling this mystery may require not just new theoretical insights, but groundbreaking experimental advancements. Quantum entanglement poses a formidable challenge to our traditional understanding of causality in space due to its unique property of creating correlations between particles that defy classical explanation. When two particles become entangled, their states become interdependent no matter how far apart they are. A change in the state of one particle instantaneously affects the state of the other, seemingly violating the principle that no information or influence can travel faster than the speed of light. This phenomenon, often referred to as spooky action at a distance by Albert Einstein, suggests that once particles are entangled, they share a collective state. Measuring the state of one particle determines the state of the other, a phenomenon that appears to happen instantaneously. This instantaneous correlation challenges the classical notion of local causality, which asserts that objects are influenced directly only by their immediate surroundings. Quantum entanglement has been empirically confirmed through numerous experiments, such as the famous Bell test experiments, which close loopholes exposing the non-local nature of entangled particles. These experiments demonstrate that entangled particles exhibit correlations that cannot be explained by any local hidden variables theory, thereby supporting the quantum mechanical prediction that entanglement fundamentally alters our classical understanding of how objects interact. This challenges our understanding of space-time and causality because it suggests that particles can be connected in a way that is not confined by spatial distance or temporal sequence. Some interpretations of quantum mechanics, like the many worlds interpretation, sidestep this issue by positing that all possible outcomes of a quantum event actually occur in a vast multiverse, with each outcome manifesting in a separate, non-communicating universe. On the other hand, the idea of quantum non-locality leads to fascinating implications for information theory and quantum computing. Entanglement is a key resource for quantum teleportation, a process where information about the state of a particle can be transmitted between entangled pairs across arbitrary distances without physically moving the particle itself. This phenomenon does not transmit information faster than light directly, but relies on the classical transmission of supplementary data, maintaining causality in a broader sense. Furthermore, the concept of entanglement potentially reconciles with space-time geometry in advanced theories. For example, the ER=EPR conjecture posits a bridge between quantum theory and general relativity, suggesting that entangled particles are connected via microscopic wormholes, also known as Einstein-Rosen bridges, providing a space-time explanation for the observed non-locality. Quantum entanglement forces us to reconsider fundamental notions of causality and locality, compelling physicists to explore new frameworks that might unify quantum mechanics with the fabric of space-time, thereby unveiling more profound insights into the nature of reality itself. The arrow of time, the concept that time seems to move in one direction from the past to the future, is rooted in various aspects of physics, philosophy, and our everyday experience. One of the primary explanations for this phenomenon lies in the second law of thermodynamics, which states that entropy or disorder in a closed system tends to increase over time. This principle forms the backbone of the thermodynamic arrow of time. In the early universe, just after the Big Bang, conditions were extremely ordered with low entropy. As the universe expanded and evolved, processes naturally led to an increase in entropy. This rise from order to disorder gives time its perceived direction, making events seem to move from low entropy states to high entropy states. For instance, a broken egg mixes into an omelette but doesn't spontaneously reassemble back into an egg, illustrating this irreversible process driven by entropy. Another perspective comes from the psychological arrow of time, which refers to our subjective experience of time passing. Human memory and cognition are structured such that we remember the past but not the future. This asymmetry shapes our understanding of causality and reinforces the perception that time flows forward. Our brain processes, which record and store information in one direction, add a psychological dimension to the arrow of time. Additionally, the cosmological arrow of time aligns with the expansion of the universe. Since the Big Bang, space itself has been expanding, creating a temporal framework where the past corresponds to a more condensed and hotter universe. This expansion offers a large-scale context in which time seems to progress in a single forward direction, from the highly ordered initial state to the complex and increasingly entropic universe we inhabit today. Quantum mechanics introduces another layer of complexity, though. At quantum scales, many processes are time-symmetric, meaning they can run equally well forward and backward in time. Yet when we observe quantum systems, the act of measurement introduces a sort of irreversibility, collapsing the wave function from a superposition of states to a single observed outcome. This process aligns more closely with our macroscopic experience of time's directionality, suggesting a bridge between quantum time symmetry and classical time's arrow. The true nature of the arrow of time remains an active area of research, particularly in efforts to reconcile these different arrows within a unified framework. The interplay of entropy, cosmological expansion, and quantum measurement may collectively contribute to the unidirectional flow of time observed in our universe, making it a profound and intriguing aspect of reality that encompasses multiple domains of physics and human experience. The apparent acausal nature of quantum mechanics stems from the fundamentally probabilistic nature of quantum events and the phenomenon of quantum non-locality. Unlike classical mechanics, where events unfold in a predictable linear sequence based on cause and effect, quantum mechanics operates on probabilities and wave functions that describe the likelihood of different outcomes. This probabilistic framework leads to situations that seem to defy classical notions of causality. One of the most striking manifestations of this acausality is quantum entanglement. When two particles become entangled, their properties become interconnected, such that the state of one particle instantaneously influences the state of the other, regardless of the distance separating them. This instantaneous correlation challenges the classical view that information can only travel at or below the speed of light. However, it is important to note that while entanglement creates correlations between distant particles, it does not allow for faster-than-light communication, preserving causality in a broader sense. The famous double-slit experiment also highlights quantum mechanics' causal nature. When particles such as electrons are fired at a barrier with two slits, they create an interference pattern on a screen behind the slits, indicating wave-like behavior. However, when one measures which slit the electrons pass through, the interference pattern disappears, and the electrons behave like particles. The act of measurement seems to retroactively affect the pathway the particles took, suggesting that the outcome is not determined until it is observed. This causal behavior is encapsulated in the concept of wave function collapse, where a quantum system remains in a superposition of states until it is measured. Upon measurement, the wave function collapses to a single state from the range of possible states, an event that appears inherently random and causal. The unpredictability of when and how this collapse occurs challenges the deterministic causality of classical physics. One theoretical attempt to reconcile these quantum features with causality involves the many worlds interpretation. According to this view, all possible outcomes of a quantum event actually occur, but in separate, non-interacting branches of the universe. This interpretation eliminates the need for wave function collapse, preserving a form of deterministic causality across a multiverse, though it does not align with our singular experience of events. Moreover, efforts in developing a theory of quantum gravity, which would unify quantum mechanics with general relativity, might provide deeper insights into these causal phenomena. Some approaches suggest that spacetime itself can be fundamentally probabilistic and interconnected in ways not fully comprehended by our current classical or quantum frameworks. The apparent acausality of quantum mechanics reveals the profound and often counterintuitive nature of the microscopic world, pushing the boundaries of our understanding of causality, locality, and the fabric of reality itself. While these quantum phenomena challenge classical causality, they open up new avenues for exploring the true nature of the universe at its most fundamental level. If tachyons, hypothetical particles that travel faster than light, were found to exist, the implications for our understanding of the universe would be profound and far-reaching. First and foremost, their existence would challenge the very foundation of Einstein's theory of relativity, which posits that nothing can exceed the speed of light. This theory underpins much of modern physics, defining the relationships between space, time, and energy. One of the most significant implications would be a re-evaluation of causality, the principle that cause precedes effect. In the context of relativity, faster-than-light travel translates to backward time travel in certain reference frames. This could theoretically allow for effects that precede their causes, introducing potential paradoxes similar to the grandfather paradox, where changes made in the past affect the present in logically inconsistent ways. This would destabilize our traditional understanding of temporal sequences and causation. Moreover, tachyons could offer a new mechanism for communication and data transfer. If we could harness these particles, it might enable instantaneous communication across vast cosmic distances, revolutionizing our ability to interact with distant parts of the universe. This would not only have practical applications for science and technology, but also elevate our understanding of information theory and signal transmission. On a more speculative front, the existence of tachyons might offer clues towards a deeper, more unified theory of physics. They could potentially be integrated into theories that seek to harmonize quantum mechanics with general relativity, such as string theory or other advanced theoretical frameworks. These particles could also help to explain unresolved cosmic phenomena or dark matter and dark energy if they interact with the known universe in currently undetected ways. Despite these tantalizing possibilities, it's important to note that no experimental evidence has confirmed tachyons' existence. Their hypothetical nature also leads to theoretical challenges, such as issues with their energy properties. In the framework of special relativity, particles faster than light would require imaginary mass and energies that complicate their physical plausibility. Finally, the discovery of tachyons would spur a wave of experimental advances and theoretical work to understand and harness these particles. It would likely lead to revisions of current physical laws, pushing the frontier of human knowledge and expanding our conception of what is possible within the universe. The existence of tachyons would not just be a revolution in physics, but a paradigm shift, necessitating new frameworks to understand and describe a universe where faster-than-light travel and communication are realities. Time dilation profoundly influences our observations of distant cosmic events, providing a window into the relativistic nature of time and space. Rooted in Einstein's theory of relativity, time dilation occurs due to the relative motion between observers or the presence of strong gravitational fields. This phenomenon means that time can appear to slow down or speed up depending on the observer's frame of reference. When we observe distant objects in the universe, such as galaxies or supernovae, we are often looking back in time. Light from these objects has traveled vast distances to reach us, sometimes taking millions or even billions of years. Because of the immense scales involved, the relativistic effects of time dilation become significant. For objects moving away from us at substantial fractions of the speed of light, due to the expansion of the universe, this relative motion causes their clocks to tick more slowly from our perspective. An observable consequence of this effect is the redshift of light from distant objects. As galaxies move away from us, their light stretches to longer, redder wavelengths due to the Doppler effect. This redshift not only gives us valuable information about the speed and distance of these objects, but also indicates the rate at which time is passing for them relative to us. For supernovae, the light curve, which describes the change in brightness over time, appears stretched. This time dilation effect means that distant supernovae seem to brighten and fade more slowly compared to similar events occurring closer to us. Gravitational time dilation also plays a critical role around massive objects, such as black holes. In regions with intense gravitational fields, time appears to slow down. When we observe material falling into a black hole, the photons emitted from this material experience redshift due to gravitational time dilation. To a distant observer, it appears as if the material's motion continually slows as it approaches the event horizon, never quite crossing it. This acts as a natural time lapse, allowing us to study the behavior of matter in extreme gravitational environments over extended periods. Furthermore, time dilation affects our cosmic models and measurements. When we fit observational data to cosmological models, we must account for the time dilation effects to accurately describe the history and evolution of the universe. This includes determining the age of distant astronomical objects and understanding the timeline of cosmic events, such as the formation of galaxies, stars, and large-scale structures. Time dilation enriches our comprehension of the universe, bridging the gap between theory and observation. By taking into account these relativistic effects, we can derive more accurate models of the cosmos, offering deeper insights into its past, present, and future. This careful consideration of time's fluidity helps to peel back the layers of the universe's grand narrative, providing clearer views of distant and ancient cosmic events. The nature of time before the Big Bang is a profoundly complex and speculative question that stretches the boundaries of our understanding of physics and cosmology. According to the standard model of cosmology, the Big Bang represents the origin of not only the observable universe, but also of time itself. Consequently, asking about a before the Big Bang is akin to asking what lies north of the North Pole. It becomes a question that challenges the very framework within which we understand space and time. Einstein's general theory of relativity describes how mass and energy warp space-time, leading to the concept that time as we understand it began with the Big Bang singularity. In this framework, talking about time before the Big Bang might be meaningless because time itself is a property that emerged with the Big Bang. Time, as we measure and perceive it, is intrinsically linked to the expansion and evolution of our universe from that initial explosion. However, several theories attempt to conceptualize what might have preceded or accompanied the Big Bang. One such theory is the idea of a cyclic universe, where the Big Bang is just one phase in a perpetual cycle of expansion and contraction. In this view, our current universe might be one of many, with each cycle effectively resetting the conditions for a new Big Bang after a big crunch or a similar event in a previous cycle. Another intriguing line of thought comes from quantum cosmology and theories such as loop quantum gravity, which propose that the Big Bang was not a singular beginning, but a quantum transition from a previous phase. In these models, time could exist in a fundamentally different form before the Big Bang, structured in a manner that we might currently find difficult to comprehend. For instance, loop quantum gravity suggests that the universe could have experienced a bounce, where a previous contracting phase rebounded into the expansion phase we see today. String theory also offers speculative ideas, including the notion that our universe could be a brane within a higher dimensional space. In such scenarios, interactions with other branes in a higher dimensional space could have led to the Big Bang, making time before our Big Bang meaningful only in the context of a larger multidimensional framework. While these theories provide fascinating possibilities, it is important to note that they remain speculative and far from empirically verified. The limitations of our current understanding and technology mean that exploring these ideas is more about pushing the boundaries of theoretical physics than providing definitive answers. The nature of time before the Big Bang, if such a concept is meaningful, invites us to rethink the very fabric of reality and continue the quest for a deeper understanding of the universe. As we advance in both theoretical frameworks and observational technology, we may inch closer to unraveling these profound cosmological mysteries, opening new frontiers in the study of time and existence. When diving into the curious realm of the multiverse, we encounter a variety of models, each with its own intriguing take on the concept of time. While every model imagines our universe as just one slice of a grander reality, they each paint a unique picture of how time itself might behave across this infinite landscape. The bubble universe model, often associated with the theory of eternal inflation, suggests that our universe is one of many that have formed in a continually inflating space. In this scenario, each bubble or universe could have its own timeline, distinct from others. Time in our bubble could move forward in a completely different rhythm compared to the timeline in a neighboring bubble. Another fascinating perspective comes from the many worlds interpretation of quantum mechanics. This model posits that every possible outcome of a quantum event actually occurs but in separate branching universes. In this framework, time functions much like a sprawling tree with countless branches, each representing a different history and future based on every possible quantum decision. Here, time is not a single river, but a vast and ever-dividing network. String theory's brane multiverse introduces another captivating vision. In this concept, our universe resides on a brane, short for membrane, floating in a higher dimensional space with other branes potentially hosting their own universes. Time on each brane could operate independently, influenced by its own physical laws and conditions. The interaction between these branes might even cause collisions that give birth to new universes with their own timelines. Thus, the multiverse is a patchwork of theories, each with a unique interpretation of time. Whether time is branching, bubbling, or brane-bound, these models expand not just our understanding of the cosmos, but also our imagination's reach towards the infinite. Quark-gluon plasma is an incredibly dense and hot state of matter that existed in the earliest moments of our universe, right after the Big Bang. Imagine a cauldron of fundamental particles so energetic that protons and neutrons themselves break down into their constituent parts, quarks and gluons. This plasma represents a form of matter where the building blocks of protons and neutrons are freed from their usual confines. The unique nature of quark-gluon plasma lies in its extreme conditions. At temperatures reaching several trillion degrees Celsius, quarks, the tiny particles that make up protons and neutrons, and gluons, the particles that glue quarks together, can move freely rather than being bound tightly together. This creates a liquid-like state where these particles interact in ways that are impossible in normal matter. Where might this exotic form of matter exist today? Primarily, quark-gluon plasma is thought to have existed just microseconds after the Big Bang, before cooling and condensing into the matter that makes up the universe. However, scientists can recreate this primordial soup in high-energy particle colliders. For instance, facilities such as the Large Hadron Collider in Europe and the Relativistic Heavy Ion Collider in the United States smash heavy atomic nuclei together at near-light speeds, generating the tremendous energies required to produce quark-gluon plasma momentarily. These brief moments of creation help physicists to explore this exotic state of matter and probe conditions similar to those that occurred at the birth of the universe. By studying quark-gluon plasma, researchers aim to unlock secrets about how the fundamental forces and particles evolved, shedding light on the very building blocks of everything we see around us today. Strange matter is a hypothetical form of matter thought to be even more stable than the typical matter we encounter daily. Composed of strange quarks in addition to the more familiar up and down quarks that form protons and neutrons, strange matter is predicted to exist in a unique and highly compact state. If it exists, it could have profound effects on the structure of neutron stars, the incredibly dense remnants of supernova. Neutron stars themselves are already fascinating objects. They pack a mass greater than the Sun's into a sphere roughly the size of a city, making them one of the densest forms of matter known. In such extreme environments, the intense pressure might force neutrons to break down, allowing the formation of quark matter, potentially including strange quarks. If strange matter forms under these pressures, it could lower the energy state within the star, making it even more compact and stable. This potential transformation could lead to the existence of strange stars or quark stars. Unlike typical neutron stars, strange stars would contain a uniform quark matter core enveloped by a thin crust of normal matter. This quark matter core would consist of strange matter, which might make the star significantly denser and possibly smaller than standard neutron stars. An interesting consequence of this increased density might be an altered gravitational field, affecting how the star interacts with its surroundings. Observationally, strange stars could exhibit slight differences in properties compared to neutron stars, such as variations in their rotational behavior or thermal emission patterns. Detecting these subtle signatures might provide clues about the true nature of matter under such extreme conditions. Through continued observations and research, scientists hope to uncover more about how these bizarre forms of matter influence the cosmos's most mysterious objects. The concept of symmetric-asymmetric matter in the universe addresses one of cosmology's greatest puzzles, the striking imbalance between matter and antimatter. According to the symmetry principles of physics, the Big Bang should have produced equal amounts of matter and antimatter. If this were the case, matter and antimatter would annihilate each other upon contact, leaving the universe filled with only energy. Yet our universe is overwhelmingly dominated by matter, with only trace amounts of antimatter observed. Symmetric matter refers to the idea that in the early universe, matter and antimatter were created in equal quantities. This symmetry poses a conundrum since it would imply that we should see evidence of both everywhere. However, what we actually observe is primarily matter-making galaxies, stars, planets, and essentially everything we know. This discrepancy suggests that some mechanism must have caused a slight excess of matter over antimatter, breaking the symmetry. This brings us to asymmetric matter, which refers to the actual state of our universe. The theorized mechanisms that could explain this imbalance involve processes that occurred during the era of baryogenesis, a period shortly after the Big Bang when conditions might have favored the creation of more matter particles over antimatter particles. Various theories, including those involving charge parity violation, attempt to explain how this asymmetry arose. CP violation implies that the laws of physics might change slightly when particles are swapped with their antiparticles and then reflected in a mirror, leading to an excess of matter. Understanding the significance of symmetric-asymmetric matter helps us delve into the fundamental rules that governed the universe's birth and evolution. It raises profound questions about why we exist at all, since, without this asymmetry, the annihilation of matter and antimatter would have left the universe a barren sea of radiation. By unraveling this mystery, scientists aim to gain deeper insights into the forces and conditions that shape the universe, offering clues about the nature of the fundamental laws that govern reality itself. Ultra-diffuse galaxies are mysterious cosmic structures that intrigue astronomers due to their large size but faint nature. These galaxies spread their stars over a vast area, making them appear ghostly and difficult to detect. Unlike typical galaxies that are dense and bright, ultra-diffuse galaxies have unusual properties that challenge our understanding of galaxy formation and evolution. One explanation for their existence lies in their dark matter content. Dark matter is an invisible substance that exerts gravitational forces, influencing the motion of stars and gas within galaxies. Ultra-diffuse galaxies seem to have a high ratio of dark matter to visible matter. This abundance of dark matter could help keep the galaxy gravitationally bound despite its sparse star population. Such a scenario can explain their extended sizes and low surface brightness. Another factor causing their unusual properties might be their formation history. Some ultra-diffuse galaxies could be failed galaxies that started out similarly to normal galaxies but lost much of their gas due to interactions with nearby galaxies or supernova explosions. These processes would have stripped them of the material needed to form new stars, leaving behind a skeleton of what could have been a typical galaxy, now only sparsely populated with stars. Observations suggest that ultra-diffuse galaxies have varying amounts of spherical clusters, known as globular clusters, compared to their more familiar galactic counterparts. Some ultra-diffuse galaxies, like the ones in the Coma cluster, are found to have an unusually high number of globular clusters, indicating a fascinating piece of their evolutionary puzzle. The presence and amount of these clusters offer clues about the galaxy's origins and how they've interacted with their environment over time. Through continued study and observations, particularly with advanced telescopes, astronomers hope to uncover more about these enigmatic structures. Understanding ultra-diffuse galaxies not only sheds light on the diversity and complexity of galactic forms, but also aids in unraveling the larger narrative of cosmic development and the role of dark matter in shaping the universe. Dark fluid is a fascinating and theoretical concept that merges two of modern cosmology's biggest mysteries, dark matter and dark energy. These two components together constitute about 95% of the universe's total mass energy content, yet they behave very differently. Dark matter appears to exert gravitational pull, holding galaxies together, while dark energy drives the accelerated expansion of the universe. The idea behind dark fluid suggests a single entity that could account for both these phenomena. The nature of dark fluid is hypothesized to be dynamic, capable of behaving like dark matter in certain contexts and dark energy in others. This dual behavior is incredibly intriguing. In regions where the density is high, such as within galaxies, dark fluid would exhibit properties similar to dark matter, creating the gravitational effects needed to hold stars and gas within galaxies. Conversely, in the vast, low-density reaches of intergalactic space, the dark fluid would act more like dark energy, contributing to the repulsive force that drives the accelerated expansion of the cosmos. This duality could provide a more unified theory and simplify our understanding of the universe. One way to imagine dark fluid is to think of it as a chameleon, adapting its properties based on environmental conditions. In denser regions, it clumps and gravitates, while in emptier stretches of space, it induces a push, facilitating cosmic acceleration. Attaining direct evidence for dark fluid remains a profound challenge. Unraveling its true nature would require exquisite observations and advanced theoretical modeling. Future missions and studies focusing on large-scale cosmic structures, galaxy rotations, and the universe's expansion history will hopefully provide further insights. If proven true, dark fluid could revolutionize our understanding of the universe's composition and the fundamental forces that govern it. This unifying perspective holds the promise of connecting disparate phenomena under a single elegant banner, offering profound new insights into the very fabric of our cosmos. Mirror matter is a theoretical concept suggesting that, alongside the familiar particles that make up our universe, there exists a parallel set of mirror particles. These mirror particles would be counterparts to every known particle, possessing similar properties but interacting mightily weakly with ordinary matter. The notion of mirror matter stems from efforts to restore symmetry in the laws of physics, particularly focusing on parity symmetry, which deals with how physical processes behave under spatial inversion. The existence of mirror matter could significantly alter our understanding of the cosmos. It offers an intriguing possible explanation for some of the universe's most puzzling phenomena. For instance, mirror matter could account for certain dark matter properties. While dark matter doesn't interact electromagnetically, which makes it invisible to our instruments, it exerts gravitational forces. Mirror matter, interacting primarily through gravity, could provide just the properties needed to clump around galaxies and influence their rotational dynamics without being directly detected. Another tantalizing implication of mirror matter involves enigmatic cosmic events like collisions between galaxies. If galaxies contain significant amounts of mirror matter, their collision dynamics could exhibit differences compared to interactions involving just ordinary matter. This additional component might shed light on the formation and behavior of large-scale structures in the universe. In terms of experimental detection, mirror matter is challenging to find due to its weak interactions with ordinary matter. Nonetheless, researchers suggest that mirror matter could occasionally interact with normal matter through rare processes, leaving unique signatures. Advanced detectors designed to capture such faint signals may someday provide the first clues of this unseen component. Understanding mirror matter could open new avenues in particle physics and cosmology, offering a richer framework for explaining the universe's composition and behavior. It underscores the ongoing quest to discover whether our universe has hidden symmetries and partners, subtly influencing the observable cosmos. Unlocking the secrets of mirror matter would not only illuminate dark corners of the universe, but also refine our grasp of the fundamental laws that sculpt reality. Bose-Einstein condensates are extraordinary states of matter that occur at temperatures barely above absolute zero. Named after physicists Satyendra Nath Bose and Albert Einstein, these condensates are formed when particles known as bosons are cooled to such an extent that they occupy the same space and quantum state, essentially behaving as a single quantum entity. This unified quantum state enables scientists to explore quantum mechanics on a macroscopic scale, revealing the fascinating intersection between quantum and classical physics. The significance of Bose-Einstein condensates extends even further when considered in the context of space. Forming these condensates in a microgravity environment, such as aboard the International Space Station, offers unique advantages. On Earth, gravity can interfere with the ultra-precise conditions required to maintain these condensates. In microgravity, however, researchers can sustain Bose-Einstein condensates for longer periods, allowing for more detailed and extended experiments that delve deeper into their quantum properties. Studies of Bose-Einstein condensates in space can provide insights into fundamental physics. For example, observing how these condensates behave in a zero-gravity environment can offer clues about quantum coherence, superfluidity, and phenomena like quantum phase transitions. This research can also contribute to our understanding of how quantum mechanics governs large-scale structures, potentially informing theories that bridge the gap between quantum mechanics and general relativity. Moreover, practical applications of this research could revolutionize technologies reliant on quantum mechanics. Enhanced understanding of quantum states could lead to advancements in quantum computing, precision measurements, and sensor technologies. These developments possess the potential to redefine areas ranging from global communications to navigation systems. The exploration of Bose-Einstein condensates in space is a frontier where the strange and counterintuitive world of quantum physics is mapped onto the grand sublime expanse of the cosmos. This convergence allows scientists to probe deeper into the universal principles that govern both the very small and the unimaginably large, offering profound revelations about the nature of reality itself. Psi. Cosmic strings are theoretical one-dimensional defects that could have formed during phase transitions in the early universe, much like the cracks that form in ice as water freezes. Although hypothetical, these cosmic strings are incredibly fascinating because of their immense mass and tension, stretching across vast distances. If they exist, cosmic strings could significantly influence the process of galaxy formation in several intriguing ways. Firstly, cosmic strings are predicted to warp space-time around them due to their extreme energy density. This warping effect would lead to strong gravitational influences. If a cosmic string were moving through space, it could act as a gravitational attractor, pulling matter towards it. This concentration of matter could seed the formation of galaxies, providing the necessary density fluctuations that eventually lead to the clumping and condensing of gas into stars and galaxies. Another effect of cosmic strings on galaxy formation could come from their interaction with primordial matter. These strings might create disturbances in the distribution of dark matter and gas in the early universe. Such disturbances could accelerate the collapse of dense regions, further aiding in the early stages of galaxy formation. Essentially, cosmic strings could serve as the scaffolding around which matter could gather, speeding up the process that leads to galaxy creation. Observationally, the presence of cosmic strings could leave distinctive imprints in the cosmic microwave background radiation, the afterglow of the Big Bang. These imprints would appear as small fluctuations or anomalies in the otherwise uniform background, offering potential evidence of cosmic strings' influence on early structure formation. Advanced observational tools and techniques could help identify these signals, providing indirect proof of cosmic strings' role in shaping the cosmos. Exploring the existence and influence of cosmic strings offers a fascinating glimpse into how the large-scale structure of the universe could be interwoven with these fundamental entities. Unlocking their role in galaxy formation could deepen our understanding of the universe's early dynamics and offer new insights into the fundamental forces that govern cosmic evolution. Dark atoms and dark photons are fascinating concepts that expand our understanding of dark matter, proposing that it may not be entirely exotic but rather composed of elements somewhat analogous to ordinary matter, albeit invisible and undetectable through conventional means. The idea behind dark atoms is that, just as ordinary atoms are composed of protons and electrons bound by electromagnetic forces, dark atoms would consist of dark matter particles bound by analogous forces, potentially mediated by dark photons. These theoretical particles would interact with each other through a dark electromagnetic force, but would have extremely weak or no interaction with regular matter and regular photons, the particles of light. Dark photons in this context are the carriers of the dark force, mirroring how ordinary photons mediate the electromagnetic force among charged particles. The existence of dark photons implies that dark matter might be more complex than we previously thought, having its own set of interactions and structures. Although dark photons would not interact with ordinary matter significantly, they could interact with dark matter, allowing for a richer and more detailed dark sector. Understanding dark atoms and dark photons could offer new insights into the behaviors and properties of dark matter. For example, dark atoms could cluster under their own dark electromagnetic interactions, forming dark structures or contributing to the formation of galaxies in ways subtly different from what dark matter physics currently suggests. This could lead to new models explaining the distribution of dark matter in the cosmos and its role in galaxy formation and behavior. Detecting or confirming the existence of dark atoms and dark photons remains an enormous scientific challenge. Researchers look for indirect evidence through astrophysical observations and specialized experiments designed to detect minuscule interactions between dark and ordinary matter. For instance, certain astronomical observations, like the detailed study of cosmic background radiation or galaxy cluster dynamics, could reveal anomalies hinting at the presence of dark interactions. The hypothesis of dark atoms and dark photons enriches the dark matter narrative, suggesting that our universe comprises a hidden complexity paralleling the familiar world of protons, neutrons, and electrons. Unraveling this potential dark sector might not only provide profound insights into the nature of dark matter, but could also redefine our conception of matter and forces fundamentally. Primordial black holes are hypothetical black holes that could have formed in the very early universe, shortly after the Big Bang. These black holes are different from the ones we typically think of, which form from the collapse of massive stars at the end of their life cycles. If primordial black holes exist, they could profoundly influence our understanding of cosmic evolution in several key ways. Firstly, primordial black holes could offer an alternative explanation for dark matter. Unlike other candidates for dark matter, such as weakly interacting massive particles, primordial black holes are composed of ordinary matter but collapsed into incredibly dense objects. If these black holes were abundant in the early universe, they could account for a significant portion of dark matter. Their presence would affect the gravitational behavior of galaxies and galaxy clusters, shaping their formation and evolution. Another intriguing aspect of primordial black holes involves their potential role in seeding the growth of supermassive black holes found at the centers of galaxies. These ancient black holes could have acted as gravitational seeds around which matter clusters over time, accelerating the formation of much larger black holes. This process could provide insights into how supermassive black holes could form so quickly in the early universe, helping to solve one of cosmology's enduring mysteries. Primordial black holes might also leave detectable imprints in the cosmic microwave background radiation, the afterglow of the Big Bang. As they form and interact in the early universe, they could create gravitational waves or other signals that might be captured by advanced observational tools. Studying these imprints allows scientists to look further back into the history of the cosmos and understand the conditions that prevailed during the universe's infancy. Furthermore, the existence of primordial black holes could impact the rate and nature of cosmic events like gamma-ray bursts or supernovae. If primordial black holes are involved in these high-energy phenomena, they could influence our understanding of the sources and mechanisms behind these events, adding an extra layer of complexity and insight into our models of the universe. Overall, confirming the existence of primordial black holes would open new pathways to understanding the evolution of the cosmos, from the formation of galaxies to the mysterious nature of dark matter. Investigating these ancient relics could provide invaluable data about the universe's formative moments, offering a deeper comprehension of the intricate tapestry that makes up our cosmic history. The enormous magnetic fields observed in some galaxy clusters are a fascinating puzzle for astrophysicists. These fields, spanning millions of light-years, are far stronger than those found in individual galaxies and indicate complex, dynamic processes at work on a cosmic scale. Several mechanisms are believed to contribute to the generation and amplification of these colossal magnetic fields. Initially, seed magnetic fields are thought to arise from primordial processes in the early universe. These weak magnetic fields could be a result of fluctuations in the density and temperature in the cosmos immediately after the Big Bang. As the universe evolves, these weak seed fields undergo significant amplification through a process known as the dynamo effect. In this context, the dynamo effect involves the interaction between turbulent motions of gas within the galaxy cluster and the seed magnetic fields, gradually strengthening them to the immense scales we observe today. Another crucial factor contributing to these vast magnetic fields is the movement and interaction of galaxies within the clusters. Galaxy clusters contain thousands of galaxies, each carrying its own magnetic field. As these galaxies move and occasionally collide, their magnetic fields can merge and stretch, influencing the cluster's overall magnetic structure. The turbulent intracluster medium, the hot ionized gas filling the spaces between galaxies, also plays a key role by enabling the magnetic field lines to tangle and stretch, leading to further amplification. Cosmic scale phenomena such as active galactic nuclei jets also contribute to the magnetization of galaxy clusters. AGNs, found at the centers of some galaxies, can emit powerful jets of plasma and particles at nearly the speed of light. These jets can propagate across galaxy clusters, dragging magnetic fields along and injecting turbulent energy into the intracluster medium. This activity helps to stir and amplify the magnetic fields, contributing to their vast scale and strength. By studying these enormous magnetic fields, scientists can uncover clues about the physical conditions and processes occurring in galaxy clusters. Observations made through radio telescopes, which detect synchrotron radiation, a type of electromagnetic radiation emitted by charged particles spiraling along magnetic field lines, are particularly valuable. These observations can map the structures and strengths of magnetic fields across clusters, offering insights into the complex interactions shaping our universe on the largest scales. Understanding the origin and evolution of these gigantic magnetic fields not only enhances our knowledge of galaxy clusters, but also provides broader insights into cosmic magnetism's role throughout the universe, influencing star formation, galaxy evolution, and even the behavior of cosmic rays. By piecing together this cosmic magnetic puzzle, we can better appreciate the turbulent, dynamic nature of the cosmos. Cosmic magnetic fields play a critical role in the propagation of high-energy particles, often referred to as cosmic rays, throughout the universe. These invisible magnetic structures act as cosmic guides, deflecting and altering the trajectories of fast-moving particles as they travel through space. Their influence is profound and multifaceted, affecting both the paths these particles take and the energy they carry. Firstly, cosmic magnetic fields cause charged particles such as protons and electrons to spiral along magnetic field lines rather than move in straight lines. This spiraling motion results from the Lorentz force, which is the force exerted on a charged particle moving through a magnetic field. Depending on the magnetic field's strength and orientation, this force can significantly change the velocity and direction of cosmic rays, leading to a variety of travel paths, from complex loops and spirals to extensive detours across interstellar and intergalactic space. In the context of galaxy clusters and the Milky Way, these magnetic fields can trap and confine high-energy particles, creating intricate networks of particle motion. Within the Milky Way, the galaxy's magnetic field ensnares cosmic rays, leading them through a twisted journey across the spiral arms and interstellar medium. This scattering effect causes cosmic rays to take longer to traverse the galaxy, thereby influencing the distribution and intensity of cosmic radiation that ultimately reaches us on Earth. Moreover, cosmic magnetic fields can also impact the energy of high-energy particles. As cosmic rays traverse regions of varying magnetic field strength, they can experience processes like magnetic reconnection or shocks from supernova remnants and other energetic astrophysical events. These interactions can either accelerate particles to even higher energies or, conversely, slow them down, leading to a broad spectrum of cosmic ray energies observed. Importantly, the deflection caused by magnetic fields makes it challenging to trace cosmic rays back to their origins, since they seldom travel in direct lines. This complicates efforts to pinpoint the sources of these high-energy particles, whether they originate from supernovae, active galactic nuclei, or other cosmic accelerators. Understanding the influence of cosmic magnetic fields is essential for unlocking the secrets of these powerful and enigmatic particles. To study these interactions, researchers employ a combination of observational data from tools like radio telescopes and direct detection instruments placed on satellites and space probes. These instruments help map out magnetic field structures and measure cosmic ray properties, offering valuable insights into both cosmic magnetic phenomena and the high-energy particles themselves. Ultimately, cosmic magnetic fields not only shape the trajectories and energies of cosmic rays, but also reveal a significant aspect of the universe's dynamic behavior, underlining the intricate interplay between matter, energy, and magnetic forces on a cosmic scale. The magnetized filaments observed near the galactic center are intriguing structures resembling massive elongated strands of magnetic fields infused with cosmic plasma. These filaments stretch tens of light-years across space, and their origins continue to captivate astronomers and astrophysicists, who propose several fascinating theories to explain their formation. One leading hypothesis suggests that these filaments result from the activity of the supermassive black hole at the center of our galaxy, known as Sagittarius A star. Although this black hole lies dormant most of the time, it occasionally flares up, releasing enormous amounts of energy in the form of jets and outflows. These energetic events could twist and shape the magnetic field lines in the surrounding region, stretching them into the filamentary structures we observe. The dynamic interplay between the black hole's activity and the magnetic fields can lead to the creation of these extended filaments. Another possibility is that these filaments arise from the interactions of cosmic rays and magnetic fields in the galactic center. The region is bustling with high-energy particles accelerated by various astrophysical processes, such as supernova explosions and stellar winds. When these cosmic rays travel through the galactic center's turbulent magnetic environment, they can induce currents and amplify magnetic fields, creating the elongated filaments. The interactions between cosmic rays and magnetic fields might therefore play a critical role in shaping these fascinating structures. Additionally, the formation of magnetized filaments could be linked to the process of magnetic reconnection, where opposing magnetic field lines break and reconnect, releasing energy. This phenomenon occurs frequently in the Sun's atmosphere and other astrophysical environments. In the chaotic and highly magnetized environment of the galactic center, magnetic reconnection events might efficiently stretch and align magnetic field lines, giving rise to the observed filamentary structures. Observations and detailed studies of these filaments are crucial for understanding their origins and properties. Instruments such as radio telescopes are immensely valuable for mapping the magnetic fields and detecting synchrotron radiation, which is emitted by high-energy electrons spiraling around magnetic field lines. These observations offer insights into the magnetic field's strength, orientation, and the high-energy processes occurring near the galactic center. Through continued observation and research, the study of magnetized filaments near the galactic center not only illuminates a specific cosmic phenomenon, but also enhances our broader understanding of magnetic fields, black hole activity, and high-energy astrophysical processes in the extreme conditions found in the heart of our galaxy. Magnetic fields play a crucial role in both the formation and evolution of stars, influencing processes that range from the initial collapse of gas clouds to the later stages of a star's life. Understanding these effects provides a richer picture of the stellar life cycle and the intricate forces at play within galaxies. During star formation, magnetic fields influence the collapse of molecular clouds, which are dense regions of gas and dust where stars are born. These clouds are often threaded with magnetic field lines, which can either inhibit or promote the collapse process. Magnetic fields can provide support against gravitational collapse by adding magnetic pressure and tension, thereby slowing down the rate at which a cloud contracts. This regulation allows for a more controlled and gradual star formation process, preventing the rapid collapse that would otherwise lead to excessive fragmentation of the cloud. As a protostar forms and evolves, magnetic fields continue to shape its development. Within the developing star, magnetic fields play a critical role in angular momentum transfer. As the protostar contracts, it spins faster, and without mechanisms to shed angular momentum, it could spin too quickly for stability. Magnetic fields help to channel angular momentum away from the star by interacting with the surrounding disk of material known as the accretion disk. This process allows the protostar to accrete material from the disk more effectively and maintain stability without spinning apart. Furthermore, magnetic fields are responsible for the phenomenon of stellar winds and magnetic braking. Young stars often exhibit strong magnetic activity, creating powerful stellar winds that expel material from the star's outer layers. Magnetic braking occurs as these winds interact with the star's magnetic field, carrying away angular momentum and gradually slowing the star's rotation. This mechanism is essential for understanding why many stars, including our Sun, rotate at relatively modest speeds despite their initial rapid rotation during formation. In the later stages of a star's life, magnetic fields can also impact stellar evolution. For massive stars, magnetic fields can influence the behavior of the stellar core and the distribution of elements within the star, affecting processes like nuclear fusion and the eventual supernova explosion. In smaller stars, magnetic activity can lead to phenomena such as star spots, flares, and the generation of X-rays, all of which impact the star's magnetic environment and the surrounding interstellar medium. Studying magnetic fields in the context of stellar formation and evolution involves a variety of observational techniques, including radio, optical, and X-ray astronomy. These methods help scientists map magnetic field lines, measure magnetic strengths, and observe the interactions between magnetic fields and stellar material. Magnetic fields are a fundamental and dynamic force in the universe, deeply intertwined with the birth, life, and death of stars. Their influence extends from regulating star formation in molecular clouds to shaping the final evolutionary stages of stars, highlighting the interconnected nature of cosmic forces and stellar processes. Magnetic anomalies on exoplanets can be an intriguing and perplexing puzzle. These unusual magnetic fields are typically caused by the internal dynamics and composition of the planets themselves. To understand this, we need to explore what happens inside these distant worlds. At the heart of many planets, both within our solar system and beyond, lies a molten core. When this core is composed of conductive materials like iron or nickel, and is in a state of constant motion, it can generate a magnetic field through a process known as the dynamo effect. The movement of the molten metals produces electric currents, creating a magnetic field that can fluctuate and exhibit anomalies based on the specific conditions inside the planet. Additionally, planetary magnetic fields can be influenced by their interactions with their parent stars. Exoplanets that orbit particularly close to their stars may experience intense stellar radiation and magnetic activity, which can induce fluctuations or irregularities in their magnetic fields. Essentially, the stellar environment adds another layer of complexity to the behavior of a planet's magnetic field, sometimes leading to these mysterious anomalies. It is also worth considering that some exoplanets could harbor vast oceans of liquid water beneath icy surfaces or deep atmospheres. If these oceans contain saline, they might contribute to unusual magnetic signatures when subjected to tidal forces or other geophysical activities. The ongoing study of magnetic anomalies on exoplanets not only helps us understand these distant worlds better, but also provides valuable insights into the nature of magnetic fields themselves. Intergalactic magnetic fields play a subtle yet significant role in shaping the large-scale structure of the universe. These magnetic fields, which permeate the vast stretches of space between galaxies, affect the movement of charged particles and can influence the formation and evolution of cosmic structures. Firstly, these magnetic fields can guide the motion of cosmic rays, which are highly energetic particles zooming through space. When cosmic rays travel through magnetic fields, they spiral around the magnetic field lines. This motion helps distribute energy and matter differently than if the fields weren't present, potentially affecting the growth of galactic clusters and larger structures. Moreover, magnetic fields impact the behavior of intergalactic gas. which is crucial for star formation. As gas moves through these fields, it experiences resistance, which can affect how the gas clumps together to form stars and galaxies. This process can either slow down star formation or concentrate gas in certain regions, thus altering the development of galaxies over billions of years. Lastly, intergalactic magnetic fields can influence cosmic-scale phenomena like jets from supermassive black holes. These jets, consisting of ionized matter, are collimated and guided by magnetic fields. As they propagate through intergalactic space, the fields shape the jets' paths and spread their energy across vast distances, making them critical in distributing matter and energy within the cosmic web. While invisible to the eye, intergalactic magnetic fields act as a tapestry, subtly guiding the formation and behavior of some of the most significant structures in the universe. They weave through the cosmos, ensuring that the universe's architecture is not just a result of gravity, but also of these enigmatic magnetic forces. Magnetic reconnection events in cosmic plasmas are profoundly significant, playing a critical role in various astrophysical phenomena. These dynamic processes occur when magnetic field lines that are oppositely directed suddenly snap and realign, releasing a substantial amount of energy. One of the most remarkable aspects of magnetic reconnection is its role in solar flares and coronal mass ejections on our Sun. During these events, the magnetic field lines in the Sun's corona rapidly reorganize, leading to explosive releases of energy. This energy can accelerate particles to near light speeds, creating powerful bursts of radiation and triggering spectacular light, shows like the northern and southern lights, when the particles interact with Earth's magnetic field. Magnetic reconnection is also crucial in magnetospheric dynamics. For instance, Earth's magnetosphere, the region dominated by Earth's magnetic field, often interacts with the solar wind, a stream of charged particles emanating from the Sun. During geomagnetic storms, magnetic reconnection events can occur at the boundary, transferring solar wind energy into the magnetosphere. This process can cause significant disturbances, affecting satellite communications, power grids, and even creating beautiful auroras. In a broader cosmic context, magnetic reconnection can impact the behavior of plasma in various environments, such as accretion disks around black holes, the interstellar medium, and even in the formation of stars. These events can influence the thermal and kinetic energy distribution in these plasmas, thereby affecting how they evolve over time. The study of magnetic reconnection helps astrophysicists understand energy transfer processes across the universe. Whether it's lighting up the night sky with auroras or driving the energetic events that occur around supermassive black holes, magnetic reconnection is a key mechanism that helps to shape the energetic and dynamic behavior of cosmic plasmas. Magnetic fields have a profound influence on the behavior of interstellar dust and gas, fundamentally shaping the structure and evolution of the interstellar medium. These fields dictate how matter moves and interacts within galaxies, leading to some fascinating outcomes. One crucial way magnetic fields affect interstellar dust and gas is through the process of star formation. In the dense regions where stars are born, magnetic fields can provide support against gravitational collapse. When gas clouds attempt to condense under gravity to form new stars, magnetic fields can partially counteract this force, slowing down the collapse and regulating the rate at which stars form. This balance ensures that star formation is a more controlled, gradual process rather than an explosive one. The alignment and polarization of interstellar dust grains are another influence of magnetic fields. Dust grains in space are often elongated and can align themselves with the local magnetic field lines. This alignment causes the light passing through these dust clouds to become polarized, a phenomenon that astronomers can measure to map out the structure and strength of the magnetic fields. These aligned dust grains can also influence radiation transfer, affecting the light we observe from distant stars and galaxies. Magnetic fields also guide the movement of ionized gas within the interstellar medium. Charged particles, such as protons and electrons in this gas, follow the magnetic field lines, creating intricate and often turbulent patterns. These motions can lead to the formation of complex filamentary structures observed within nebulae and other gas clouds. Furthermore, the presence of strong magnetic fields can suppress certain instabilities in the gas, providing stability to these vast cosmic structures. Overall, magnetic fields are invisible architects in the cosmos, orchestrating the behavior of interstellar dust and gas in ways that underlie many of the beautiful and complex phenomena we observe. Whether it's controlling star formation, polarizing light, or shaping the patterns of gas clouds, these fields play an indispensable role in the evolution of the universe. Primordial magnetic fields are thought to be ancient magnetic fields that originated in the early universe, just a heartbeat after the Big Bang. These fields, if they exist, would have been created during the very first moments of cosmic time, influencing the formation and evolution of the large-scale structures we see today. One possible origin for these primordial magnetic fields is during the inflationary epoch, a period of rapid expansion just fractions of a second after the Big Bang. During this phase, quantum fluctuations could have stretched to macroscopic scales, freezing in magnetic fields that permeated the early universe. These fields, although weak by today's standards, could have provided the seeds around which larger magnetic structures later grew. Another scenario involves the phase transitions in the early universe, such as the electroweak or the quantum chromodynamics phase transition, where the fundamental forces and particles we know today emerged. During these violent transitions, various mechanisms, including turbulence and currents, could have generated magnetic fields that spread throughout the universe. These fields would then evolve over time, influencing the formation of galaxies and galaxy clusters by guiding the motion of charged particles and intergalactic gas. Primordial magnetic fields are believed to be incredibly weak compared to those generated by stars or galaxies through later cosmic processes. However, even such faint fields could have had significant long-term effects. For instance, they might have contributed to the magnetization of cosmic structures by compressing and amplifying as matter clumped together under gravity to form the first stars and galaxies. Alternatively, these fields could provide a subtle baseline influence, affecting the dynamics of cosmic plasma over billions of years. Detecting these primordial magnetic fields remains a challenging frontier in astrophysics. Scientists use various observational techniques such as studying the polarization of light from the cosmic microwave background or the Faraday rotation of light from distant galaxies to uncover the faint fingerprints of these ancient fields. Whether we can detect them or not, the concept of primordial magnetic fields gives us a window into understanding the earliest moments of our universe and the forces that have shaped its evolution. Magnetic fields are pivotal in shaping the jets that emanate from active galactic nuclei. These jets, which can stretch for thousands or even millions of light years, are streams of charged particles traveling at nearly the speed of light, originating from the supermassive black holes at the centers of active galaxies. The generation of these jets begins in the vicinity of the black hole. As matter falls into the black hole, it forms an accretion disk, an extremely hot and dense region where material spirals inward. The intense magnetic fields in the accretion disk play a crucial role in the launch of the jets. These fields twist and wind up due to the differential rotation of the accretion disk, effectively channeling and accelerating particles away from the disk's plane along the poles. This process, known as the Blandford-Znajek mechanism, relies heavily on the presence of strong magnetic fields to extract the rotational energy of the black hole and convert it into the kinetic energy of the jets. Once the jets are launched, magnetic fields continue to influence their structure and stability. The fields provide a form of scaffolding that maintains the collimation of the jets, preventing them from dispersing too quickly. This is crucial for the jets to remain narrow and focused, allowing them to travel vast distances while remaining intact. Magnetic fields also help stabilize the jets against various instabilities that could otherwise cause them to fragment or lose coherence. Furthermore, magnetic fields within the jets can accelerate particles to relativistic speeds through a process called magnetic reconnection, where oppositely directed magnetic field lines break and reconnect, releasing energy. This acceleration process leads to the emission of high-energy radiation, including radio waves, X-rays, and gamma rays. These emissions make the jets observable across the electromagnetic spectrum, allowing astronomers to study their properties and behavior. Magnetic fields are indispensable from the birth of the jets near the black hole to their long-distance travel through intergalactic space. They not only assist in the formation and acceleration of the jets, but also ensure their stability and coherence over immense distances, illuminating the cosmos in astonishing and powerful ways. The hypothesized cosmic phase transitions in the early universe were driven by changes in temperature and density as the universe expanded and cooled. These transitions were crucial in shaping the fundamental properties of matter and the forces that govern it, occurring during different epochs as the universe evolved. One of the key phase transitions is believed to have taken place shortly after the Big Bang, during the so-called Grand Unified Theory epoch. At incredibly high temperatures and energies, the strong nuclear force, the weak nuclear force, and the electromagnetic force may have been unified into a single force. As the universe expanded and cooled, it is theorized that this unified force split through a phase transition into the distinct forces we observe today. This transition released a tremendous amount of energy and could have led to the generation of magnetic fields, along with other cosmic phenomena. Another critical phase transition occurred during the electroweak epoch, when the universe was roughly 1/10,000th of a second old. During this time, the unified electroweak force separated into the electromagnetic force and the weak nuclear force. This phase transition involved the Higgs field gaining a non-zero value, endowing elementary particles with mass. The energy released during this transition may have created fluctuations and turbulence in the primordial plasma, further contributing to the formation of magnetic fields and the structure of the universe. A subsequent and equally significant phase transition is thought to have occurred during the quantum chromodynamics epoch, around 1 microsecond after the Big Bang. At this juncture, the universe cooled to a point where quarks and gluons condensed to form protons and neutrons, the building blocks of atomic nuclei. This process, often compared to water freezing into ice, resulted in a change in the state of matter. This transition also impacted the dynamics of the early universe, influencing its thermal history and potentially seeding further cosmic structures. Each of these phase transitions represents a profound change in the fabric of the universe, profoundly altering its energy landscape and the behavior of fundamental particles. By studying these early cosmic phase transitions, scientists hope to uncover the forces and mechanisms that gave rise to the universe's intricate and diverse structure. These transitions are not merely historical footnotes, they are essential to understanding the universe's past, its present structure, and its long-term future. The apparent fine-tuning of universal constants refers to the observation that the fundamental constants and parameters of the universe, such as the speed of light, the gravitational constant, and the strength of the electromagnetic force, are precisely set in such a way that they allow for the existence of complex structures, including stars, planets, and life itself. Even tiny deviations in these constants could render the universe hostile to the formation of such structures. One explanation for this fine-tuning is the anthropic principle, which essentially states that we observe the universe to be as it is, because if it were any different, we wouldn't be here to observe it. In other words, only a universe with the right conditions for life to develop would have observers who could ponder its characteristics. This principle frames our understanding in a context that makes our existence a necessary prerequisite for asking why the universe appears fine-tuned. Another compelling explanation comes from the concept of the multiverse. According to this hypothesis, our universe is just one of an enormous number of universes, each with its own set of physical constants and laws. In such a diverse multiverse, it is not surprising that at least one universe would have the right combination of parameters to support life. Our universe, then, might just be one of the rare few where the constants happen to fall within the narrow range required for complexity and life to emerge. A third perspective is rooted in the idea that there may be deeper, more fundamental laws that necessitate the constants as they are. Physicists are still striving for a theory of everything, a comprehensive framework that unites the fundamental forces and explains why the constants take their observed values. If such a theory exists, it could reveal that the seeming fine-tuning of these constants is not a coincidence, but a natural outcome of deeper physical principles. Lastly, some researchers propose that what we perceive as fine-tuning could be a result of our limited understanding. Future discoveries in quantum mechanics, cosmology, and particle physics may provide insights that show the constants and initial conditions of the universe are indeed interdependent and result from inevitable processes in the early universe's development. While these theories vary in their approaches, they all attempt to address one of the most fascinating and profound questions in cosmology. Whether through anthropic reasoning, the vastness of the multiverse, deeper physical principles, or yet-to-be-discovered scientific truths, the question of fine-tuning continues to stimulate thought and research, beckoning us toward a deeper understanding of the cosmos. Cosmic inflation is a theory that proposes a period of extremely rapid expansion of the universe immediately following the Big Bang, occurring within a fraction of a second. This rapid growth stretched space-time itself, causing the universe to balloon exponentially and smooth out any irregularities, setting the stage for the universe we observe today. The nature of cosmic inflation stems from the concept of a high-energy scalar field, often referred to as the inflaton field. This hypothetical field permeated the early universe, and its associated potential energy drove the accelerated expansion. The inflaton field is characterized by a potential energy curve that determines how the field evolves over time. During inflation, the inflaton field was in a high-energy state, which caused space to expand at an exponential rate. As to what initiated cosmic inflation, it likely began when the inflaton field found itself in a state of high potential energy. Quantum fluctuations in the early universe could have caused regions of this field to be displaced from equilibrium, leading to a state where the field had excessive energy. This excess energy acted as a repulsive force, overcoming the gravitational pull and causing the universe to expand rapidly. The termination of cosmic inflation, or reheating, occurred when the inflaton field rolled down its potential energy curve to a lower energy state. As the field settled into this stable, low-energy state, the stored potential energy was released and converted into particles and radiation. This energy transfer reheated the universe, filling it with the hot plasma that would later cool and coalesce to form the cosmic structures we observe today. Cosmic inflation provides elegant solutions to several problems in cosmological theory. It explains the uniformity and flatness of the observable universe and accounts for the slight density fluctuations that led to the formation of galaxies and other cosmic structures. These fluctuations, seeded by quantum effects during inflation, were stretched to macroscopic scales, laying the groundwork for the cosmic microwave background radiation and the large-scale structure of the universe. While compelling, the theory of cosmic inflation remains an area of active research and debate. Physicists continue to seek direct evidence through observations, such as the characteristics of the cosmic microwave background or the search for primordial gravitational waves, which could provide further confirmation and detail about this transformative phase in the universe's early history. In a Big Bounce scenario, the universe's history unfolds differently than the conventional Big Bang model. Instead of beginning from a singularity, a point of infinite density and temperature, the universe experiences a cycle of contraction and expansion. Essentially, instead of a single explosive beginning, the universe might oscillate through phases of collapse and rebirth. In this model, before our current expanding phase, the universe would have been contracting, with galaxies and cosmic structures gradually moving closer together. As the universe contracts, the density and temperature increase, but instead of collapsing into a singularity, the contraction reaches a critical point. At this juncture, quantum gravitational effects or other speculative physical phenomena come into play, preventing a singularity and instead triggering a bounce. This bounce marks the transition from contraction to expansion. The physics underlying the bounce might involve new theories of gravity, such as loop quantum gravity or modifications to general relativity, which allow for a finite smallest scale to space and time. These theories often incorporate principles that can avoid the singularity, providing a framework where the universe's density reaches a maximum but never becomes infinite. The stored energy during the contraction is converted into the expansive energy that propels the universe into its next cycle of growth. Post-bounce, the universe enters an expansion phase similar to what we observe today. The remnants of the previous cycle, such as thermal distributions and quantum fluctuations, influence the early moments, similarly to how inflation smooths and seeds the universe in the Big Bang model. Over time, galaxies, stars, and other cosmic structures form, and the universe evolves in ways not unlike our current understanding, but all within a cyclical framework. One intriguing aspect of the Big Bounce scenario is its philosophical implications. This model suggests an eternal, cyclical cosmology where the universe has no ultimate beginning or end, with each cycle providing opportunities for different physical properties and evolutionary paths of matter and energy. Observational evidence to support a big bounce might come from examining patterns in the cosmic microwave background, or searching for imprints left by previous cycles, such as unusual gravitational wave signatures. While the big bounce remains speculative and requires further theoretical and observational validation, it presents a fascinating alternative to the traditional Big Bang theory. It enriches our understanding of the cosmos, offering potential insights into the ultimate nature and destiny of the universe. Baryon acoustic oscillations, or BAOs, are significant because they provide a standard ruler for measuring the universe's expansion and understanding its large-scale structure. These oscillations are essentially sound waves that propagated through the hot, dense plasma of the early universe before permanently imprinting their pattern on the cosmic microwave background and later influencing the distribution of galaxies. In the early universe, roughly 400,000 years after the Big Bang, conditions were such that photons and baryons particles like protons and neutrons were tightly coupled due to frequent interactions. Acoustic waves generated by gravitational forces traveled through this plasma, creating regular periodic density fluctuations. These sound waves set up regions of compression and rarefaction in the primordial plasma. When the universe cooled enough for photons to decouple from baryons, known as recombination, the sound waves effectively froze in place, leaving an imprint of these oscillations in the form of slight overdensities of matter. These imprints can be seen in the CMB as subtle temperature variations. As the universe continued to expand and structure formed, these overdensities seeded the large-scale distribution of galaxies we observe today. The significance of BAOs lies in their ability to help cosmologists measure the cosmic expansion history. The characteristic scale of these oscillations is well known from CMB observations and can be used as a cosmic yardstick. By comparing the observed scale of BAOs in the distribution of galaxies at different distances, and hence different times in the universe's history, scientists can infer the expansion rate of the universe. This knowledge is critical for understanding dark energy, the mysterious force driving the universe's accelerated expansion. Furthermore, BAOs provide a method to cross-check and improve the accuracy of other cosmological measurements. By offering an independent measure of distance, they help refine models of the universe's geometry and the parameters governing its evolution. This makes BAOs a powerful tool in the quest to understand the fundamental properties of the cosmos, including the matter-energy content and the nature of dark energy. Baryon acoustic oscillations are a fundamental aspect of our universe's early acoustic history. They serve as a cosmic signature, allowing scientists to trace the universe's expansion with remarkable precision and providing critical insights into the forces and factors that shape our cosmic environment. The cyclic nature of star formation in galaxies is driven by a repeating sequence of events involving the interstellar medium, the birth and death of stars, and the dynamic processes within galaxies themselves. This cycle perpetuates the continuous regeneration of new stars and shapes the evolution of galaxies over billions of years. Star formation begins in regions of cold, dense molecular clouds composed primarily of hydrogen gas. When these clouds become gravitationally unstable, often triggered by external perturbations such as shock waves from supernova explosions or gravitational interactions with other galaxies, they collapse under their own gravity. As the clouds collapse, they fragment into smaller clumps, which can further condense to form protostars. As these protostars evolve and eventually ignite nuclear fusion in their cores, they become main sequence stars. During their lifetimes, varying from millions to billions of years depending on their mass, stars play a crucial role in the galactic ecosystem. Massive stars in particular have relatively short but intensely energetic lives, ending dramatically in supernova explosions. These explosions not only distribute heavy elements and other byproducts of nuclear fusion into the surrounding interstellar medium, but also generate powerful shock waves. The material ejected by supernovae, along with radiation pressure and stellar winds from massive stars, injects energy into the surrounding gas, compressing nearby molecular clouds and triggering new rounds of star formation. This feedback mechanism ensures that the cycle of star formation continues, with one generation of stars providing the necessary conditions for the next. Galactic dynamics also contribute to the cyclical nature of star formation. Movements such as spiral arm rotation in spiral galaxies can compress interstellar gas as it flows into these arms, enhancing star formation rates in these regions. Interactions with other galaxies, such as mergers or close passes, can also disturb the gas within galaxies, leading to bursts of star formation as compressed gas clouds collapse. Altogether, the cyclic nature of star formation is a complex interplay of gravitational collapse, stellar evolution, feedback mechanisms, and galactic dynamics, creating a continuous and self-sustaining process. This cycle not only fuels the growth and development of galaxies, but also plays a crucial role in enriching the interstellar medium with the elements necessary for the formation of planets and potentially life itself. Reionization is a pivotal phase in the history of the early universe, marking the period when the first stars and galaxies began to form and light up, ultimately transforming the dark, opaque cosmos into the transparent, luminous universe we observe today. This process occurred roughly 1 billion years after the Big Bang, following the cosmic dark ages. The universe began with the Big Bang, which produced a hot, dense plasma of particles. As the universe expanded and cooled, protons, neutrons, and electrons combined to form neutral hydrogen atoms, leading to a period called recombination. This event resulted in the decoupling of photons from matter, allowing light to travel freely and creating the cosmic microwave background radiation. However, the universe then entered the Dark Ages, a time when light-emitting objects had not yet formed, and clouds of neutral hydrogen pervaded space. Reionization began as the first stars, galaxies, and quasars formed from the gravitational collapse of these primordial gas clouds. The intense ultraviolet and X-ray radiation emitted by these early luminous objects had enough energy to ionize the surrounding hydrogen, breaking it down into protons and electrons once more. As more stars and galaxies formed, their radiation gradually permeated the intergalactic medium, reionizing it and making it transparent to light. The reionization process did not occur uniformly throughout the universe, but rather in patches. Initially, ionized bubbles formed around the first light-emitting sources. Over time, these bubbles grew and merged, eventually enveloping the entire universe. The combined radiation from numerous stars and galaxies ensured that the neutral hydrogen was ionized and remained in that state, allowing light to travel freely and enabling the formation of large-scale cosmic structures. Reionization signifies not just a critical transformation in the universe's transparency, but also an epoch that laid the foundation for the cosmic web of galaxies and clusters we see today. By studying the signatures of reionization, such as the absorption features in the spectra of distant quasars and the polarization of the cosmic microwave background, astronomers gain insights into the nature and timing of this crucial period. Understanding reionization helps us piece together the universe's evolution from a dark, unlit cosmos to the complex, structured, and light-filled universe of the present day. The evolution of dark energy is one of the most profound and mysterious questions in cosmology, as it dictates the ultimate fate of the universe. Dark energy is the term given to the unknown force driving the accelerated expansion of the universe, and how it evolves over time could lead to dramatically different cosmic futures. One scenario is that dark energy remains constant over time. The simplest model for such a cosmological constant is known as the lambda cold dark matter model, or lambda CDM. In this model, dark energy is represented by a constant, unchanging energy density filling space uniformly. If this is the case, the universe will continue to expand at an accelerating rate indefinitely. Galaxies will recede from one another faster and faster, eventually becoming so distant that they will be isolated in a dark, cold universe, leading to a scenario termed the Big Freeze. Another possibility is that dark energy could vary with time. In models involving dynamic dark energy, often represented by a field called quintessence, the energy density of dark energy changes as the universe evolves. If the strength of dark energy increases over time, the accelerating expansion of the universe could speed up even more, leading to a big rip. In this catastrophic scenario, the force driving cosmic acceleration eventually becomes powerful enough to tear apart galaxies, stars, planets, and even atomic structures. Conversely, if dark energy decays or diminishes over time, the universe's expansion might slow down or even reverse. This leads to a potential big crunch, where the universe stops expanding and begins to contract. Over billions of years, all matter and energy in the universe could collapse back into a highly dense and hot state, possibly leading to a new Big Bang and a cyclical model of cosmic evolution. There is also the intriguing hypothesis known as phantom energy, where dark energy's equation of state results in it growing stronger with time, leading to increasingly violent expansions. Under this model, the Big Rip scenario is an inevitable endgame, with everything in the cosmos ultimately being torn apart as the universe grows exponentially. To understand which of these outcomes is most likely, scientists use observational data from supernovae, cosmic microwave background radiation, and large-scale structure surveys to study the behavior of dark energy. Future missions and telescopes aim to further refine our understanding of this enigmatic force. The evolution of dark energy will determine whether the cosmos ends in perpetual expansion, collapse, or even violent tearing, making it one of the most fascinating topics in the study of the universe's ultimate destiny. The apparent periodicity in mass extinction events on Earth has intrigued scientists for decades, suggesting that these catastrophic events might be driven by regular, possibly cyclical, cosmic or terrestrial forces. Understanding these drivers helps us piece together not only the history of life on our planet, but also the complex interplay between Earth's biosphere and its broader cosmic environment. One hypothesis is linked to the Earth's movement through the Milky Way galaxy. Our solar system orbits the center of the Milky Way in a roughly 200 million-year cycle. As it travels, It occasionally moves through dense regions of the galactic disk filled with interstellar dust and gas. This movement might lead to gravitational disturbances that can redirect comets from the Oort cloud, a distant region of icy bodies surrounding our solar system, sending them towards Earth. Increased comet and asteroid impacts could then trigger mass extinction events by causing dramatic climate changes and widespread environmental disruptions. Another cosmic factor involves the possible influence of nearby supernovae. Exploding stars in our galactic vicinity can emit intense radiation and energetic particles, which might strip away portions of Earth's atmosphere or induce significant environmental changes. These supernovae events could periodically expose Earth to hostile conditions, contributing to mass extinctions. Nonetheless, direct evidence linking supernova to specific extinction events remains scarce, but it's a compelling area of ongoing research. Terrestrially, Earth's own geological processes might contribute to periodic extinctions. The dynamics of plate tectonics, particularly volcanic activity from large igneous provinces, can cause massive releases of volcanic gases like sulfur dioxide and carbon dioxide. These gases can lead to rapid climate changes, ocean acidification, and the disruption of ecological systems. Periodic resurfacing due to mantle plumes or other deep Earth processes might drive these extensive volcanic events. Moreover, some researchers suggest that the periodicity could be influenced by complex interactions of multiple factors rather than a single dominant cause. The interplay between cosmic impacts, volcanic activity, climate oscillations, and biological factors might together set the rhythm for mass extinctions. While the evidence for a strict periodicity remains debated, understanding these potential drivers emphasizes the interconnectedness of Earth's biological systems with its geological and cosmic context. The ongoing study of mass extinction periodicity combines data from paleontology, geology, and astronomy, offering a multidisciplinary approach to unraveling Earth's deep-time mysteries. Each piece of this puzzle helps us comprehend not only the past cycles of life and death on our planet, but also the potential future threats and the resilience of life on Earth. Galactic magnetic field reversals significantly influence the propagation of cosmic rays. High-energy particles originating from sources like supernovae, active galactic nuclei, and other astrophysical events. These magnetic field reversals can alter the journey of cosmic rays as they travel through the galaxy, impacting their trajectories, energies, and eventual arrival at Earth. Within the Milky Way, the galactic magnetic field is not uniform, but exhibits complex structures, including regions where the direction of the field reverses. These reversals result from the dynamic processes within the galactic disk, such as the movement of plasma and the rotation of the galaxy. When cosmic rays encounter these reversed magnetic fields, their paths get deflected, causing them to follow spiral or corkscrew-like trajectories rather than traveling in straight lines. This bending and twisting of cosmic ray paths due to magnetic field reversals create what's known as cosmic ray diffusion. The particles scatter as they move through regions of alternating magnetic fields, which can significantly slow down their progress. As a result, cosmic rays take longer to traverse the galaxy and experience a form of random walk, making it difficult to trace them back to their original sources. Moreover, the energy spectrum of cosmic rays is also affected by these magnetic field reversals. High-energy cosmic rays with more momentum can better penetrate magnetic field reversals and maintain more straightforward paths, while lower-energy cosmic rays are more susceptible to being deflected. This results in energy-dependent propagation, where higher-energy cosmic rays travel more directly and potentially reach Earth more quickly than their lower-energy counterparts. Additionally, magnetic field reversals can lead to the trapping and confinement of cosmic rays within certain regions of the galaxy. These confined cosmic rays can undergo further interactions, such as collisions with interstellar gas, leading to secondary particle production and gamma-ray emissions. These interactions contribute to the complexity of the cosmic ray spectrum observed here on Earth. Galactic magnetic field reversals play a crucial role in shaping the propagation and characteristics of cosmic rays. They cause significant deviations in the paths of these high-energy particles, influencing their diffusion, energy distribution, and eventual detectability. Understanding these magnetic fields helps scientists decode the intricate journey of cosmic rays, shedding light on the high-energy processes occurring both within and beyond our galaxy. Life in the methane seas of Titan-like worlds would likely be quite different from anything we know on Earth, given the radically different environmental conditions. Titan, one of Saturn's moons, offers an intriguing model for such exotic life, with its lakes and seas of liquid methane and ethane. These conditions pose unique challenges and opportunities for life, prompting scientists to think creatively about the biochemistry that could support life in such an environment. In the methane-rich, extremely cold environment of Titan, where temperatures plunge below 290 degrees Fahrenheit, life would have to rely on a chemistry radically different from water-based life on Earth. One hypothesis is that such life forms might use liquid methane as a solvent instead of water. This would require a fundamentally different sort of biochemistry because the chemical interactions in liquid methane are unlike those in water. For example, with methane being a non-polar solvent, the kind of molecules that could dissolve and interact within it would differ greatly from those in water. Membrane structures, crucial for cells, would also have to be adapted. On Earth, cell membranes rely on phospholipid bilayers that function well in water. In methane, life forms might utilize membranes made of entirely different compounds, such as small nitrogen-containing molecules called azotosomes. These hypothetical structures would be stable and flexible in methane, allowing for cellular integrity and the compartmentalization of biochemical processes. Another key consideration is metabolism. Earth's life forms gain energy through redox reactions involving oxygen and organic molecules. On a Titan-like world, such energy harvesting processes might revolve around reactions involving hydrogen, acetylene, and ethane. For instance, methanogenic life on Titan might combine hydrogen with acetylene to produce energy and methane, a process that could sustain a stable biosphere. This would be a mirror of some anaerobic processes known on Earth, but adapted to Titan's specific chemical environment. Exploring the potential biochemistry and ecology of methane-based life extends our understanding of life's adaptability. Instruments aboard missions like the proposed Dragonfly drone, which aims to explore Titan's surface, could provide crucial data. Studying these environments could reveal whether such exotic forms of life exist and how they thrive, shedding light on the broader possibilities for life in the universe. The existence of life on Titan-like worlds would expand our understanding of habitability far beyond the traditional criteria, showing that life can adapt to conditions vastly different from those on Earth. The possibilities for life in the subsurface oceans of icy moons such as Europa, Enceladus, and Titan are particularly exciting because these environments combine several key ingredients thought to be essential for life: liquid water, energy sources, and the necessary chemical building blocks. Subsurface oceans are kept in a liquid state beneath thick ice crusts due to the gravitational interactions these moons experience with their parent planets. For instance, Europa, one of Jupiter's moons, and Enceladus, orbiting Saturn, undergo tidal flexing. This constant kneading generates internal heat, preventing the subsurface oceans from freezing solid. This geological activity also suggests that these moons could have hydrothermal vents on their ocean floors, similar to those found in Earth's oceans. Hydrothermal vents on Earth are teeming with life, despite their extreme conditions, relying on chemosynthesis instead of photosynthesis. In these deep-sea environments, microorganisms use chemical reactions involving compounds like hydrogen sulfide and methane to produce energy. If similar vents exist in the subsurface oceans of icy moons, they could provide a stable energy source and a rich chemical environment suitable for life. The key is that these environments offer a setting where organic molecules could undergo complex chemistry, potentially leading to microbial life. The thick ice crusts of these moons also act as protective shields, barricading the oceans from harmful cosmic radiation and meteoric impacts. Within this safe cocoon, life would have a stable habitat, allowing for potentially lengthy evolutionary processes. The recent discovery of water plumes erupting from Enceladus and suspected plumes on Europa offers a tantalizing glimpse into the subsurface oceans, hinting at dynamic processes beneath the ice and providing a method for sampling these hidden oceans without needing to drill through kilometers of ice. On Titan, the largest moon of Saturn, there's the additional possibility of life in liquid water-ammonia mixtures beneath the icy crust. Ammonia's presence lowers the freezing point of water, maintaining a subsurface ocean in a liquid state despite Titan's frigid temperatures. This environment would be chemically different from the predominantly water-based subsurface oceans of Europa or Enceladus, potentially supporting unique forms of life that could use ammonia as part of their biochemistry. The investigation of these subsurface oceans has become a focus for missions like the Europa Clipper, set to explore Europa's habitability, and plans for potential future missions to Enceladus. These missions aim to analyze the chemical composition of the plumes, the ice surface, and other geophysical characteristics, searching for biosignatures or direct evidence of life. Discovering life in the subsurface oceans of icy moons would have profound implications, demonstrating that life can arise and persist in environments vastly different from Earth's surface, and expanding our understanding of the diversity and resilience of life in the cosmos. Adapting to the extreme radiation environments around red dwarf stars presents unique challenges for any potential life forms, but it also opens avenues for remarkable adaptations and survival strategies. Red dwarf stars, the most common type of star in the galaxy, are known for their volatile nature, frequently emitting powerful solar flares and bursts of radiation. Despite this, planets within their habitable zones, where liquid water might exist, could still theoretically sustain life, but that life would need to be extraordinarily resilient. One adaptation strategy could involve life forms developing robust radiation shielding mechanisms. On Earth, various organisms, such as tardigrades and specific species of bacteria, exhibit an extraordinary tolerance to radiation through mechanisms like efficient DNA repair systems and protective proteins that stabilize cellular structures. Life around red dwarf stars might evolve similar or even more advanced biological repair mechanisms to cope with the increased radiation exposure. These organisms might also produce pigments or other compounds that act as biological sunscreens, mitigating the damaging effects of ultraviolet radiation. Alternatively, life might find refuge underground or beneath thick layers of ice or water, using natural barriers to shield themselves from harmful radiation. Subsurface habitats on planets orbiting red dwarf stars could, in this scenario, provide a stable and protected environment where life could thrive away from the intense surface radiation. Just as life on Earth finds niches in extreme environments, like hydrothermal vents deep in the ocean or subsurface colonies of microbes deep in the Earth's crust, similar niches could exist on planets around red dwarf stars. Furthermore, life might adapt by becoming nocturnal or seeking sites that offer periodic shelter from radiation. If a planet is tidally locked to its red dwarf star, meaning one side always faces the star and the other side remains in perpetual darkness, potential life forms could thrive in regions of perpetual twilight or on the night side where radiation levels would be considerably lower. They might also develop circadian rhythms synchronized with the quieter periods of the star's activity, remaining dormant or minimally active during peak radiation times. Lastly, red dwarf planets could have evolved thick atmospheres rich in gases like carbon dioxide or methane, providing an additional layer of protection against stellar radiation. These atmospheres could absorb or deflect harmful rays, allowing life to exist on the surface or in the atmospheric layers just below the shielding gases. Additionally, if the planet possesses strong magnetic fields, these could help deflect much of the cosmic and stellar radiation, providing further protection to any potential surface or near-surface biological entities. While the hostile radiation environment of red dwarf stars poses significant challenges, life could find inventive and multifaceted ways to adapt. These adaptations would likely encompass biological, ecological, and perhaps even atmospheric or geophysical strategies, revealing the extraordinary resilience of life in facing cosmic hazards. Understanding these potential adaptations aids in the search for extraterrestrial life by guiding our exploration and expectations of the varied forms life might take in different stellar environments. Silicon-based life forms, emerging in extreme cosmic environments, would differ significantly from the carbon-based life we know on Earth, drawing from the unique chemical properties of silicon. While silicon chemistry is not as versatile as carbon's, it still offers hypothetical possibilities for robust life forms in environments that might be too extreme for carbon-based organisms. In high-temperature environments such as the surfaces of extreme exoplanets or around geothermal vents, silicon-based life could thrive due to silicon's higher bond strength at elevated temperatures. These life forms might use silanes, which are analogous to alkanes in carbon chemistry, or silicon-oxygen compounds such as silicates as the backbone of their biochemistry. Silicate-based biopolymers could form the structural and functional molecules within these organisms, potentially creating resilient, heat-resistant structures akin to mineral-like shells or exoskeletons. Silicon-based organisms might also exploit environments where traditional carbon-based life forms cannot survive due to scarcity of liquid water. In regions rich in silica, such as planetary crusts or icy moons with high silicon content, silicon-based life could leverage the abundant silicon compounds to build complex molecules. While terrestrial life relies heavily on water as a solvent, these hypothetical organisms might operate in environments where alternatives like liquid ammonia or even liquid methane are present, using them to facilitate biochemical reactions. Silicon life forms would likely display stark differences in metabolic processes compared to our carbon-based systems. Given the energy dynamics around silicon chemistry, these life forms might rely on alternative energy sources, possibly drawing energy from inorganic reactions involving silanes and oxygen. Their metabolism could resemble chemosynthetic life on Earth, but would be uniquely adapted to harnessing energy from silicon compounds. Moreover, considering environments with extreme radiation, such as planets orbiting red dwarf stars or within high radiation zones of galaxy cores, silicon-based life might develop robust radiation-resistant mechanisms. The stronger silicon-oxygen bonds could provide enhanced stability under high radiation levels, reducing the likelihood of structural breakdown. These organisms might also employ additional protective strategies, such as radiation-absorbing outer layers or efficient repair systems akin to those observed in extremophiles on Earth. From a structural standpoint, silicon-based life could exhibit diverse forms, from crystalline structures that grow and reproduce by accretion of silicate materials to more fluid-based entities with silane or siloxane-based chemistry, allowing for greater flexibility and movement. They might communicate and sense their environment using mineral-based sensors or electrochemical gradients distinct from those in carbon-based life. While the concept of silicon-based life remains speculative and awaits empirical validation, envisioning such organisms expands our understanding of biological possibilities and the adaptability of life in the universe. It challenges scientists to contemplate how different chemistries might support life under conditions far removed from those on Earth, enhancing our quest to uncover the myriad ways life might manifest across the cosmos. Life surviving in the upper atmosphere of gas giants like Jupiter or Saturn would need to adapt to a unique set of challenges, including extreme pressures, temperatures, and radiation levels. Despite these harsh conditions, the existence of life in such environments, while speculative, is an exciting possibility driven by the discovery of complex chemistry and organic molecules in these celestial realms. Here's how life might adapt to and thrive in the thick, dynamic clouds of a gas giant. One major challenge is the highly turbulent and dynamic nature of gas giant atmospheres. Organisms would need to be incredibly resilient to rapid changes in environmental conditions. They might develop buoyant structures or gas-filled sacs to maintain their position within more stable atmospheric layers. These buoyant adaptations could allow them to float at altitudes where temperatures and pressures are more conducive to biological processes, similar to how certain microorganisms maintain buoyancy in Earth's oceans. Energy acquisition on gas giants would also be fundamentally different from solar energy-driven photosynthesis on Earth. These life forms might rely on chemosynthesis, harnessing energy from chemical reactions. The atmospheres of gas giants are rich in hydrogen, methane, ammonia, and other chemicals. Life might metabolize these compounds, similar to terrestrial extremophiles that derive energy from chemicals in deep-sea hydrothermal vents. For example, organisms could harness energy through the oxidation of hydrogen sulfide or ammonia, facilitating life in an environment devoid of sunlight. To cope with the intense radiation and fluctuating environmental conditions, life forms might develop sophisticated protective mechanisms. These could include thick outer shells or layers of complex molecules that absorb and dissipate radiation. Additionally, some microbial life on Earth produces pigments that protect against ultraviolet radiation. A similar strategy could be employed by gas giant organisms to shield themselves from the intense radiation belts around these planets. The chemical makeup of life in gas giant atmospheres could also be significantly different. While carbon is the basis of life on Earth, life's essential molecules on a gas giant could incorporate other elements prevalent in the surroundings, such as sulfur and nitrogen. Flexible and adaptive biochemical pathways might arise, enabling life to utilize the specific resources available in such an environment. Moreover, the observed presence of organic molecules and the possibility of liquid water in the deeper layers of these atmospheres provide additional reasons to consider the potential for life. Water, even in trace amounts or condensed into droplets, might serve as a crucial solvent for biochemical reactions, supporting life on a micro scale within the vast gaseous expanse. Investigation of these possibilities is ongoing, with missions like NASA's Juno probing Jupiter's atmosphere and future missions planned for the exploration of gas giants and their moons. Such missions aim to gather data that could reveal signs of habitability or even direct evidence of life. Understanding how life could adapt to gas giants not only expands our view of habitability, but also enriches our comprehension of life's potential diversity and resilience in the cosmos. YDDR. Binary star systems, where two stars orbit each other, present an intriguing setting for the possibility of life due to their complex yet dynamically stable habitable zones. The unique orbital configurations and varying radiation patterns in these systems create diverse environmental conditions that life might learn to adapt to, offering several fascinating possibilities. One possible scenario involves planets in circumbinary orbits, where they revolve around both stars in wide, stable paths. These planets, also known as Tatooine planets after the famous planet in Star Wars, would experience a day-night cycle influenced by the dual suns. If the stars are sufficiently close, their combined energy can create a broad, stable, habitable zone where liquid water and, by extension, life could potentially exist. The dual star system might provide more consistent energy and light, potentially fostering diverse ecosystems that could adapt to the cyclical fluctuations in luminosity. The other scenario involves planets in S-type orbits, meaning they orbit one star within a binary system while experiencing periodic influences from the companion star. These planets might have more complicated seasonal and diurnal cycles as the gravitational effects and radiation from the second star impact their climate. Life on such planets would need to be highly adaptable to cope with these variable conditions. This could include organisms with flexible metabolisms that can switch between different energy sources depending on the prevailing environmental conditions, or developing protection mechanisms against increased radiation during certain orbital phases. Additionally, binary star systems can exhibit stable regions known as Lagrange points, where the gravitational forces from both stars balance the orbital motion of a planet or moon. Objects in these locations might enjoy relatively stable conditions, offering potential niches for life. The equidistant energies from the stars might foster environments that blend the unique properties of each star's light and radiation, perhaps supporting hybrid photosynthetic processes or other energy utilization methods adapted to a mixed spectrum environment. In more complex scenarios, some binary systems involve stars of differing types, such as a combination of a main sequence star and a red dwarf, or a white dwarf and a sun-like star. The varying radiation spectra and energy outputs could encourage the evolution of life forms with specialized adaptations for exploiting different wavelengths of light. For instance, some organisms might be adapted to harness energy from the ultraviolet-rich light of a hotter star, while others might use the infrared light from a cooler companion. Moreover, habitability in binary systems would rely on the stability of climates over geological timescales. Planets within these systems could benefit from the potential for longer stable periods, facilitating the complex evolutionary processes needed for life. The gravitational interactions might also foster geologic and atmospheric activity, replenishing planetary surfaces with essential minerals and gases, further supporting biological processes. Research into these systems, aided by advanced telescopes and space missions, continues to uncover potentially habitable planets in binary settings, broadening our understanding of life's potential resilience and adaptability. Binary star systems challenge traditional notions of habitable zones and show that life could thrive in complex and dynamic environments, demonstrating the vast possibilities and profound adaptability of life in the universe. Rogue planets, also known as nomad or free-floating planets, are planets that do not orbit a star but drift through interstellar space. The idea of life evolving on such isolated, starless worlds is both captivating and challenging, since these planets would face extreme conditions, primarily the absence of sunlight. However, life on rogue planets is not beyond the realm of possibility. There are several ways in which it might adapt and thrive. One of the most crucial aspects of a rogue planet's capacity to support life would be the presence of a substantial internal heat source. Even without a parent star, rogue planets can retain heat generated by the decay of radioactive elements in their cores, much like Earth. Additionally, gravitational interactions with other celestial objects before they were ejected could have resulted in residual geothermal energy. This internal heat might keep subsurface oceans beneath a thick ice crust in a liquid state, providing a potentially habitable environment. In such subsurface oceans, life could rely on chemosynthesis instead of photosynthesis. Just as extremophiles on Earth thrive near hydrothermal vents on the ocean floor, utilizing chemical reactions involving sulfur and other minerals, life on a rogue planet might similarly exploit geothermal vents for energy. These ecosystems could host microbial life forms adapted to harnessing chemical energy from the planet's internal heat and mineral-rich environment. Another intriguing possibility involves the presence of thick atmospheres on rogue planets. A dense atmosphere composed of greenhouse gases like carbon dioxide and methane could trap heat generated by the planet's core, creating a stable, warm environment on the surface or just beneath an ice layer. This atmospheric insulation could mimic the greenhouse effect on Earth, albeit without sunlight, and maintain conditions conducive to liquid water and consequently life. The atmosphere might also shield potential life forms from cosmic radiation, providing a more stable environment for biological processes. In a different scenario, some rogue planets might carry biospheres with life forms that originated while the planets were still part of a star system. If these planets were ejected with existing ecosystems, they might evolve mechanisms to cope with the new starless conditions. This could include metabolic pathways that do not depend on sunlight, using stored chemical energy or bioluminescence, where organisms generate their own light through biochemical processes. Lastly, life on rogue planets might also be influenced by panspermia, the hypothesized transfer of life or its precursors between planetary bodies. Microbial life could hitch a ride on comets, asteroids, or even dust, potentially seeding rogue planets with life. If a rogue planet passed through a region of space rich in organic molecules, it could capture these building blocks and foster the development of complex chemistry conducive to life. Despite the harsh and isolated conditions, life on rogue planets might evolve through the utilization of internal heat sources, chemosynthesis, thick atmospheric insulation, or through being seeded by panspermia. These adaptations would demonstrate the extraordinary resilience and adaptability of life, hinting at the diverse forms it might take across different cosmic environments. Investigating rogue planets enriches our understanding of life's potential to thrive under a wide range of conditions, pushing the boundaries of our search for extraterrestrial life. Super-Earth exoplanets, which are larger and more massive than Earth, but smaller than ice giants like Neptune, present intriguing environments where the extreme pressures could foster unique forms of life. These planets may have surface conditions and internal structures vastly different from those on Earth, shaped by their greater mass and gravitational forces. Life forms adapted to such high-pressure environments would need to exhibit extraordinary biochemical and physiological traits. One possibility is that life on super-Earths might evolve in deep, high-pressure oceans. These oceans could be hundreds of kilometers deep, compared to Earth's oceans, which reach only about 11 kilometers at their deepest point. In these vast, pressurized environments, life might resemble Earth's deep-sea extremophiles, which thrive under extreme pressure conditions. Such organisms could have cellular structures reinforced by pressure-resistant proteins and membranes, ensuring their biological processes remain stable. In these high-pressure oceanic environments, metabolic processes might differ from those seen in terrestrial life. Organisms could use alternative biochemistries that are better suited to high-pressure conditions, possibly involving proteins and enzymes that maintain their functionality under extreme compression. These organisms might rely on chemosynthesis, harnessing energy from chemical reactions involving minerals and gases released from hydrothermal vents on the ocean floor, similar to Earth's deep-sea ecosystems. This could support complex food webs based on the chemosynthetic energy supply. Surface life on super-Earths, if it exists, would need to cope with the planet's strong gravitational pull, which could be several times that of Earth's. Higher gravity would likely result in shorter, sturdier organisms to support their own weight and prevent structural collapse. Their cellular structures would need to be extremely robust, potentially incorporating denser biomaterials or novel molecular frameworks to endure the stress. These life forms might possess compact, reinforced skeletal or exoskeletal systems, allowing them to withstand high gravity and pressure. Moreover, the atmosphere of a super-Earth could be thicker and more enriched with a variety of gases. Life forms might develop specialized adaptations for breathing or metabolizing in such an environment. For example, respiratory systems would need to be highly efficient in extracting oxygen or other critical gases under higher atmospheric pressure. Alternatively, the presence of greenhouse gases like carbon dioxide or ammonia might influence the metabolic pathways, driving life to exploit these compounds chemically. In regions where solid surfaces and deep oceans interact, life might evolve at the interfaces between water and rock, utilizing mineral-rich vents for energy. These niches could support novel forms of biofilm or microbial mats, capable of withstanding the dual pressures of rock and ocean. Such ecosystems might closely parallel Earth's vent communities, but adapted to even more extreme conditions. Life on super-Earth exoplanets would likely exhibit impressive adaptations to survive the immense pressures and gravitational forces, ranging from pressure-resistant cellular structures to unique metabolic processes. Investigating these possibilities not only broadens our understanding of life's potential diversity and resilience, but also guides our search for biosignatures in exoplanetary systems. These high-pressure worlds present a fascinating frontier in the quest to discover the myriad ways life could evolve and thrive beyond Earth. Life adapting to the harsh conditions of neutron star planets, which are planets orbiting the remnants of supernovae, would need to develop extraordinary and unprecedented strategies. Neutron stars are incredibly dense and exert intense gravitational fields. Moreover, they emit powerful radiation, including X-rays and gamma rays. Life in such an extreme environment would be profoundly different from anything we know, built to withstand severe conditions. First, the intense gravity of a neutron star would significantly influence the structure of potential life forms. Adaptations to withstand this gravity might include highly compact and robust body structures to prevent being crushed. Organisms might be exceptionally small, with tissues and cellular structures reinforced by extremely strong molecular bonds. These might involve materials or biological mechanisms far beyond the strength of those found in terrestrial organisms. Surviving extreme radiation would require even more radical adaptations. One possibility is that life forms could develop advanced radiation repair mechanisms. On Earth, certain microbes like Deinococcus radiodurans can repair DNA damage caused by radiation remarkably quickly. Life on a neutron star planet might take this capability to an extreme, potentially using entirely different molecular mechanisms to protect and repair genetic material. Organisms might also have evolved thick, radiation-absorbing exteriors, perhaps composed of materials similar to those found in radiation shielding. Another extreme adaptation could involve life forms utilizing the extreme radiation as an energy source. This hypothetical biochemistry, termed radiotrophic biology, could mimic how some earthly organisms use radioactive decay for chemosynthesis. Instead of relying on chemical energy sources, these organisms might harness radiation directly, converting it into usable biochemical energy through as yet undiscovered pathways. Additionally, neutron stars often emit intense magnetic fields. Organisms might evolve ways to shield themselves or exploit these fields. This could involve using magnetically aligned structures for navigation or even energy harnessing, assuming some way to convert magnetic energy into biochemical energy can be devised. On Earth, certain bacteria known as magnetotactic bacteria align themselves with Earth's magnetic fields, hinting at possible mechanisms of magnetic field utilization. Another intriguing consideration is the subterranean or subsurface refuge. Just as certain extremophiles on Earth find sanctuary within the planet's crust, life on a neutron star planet might dwell deep below the surface. Below the planet's crust, these organisms could be shielded from intense radiation and abrupt gravitational changes. Life could thrive in pockets or cavities protected by layers of rock and aided by internal heat sources, analogous to Earth's deep biosphere. Similarly, these organisms might subsist on chemoautotrophic processes, using chemical reactions with minerals sourced from deep within the planetary crust. Considering the above conditions and the need for unprecedented biological innovation, such life would vastly expand our understanding of life's potential adaptability and resilience. While speculative, these scenarios urge us to appreciate the extraordinary versatility that life might exhibit and challenge us to search for signs of life's tenacity, even in the universe's most extreme environments. The study of such possibilities advances our understanding of life's fundamental requirements and the outer limits of biological survival. The possibilities for life in the theorized subsurface oceans of Pluto-like objects, such as those found in the Kuiper Belt, are fascinating and tantalizing. Despite the apparent harshness of these environments, where surface temperatures are extremely low and sunlight is scarce, the subsurface oceans could provide relatively stable habitats with conditions conducive to life. One of the key factors making subsurface oceans on Pluto-like objects potentially habitable is the presence of liquid water beneath an icy crust. Geological evidence suggests that internal heat, generated by radioactive decay and potentially tidal flexing if these objects have moons or are influenced by other celestial bodies, could maintain liquid water below a thick shell of ice. These oceans might be insulated from the surface's extreme cold by this ice layer, allowing life to persist in a relatively stable, albeit dark, environment. In such subsurface oceans, life could resemble extremophiles found in Earth's deep oceans, particularly those around hydrothermal vents. On Earth, organisms near these vents rely on chemosynthesis, using energy from chemical reactions involving hydrogen sulfide, methane, or other compounds. In the subsurface oceans of Pluto-like objects, similar chemosynthetic communities might exist, deriving energy from the interaction between water and the rocky mantle or core. The availability of chemical nutrients from hydrothermal venting or other geothermal processes could sustain complex ecosystems, even in complete darkness. Another consideration is the water chemistry in these subsurface oceans. If ammonia or other antifreeze compounds are present, they could lower the freezing point of water, keeping it liquid at lower temperatures. This could expand the habitable zone within these icy bodies. Life in ammonia-rich waters might have unique biochemistries adapted to these conditions, potentially utilizing ammonia in metabolic processes where biological molecules maintain their functionality at lower temperatures. Regarding energy sources besides chemical reactions, potential life forms could exploit other means. For instance, if hydrothermal activity is present, it could provide heat and nutrient flux, mimicking deep-sea hydrothermal ecosystems on Earth. Moreover, these organisms could develop unique bioluminescent capabilities, using their own light for communication or to attract prey, given the perpetual darkness of their environment. Moreover, recent studies indicate that some Pluto-like objects might experience episodic cryovolcanism, where liquid water or icy slurries are periodically expelled to the surface. These events could temporarily expose subsurface materials to the surface environment, potentially allowing for interesting biochemical interactions. Life forms might adapt to these cycles, developing mechanisms to endure surface exposure and re-enter subsurface habitats during stable periods. Missions aimed at exploring the outer solar system, such as potential missions to Europa, Enceladus, or even Pluto's subsurface, could yield critical insights into these environments. Instruments designed to detect biosignatures, like specific organic molecules, isotopic ratios, or geological features shaped by biological processes, could help confirm whether subsurface oceans on Pluto-like objects harbor life. The subsurface oceans of Pluto-like objects offer compelling possibilities for life that can adapt to extreme isolated environments. Such life would likely display remarkable biochemical and physiological adaptations to thrive in the cold, dark, and chemically rich waters beneath thick ice layers. Exploring these environments broadens our understanding of habitability and life's potential resilience, pushing the boundaries of where we might find life in our solar system and beyond. The ultimate fate of black holes in an expanding universe is a topic that combines the intriguing aspects of general relativity, quantum mechanics, and cosmology. While black holes are known for their immense gravitational pull, they are not immune to the passage of time and the ever-expanding nature of the universe. One of the most widely discussed and accepted theories concerning black holes' ultimate fate involves Hawking radiation, a quantum mechanical effect proposed by physicist Stephen Hawking. According to this theory, black holes emit radiation due to quantum fluctuations at the event horizon, where particle-antiparticle pairs are generated. One of these particles falls into the black hole, while the other escapes, effectively causing the black hole to lose mass over time. This process, though extremely slow for massive black holes, leads to gradual evaporation. In the distant future, assuming the theory holds, black holes will continue to lose mass through Hawking radiation. The smaller the black hole becomes, the faster it loses mass, leading to an accelerated evaporation process. Eventually, black holes might shed all their mass and energy, culminating in a final burst of radiation before disappearing entirely. This evaporation process, however, would take an extraordinarily long time, far surpassing the current age of the universe. In an expanding universe, especially in scenarios where cosmic acceleration continues to increase due to dark energy, black holes would find themselves in an increasingly isolated environment as galaxies drift further apart. This isolation means that the black hole's surroundings would become less dense over time, diminishing the amount of material they could potentially accrete. Thus, their primary fate would be guided by internal mechanisms like Hawking radiation rather than external forces. In the far future, beyond the time frame of black hole evaporation, the universe may enter a phase known as the heat death, or the Big Freeze, where it continues to expand indefinitely. In this scenario, galaxies, stars, and other celestial bodies would drift apart, leaving cold, dark remnants. Following the evaporation of all black holes due to Hawking radiation, the universe would become a sparse, cold expanse filled with low-energy particles and radiation, ultimately reaching a state of maximum entropy with no significant sources of energy left. Alternatively, in other cosmological models that involve different potential fates for the universe, the ultimate end of black holes and the universe might differ. These include the Big Rip, where the accelerated expansion tears apart all structures in the universe, or the Big Bounce, where a contracting phase leads to a new cycle of expansion. The role and fate of black holes under such theories would align with the dynamics and properties unique to these models. While much about the distant future remains speculative, the current understanding suggests that black holes will eventually evaporate through Hawking radiation, contributing to the final stages of an increasingly cold and isolated universe. This process reflects the profound interconnection between quantum mechanics and cosmology, shedding light on the long-term evolution of some of the most enigmatic objects in the cosmos. The accelerating expansion of the universe, driven by a mysterious force known as dark energy, will have profound implications for galaxy formation and the broader cosmic structure in the far future. As the expansion accelerates, the distances between galaxies will increase at an ever-growing rate, dramatically altering the conditions under which galaxies can form and evolve. In the current epoch, gravity still plays a dominant role in assembling matter into galaxies and galaxy clusters. However, as the universe continues to expand at an accelerating pace, this cosmic tug-of-war will increasingly favor the repulsive force of dark energy. Over time, this acceleration will lead to a scenario where galaxies become isolated from each other, making future galaxy interactions and mergers exceedingly rare. One immediate consequence of the accelerating expansion is that new galaxy formation will essentially cease in regions outside gravitationally bound clusters. As galaxies drift further apart, the gas needed to form new stars will become too diffuse and will no longer be able to collapse under its own gravity to form galactic structures. Existing galaxies will use up their remaining gas reserves, and once their star-forming material is exhausted, new star formation will dwindle and eventually stop. In the far future, the accelerating expansion will also affect the observable universe. Currently, we can observe galaxies that are many billions of light years away because their light has had time to reach us since the Big Bang. However, as the expansion accelerates, more and more galaxies will recede beyond the cosmic event horizon, the point beyond which light emitted today will never reach us. This will lead to a diminishing observable universe, isolating galaxies within their own local clusters or superclusters. In regions like these local clusters, which remain gravitationally bound despite dark energy's repulsive force, some degree of galactic evolution will still continue for a longer period. Interaction and mergers between galaxies within these clusters will proceed as usual for some time, generating new star formation and possibly new galactic forms. Over extremely long timescales, even these clusters may eventually become more isolated as space continues to stretch. As the expansion persists, the isolation of galaxies increases, leading to a cosmic desert where the night sky of these future galaxies appears increasingly empty. Stars within individual galaxies will age and die, leaving behind remnants such as white dwarfs, neutron stars, and black holes. Eventually, these too will cool and fade, heading toward a dark and entropy-dominated state known as the heat death. While these scenarios paint a somewhat bleak cosmic future, they underscore the transient nature of the vibrant, star-filled universe we currently inhabit. The accelerating expansion will profoundly reshape the cosmos, turning once clustered and interactive galaxies into isolated islands of aging stars in an ever-expanding ocean of dark energy. These changes will fundamentally alter the landscape of the universe, providing a stark contrast to the dynamic cosmic era we experience today. As the universe ages and stars gradually burn out, the prospects for life will fundamentally change, driven by the dwindling of stellar energy sources and the broader cosmic factors at play. This gradual dimming of the cosmos, often referred to as the degenerate era, marks an epoch dominated by stellar remnants and long-lasting but faint celestial objects. In the more immediate cosmic future, life as we know it could continue to thrive for billions of years, particularly around stars like our Sun and longer-lived low-mass stars or red dwarfs. Red dwarfs, in particular, have lifetimes that can extend trillions of years, providing prolonged stability for any life-bearing planets orbiting them. However, as even these stars eventually exhaust their nuclear fuel, the universe will enter a phase where star formation ceases and existing stars progressively burn out. As massive stars die, they leave behind white dwarfs, neutron stars, and black holes. Planets orbiting white dwarfs could, in theory, host life if they maintain stable orbits within the habitable zone, though these zones are much closer to the remnant star, and the conditions would be substantially different from those around a main sequence star. The energy output of white dwarfs, however, will steadily decline over billions to trillions of years, leading any potential biospheres to become increasingly frigid and energy-starved. In parallel, neutron stars and black holes provide even more hostile environments for life. Any potential life forms would need to adapt to extreme gravitational forces and intense radiation fields, making the prospect of life around such objects exceedingly unlikely by our current understanding. The habitable zones around these remnants, if they exist, would be incredibly narrow and prone to severe dynamical and radiative challenges. As time marches on, the remaining stellar remnants will cool and darken, ushering in an era where only the faint glow of white dwarfs and brown dwarfs remains. Brown dwarfs, often described as failed stars, could provide some residual heat, but their low luminosity makes them unlikely hosts for complex life. Once these objects exhaust their minimal reserves of fusion fuel, the universe will be populated predominantly by dark, cold remnants drifting in the vastness of space. Life in this distant future would thus face extreme energy scarcity, relying on non-stellar sources of energy if any exist. Hypothetically, advanced civilizations might tap into alternative energy sources, such as the faint residual heat from black holes through processes like Hawking radiation, or harness geothermal energy from the cores of large planets. Such civilizations might also develop technologies to artificially sustain biospheres using fusion reactors or other yet-to-be-imagined technologies. Ultimately, as the universe heads towards higher entropy and approaches the so-called heat death, the availability of usable energy will diminish to nearly zero. This state represents a cosmological endgame where any remaining life forms would find it nearly impossible to sustain themselves. The universe would become a vast expanse of near-uniform temperature, filled with the faint glow of radiation and the remnants of once luminous stars. The gradual burning out of stars thus charts a course towards an increasingly inhospitable universe, pushing the boundaries of life's resilience and adaptability to the limits. While the distant future remains speculative, it serves as a profound reminder of the transient nature of cosmic epochs and life's enduring quest for survival in an ever-changing universe. The nature of dark energy, the mysterious force driving the accelerated expansion of the universe, plays a crucial role in determining the long-term evolution of the cosmos. Depending on the properties and behavior of dark energy over time, the fate of the universe could follow several different scenarios, each with profound implications for the large-scale structure and dynamics of the cosmos. One of the most widely discussed models of dark energy is the cosmological constant, often denoted by the Greek letter lambda. In this model, dark energy has a constant energy density that does not change over time or distance, akin to a vacuum energy permeating space. If dark energy truly behaves this way, the universe will continue to expand at an accelerating rate indefinitely. Over time, galaxies will recede from each other faster and faster, eventually moving beyond each other's observable horizons. This leads to the Big Freeze or heat death, where the universe becomes a cold, dark, and sparse place as existing stars burn out and galaxies drift into isolation. Another possibility involves quintessence models, where dark energy is dynamic and its energy density changes over time. In these models, dark energy might either weaken or strengthen. If it weakens, the accelerated expansion could slow down, potentially stabilizing or even reversing into a contracting phase. This could lead to a scenario known as the Big Crunch, where the universe might eventually collapse back into a highly dense and hot state, possibly setting the stage for a new Big Bang in a cyclic model of cosmic evolution. Conversely, if dark energy strengthens over time, the universe might face an even more extreme fate known as the Big Rip. In this scenario, the repulsive force of dark energy grows so powerful that it eventually overwhelms all other forces. First, it would tear apart galaxy clusters and individual galaxies. Then it would overpower the gravitational binding of star systems. And finally, it would rip apart stars, planets, and even atomic and subatomic structures. This catastrophic end would result in the complete disintegration of all matter in an ever-accelerating expansion. Some theories also suggest that dark energy's behavior could undergo phase transitions, similar to how certain materials change state under different conditions. Should dark energy undergo such a transition, it could introduce new dynamics to cosmic evolution, potentially altering the balance between expansion and contraction. This could lead to unexpected shifts in the course of the universe's development, adding complexity to its ultimate fate. Moreover, there is the speculative idea of phantom energy, which posits that the equation of state parameter of dark energy, the ratio of pressure to energy density, is less than -1. If phantom energy governs the cosmos, the rate of expansion would accelerate in such an extreme way that the universe would experience a big rip far more dramatically than in standard quintessence scenarios. Current and future cosmological observations aim to better understand the nature of dark energy and its properties. Missions like the European Space Agency's Euclid or NASA's Wide Field Infrared Survey Telescope are designed to precisely measure the expansion rate of the universe and gather data on the large-scale structure of the cosmos, providing crucial insights into the behavior of dark energy. The ultimate long-term evolution of the cosmos and the role of dark energy in shaping it remains one of the most profound questions in cosmology. Whether it leads to a cold, dark, and desolate universe, a cataclysmic disintegration, or a cyclical regeneration, dark energy is the key to understanding the universe's distant future and the fate of all its constituents, including stars, galaxies, and potentially life itself. The Big Rip scenario is a dramatic and hypothetical cosmological event that posits the possibility of dark energy growing so powerful that it ultimately tears apart the fabric of space itself. According to this theory, the acceleration of the universe's expansion would intensify to such an extreme that it overcomes all other forces, resulting in progressively catastrophic consequences for cosmic structures. In the Big Rip scenario, the key factor determining the universe's fate is the behavior of dark energy, particularly its equation of state parameter, often denoted by the symbol W. This parameter is defined as the ratio of the pressure exerted by dark energy to its energy density. If W is less than -1, a condition known as phantom energy, the repulsive force of dark energy increases over time. This leads to a runaway expansion that accelerates more dramatically as it progresses. As the universe approaches the Big Rip, several critical stages occur. Initially, the accelerated expansion causes galaxy clusters to drift apart. The gravitational bindings holding these clusters together weaken, and eventually, galaxies become isolated as they are pulled away from each other. As the expansion continues to accelerate, the same fate befalls individual galaxies. The gravitational forces that keep stars bound within galaxies are overwhelmed, and galaxies themselves begin to disperse. The stars become solitary travelers through an increasingly empty cosmos. Moving closer to the Big Rip, the expansion force overcomes the binding forces within solar systems. Planets and moons are torn away from their parent stars, and eventually the stars themselves are pulled apart. In the final moments, the expansion would become so rapid and powerful that even atomic and subatomic structures could not withstand the force. Electrons would be stripped from atoms, nuclei would be ripped apart, and fundamental particles would be separated. Ultimately, the expansion force would be so extreme that it disrupts the fabric of space-time itself. Distances between points in space would grow infinitely, leading to a state where the very concept of distance becomes meaningless. While the Big Rip scenario presents a captivating and cataclysmic vision of the universe's end, its likelihood hinges on the precise properties of dark energy, which are currently not fully understood. Ongoing and future cosmological observations aim to measure the equation of state parameter for dark energy with greater precision. If this parameter is found to be less than -1, it could lend support to the Big Rip hypothesis. Though, as of now, most observations suggest it hovers around -1, consistent with the cosmological constant model. Moreover, alternative theories of dark energy, such as quintessence or evolving scalar fields, present different outcomes that do not necessarily lead to a Big Rip. These models suggest that dark energy may change its behavior over time, potentially leading to outcomes like the Big Freeze or a cosmic rebound. While the Big Rip remains one of several speculative futures, it highlights the profound uncertainties and complexities surrounding the nature of dark energy. Understanding whether the universe will end in a catastrophic rip, a slow freeze, or a cyclic rebirth continues to challenge our understanding of cosmology and the fundamental forces shaping the cosmos. If protons decay, as some theories of particle physics suggest, this process would profoundly impact the very long-term future of matter in the universe. The potential decay of protons, although not yet observed, is predicted by various grand unified theories that aim to unify the fundamental forces of nature. These theories propose that protons might have an incredibly long but finite half-life, typically on the order of 10 to the 31st to 10 to the 33rd years. Should proton decay occur, the gradual disappearance of matter would unfold over extraordinarily long timescales. All protons in baryonic matter, which includes all ordinary matter like atoms, would eventually decay into lighter particles such as positrons and neutrinos. This process would lead to the gradual disintegration of all matter, from individual atoms to complex structures like stars, planets, and celestial bodies. Elemental composition and the molecules formed would continuously break down, reducing the universe's inventory of stable matter. Existing stars would eventually exhaust their nuclear fuel and end up as white dwarfs, neutron stars, or black holes. If proton decay occurs, even these stellar remnants would not last indefinitely. White dwarfs and neutron stars, composed mostly of protons and neutrons, would slowly disintegrate, leaving behind electrons, positrons, neutrinos, and other subatomic particles. Black holes might persist longer, but would eventually evaporate via Hawking radiation, leading to the same end. The decay of protons would have a devastating effect on any remaining life or complex structures. Proteins, DNA, and other essential biomolecules rely on stable atomic structures. As protons decay, the atoms that make up these molecules would disintegrate, making the persistence of life impossible. Over trillions upon trillions of years, even hypothetical long-lived civilizations using advanced technology to sustain themselves would be unable to counteract the pervasive decay of fundamental particles. As protons decay and matter disappears, the universe would become increasingly dominated by radiation like photons and neutrinos and other massless or nearly massless particles. This transition heralds an entropy-driven state where energy distribution becomes uniform and structures become less distinguishable. The universe would resemble a cold, featureless expanse filled with low-energy particles, signifying a state of maximum entropy. Proton decay would contribute to the heat death scenario, where the universe reaches thermodynamic equilibrium and no significant energy transformations or structural formations can occur. With all matter decayed into subatomic constituents and energy spread thinly throughout the cosmos, the universe would enter a state where all activity ceases, fundamentally marking the end of cosmic history. Currently, experiments such as those in particle detectors like Super Kamiokande in Japan aim to detect signs of proton decay. Despite decades of observations, no proton decay has been definitively observed, suggesting that if it occurs, it is with a half-life far beyond current experimental reach. Confirmation or rejection of proton decay remains a critical objective in understanding the ultimate fate of matter in the cosmos. The potential decay of protons underscores the transient nature of matter and highlights the long-term evolution of the universe governed by fundamental particles and forces. If protons do decay, it would signify a transformative process leading to the eventual disappearance of all conventional matter, marking a profound and inevitable end as the universe evolves towards a state of ultimate entropy and inertness. The theoretical heat death of the universe, also known as the Big Freeze, represents a scenario where the universe reaches a state of maximum entropy, where all usable energy is uniformly distributed and no significant astrophysical processes can occur. This ultimate fate would mark the end of thermodynamic activity and the cessation of any organized structures or energetic events. As the universe expands, energy becomes increasingly spread out. Stars will burn out, galaxies will drift apart, and any remaining matter will be subject to entropy's inexorable increase. In a state of maximum entropy, all energy gradients that power processes from stellar fusion to basic biological activity will disappear. The universe will become a cold, dark expanse with temperatures approaching absolute zero. Star formation depends on the gravitational collapse of gas clouds, a process driven by available molecular gas and dust. As the universe ages, star formation will cease due to the exhaustion of these reservoirs. Existing stars will eventually exhaust their nuclear fuel and leave behind remnants like white dwarfs, neutron stars, and black holes. These stellar remnants will also cool and darken over unimaginable timescales. Any remaining structures will gradually disintegrate. Stellar remnants, including white dwarfs and neutron stars, will slowly lose energy and radiate away what little heat they have left. Black holes, through Hawking radiation, will gradually evaporate. Atom and molecular bonds will break down due to the lack of any remaining energy density, leading to a universe with no bonded structures. The accelerating expansion of the universe, driven by dark energy, will eventually isolate all remaining matter to such an extent that each galaxy or galaxy cluster will become essentially isolated from all others. Beyond a certain point, the observable universe for any remaining observers will be limited to their local region. Eventually, this isolation will lead to a time when no new information or matter can traverse the expanding space. Heat death is characterized by a state of maximum entropy, where all localized energy sources and structures capable of doing work have been dissipated. This implies that all energy transactions will be uniformly dispersed, with microstates of the universe overwhelmingly tending towards disorder. In this equilibrium, no spontaneous processes can occur because there will be no energy differences to drive them. In a universe at heat death, the notions of time and activity lose conventional meaning. Without processes to mark the passage of time or interactions to lead to new states, time would become an abstract concept, essentially ceasing from an experiential perspective. The universe would be a static, invariant void with no events to delineate its temporal progression. For life and intelligence to exist, energy sources and orderly environments are essential. With the universe in a state of heat death, the conditions necessary for life would no longer be available. Any form of life, from basic microbes to advanced civilizations, would be impossible in such a high entropy state. This marks the end of not only physical processes, but also the cessation of consciousness and intelligence. While the concept of heat death represents a long-term and seemingly inevitable fate within the bounds of current physical understanding, it underscores the dynamism and eventual decline inherent in the universe's evolution. If this is indeed the ultimate destiny of the cosmos, it would reflect the profound and total reach of the second law of thermodynamics, dictating the gradual march from order and energy to disorder and cold inertness. Quantum tunneling's potential impact on the stability of the vacuum in the far future is a profound and speculative topic rooted in quantum field theory. The concept revolves around the idea that the vacuum of our universe, the lowest possible energy state, might not be entirely stable, but instead be a false vacuum. This false vacuum is a local minimum of energy, whereas a true vacuum represents a global minimum of energy. In quantum field theory, the vacuum state with the lowest possible energy might not correspond to our current universe's vacuum. Instead, it might be perched in a false vacuum, an energy state that appears stable but could transition to a more stable, lower energy true vacuum. This transition could happen through quantum tunneling, a process where particles or fields can probabilistically tunnel through energy barriers that would otherwise be insurmountable in classical physics. The false vacuum could decay via a tunneling event, creating a bubble of true vacuum that forms spontaneously. This bubble would expand outward at the speed of light, converting the surrounding false vacuum into the true vacuum. Inside this bubble, the laws of physics could be drastically different, including changes in fundamental constants or particle masses. The true vacuum would represent a more stable, lower energy state of the universe. The transition from a false vacuum to a true vacuum could have catastrophic consequences. Within the bubble of true vacuum, the different fundamental constants and altered physics could render existing matter unstable. Atoms, molecules, and all structures as we know them might disintegrate or be fundamentally altered. The expansion of this bubble would effectively rewrite the fabric of space, decimating any regions of false vacuum it encounters. The likelihood of vacuum decay through quantum tunneling depends on factors like the height and width of the energy barrier separating the false vacuum from the true vacuum. Current theories suggest the timescale for such an event is extremely long, likely far exceeding the current age of the universe. Nevertheless, because quantum tunneling is a probabilistic process, such a decay could theoretically happen at any time, although the probability is exceedingly low. Certain high-energy astrophysical events could, in theory, catalyze the tunneling process. For instance, collisions between particles at energies much higher than those currently accessible might provide the conditions necessary to overcome the energy barrier, instigating a vacuum decay. However, such conditions are expected to be exceedingly rare, even in the high-energy phenomena of the universe. If vacuum decay were to occur, it would redefine the concept of cosmological fate profoundly. Instead of gradually leading to a heat death, where the universe becomes thermodynamically inert and cold, or experiencing a big rip or crunch, vacuum decay would provide a sudden and radical alteration of the universe's state. It would be less a gradual evolution and more an instantaneous and comprehensive transformation. The concept of a false vacuum and the potential for quantum tunneling to induce a vacuum decay remains speculative and deeply theoretical, representing perhaps one of the most exotic and consequential possibilities explored by modern physics. These ideas hinge on our deeper understanding of quantum field theory and the fundamental nature of vacuum energy, likely requiring both theoretical advancements and empirical evidence to substantiate. Nonetheless, the speculation underscores the incredible complexities and mysteries surrounding the ultimate fate of our universe. The long-term fate of information in a universe dominated by black holes is a compelling and deeply debated topic in theoretical physics. Information, in this context, refers to the fundamental details about particles and fields, including their properties and configurations. The ultimate fate of this information touches upon several key issues, including the nature of black holes, quantum mechanics, and the principles of information conservation. The crux of the debate lies in the information paradox, first articulated by Stephen Hawking. According to classical general relativity, anything that falls into a black hole is lost to the observer outside the event horizon, leading to an eventual scenario where all the information about the infalling matter appears to be irretrievably destroyed. However, quantum mechanics, particularly the principle of unitarity, posits that information cannot be lost completely. It must be preserved in some form through the universe's evolution. Hawking proposed that black holes emit radiation due to quantum effects near their event horizons, a process known as Hawking radiation. This leads to the gradual evaporation of black holes. However, the nature of the emitted radiation is thermal and appears to carry no information about the specific entities that fell into the black hole. If a black hole fully evaporates, it seems that the information about what fell into it remains lost, exacerbating the information paradox. Various theories have been proposed to resolve the information paradox, each suggesting different fates for the information. One such theory is black hole complementarity, which suggests that information is both reflected at the event horizon and passes into the black hole, meaning that different observers, one falling into the black hole and one remaining outside, would see complementary perspectives without contradiction, preserving information without violating general relativity. Another idea is the holographic principle, which suggests that the information falling into a black hole is encoded on its event horizon, preserving information in a lower dimensional form. This principle, rooted in string theory, implies that all the information contained in a volume of space can be represented as a hologram, a theory extensively discussed in the ADS-CFT correspondence within theoretical physics. The firewall hypothesis is another controversial idea that proposes an information firewall exists at the event horizon, where the infalling information is rapidly transformed into radiation, thus breaking general relativity but preserving unitarity. However, this hypothesis remains contentious and lacks consensus. Some theories propose that black hole evaporation leaves behind stable remnants containing all the fallen information. These remnants would be incredibly dense and small, preserving information but posing new theoretical challenges. 作为 If the universe were to be dominated by black holes in the far future, the long-term fate of information would hinge on the prevailing resolution to the information paradox, as black holes slowly evaporate via Hawking radiation over incredibly long timescales. How they handle information will determine whether the information is ultimately lost or preserved in some form. In a scenario where information is preserved through mechanisms like the holographic principle, the long-term cosmos would retain a form of information encoding even after black holes have evaporated. Conversely, if information is handled via a mechanism not yet understood, the fundamental nature of information conservation in the universe could be profoundly different from current models. Many physicists believe that resolving the information paradox requires a more complete theory of quantum gravity, which unites quantum mechanics and general relativity. Such a theory might provide new insights into the nature of space, time, and information, potentially revealing novel mechanisms through which information remains conserved even in a black hole-dominated universe. Ultimately, the long-term fate of information remains intertwined with some of the most profound questions in fundamental physics. As our understanding of black holes, quantum mechanics, and the nature of information continues to evolve, new insights may finally bridge these theoretical gaps, providing a clearer picture of the universe's distant future. The influence of intelligent life on the long-term evolution of the cosmos is a speculative but fascinating topic that touches upon advanced technological capabilities, potential cosmic engineering, and our broader role in the universe. If intelligent civilizations continue to develop and advance, their impact could be profound in several ways. Advanced civilizations might construct megastructures like Dyson spheres or swarms, which involve capturing a significant fraction of a star's energy output. This could alter the star's life cycle and significantly change the distribution of energy within their local stellar environment. Technologies might evolve to control or extend the lifespans of stars, such as by regulating fusion processes or replenishing stellar fuel. This could stabilize habitable zones for longer periods, supporting sustainable biospheres. High-level civilizations could engineer on a galactic scale, possibly rearranging stars or even optimizing the distribution of matter to prevent collision between galaxies or to manage galaxy evolution. Such actions would require an enormous understanding and control of gravitational and other astrophysical processes. The deployment of self-replicating probes throughout the galaxy to explore, gather data, and potentially terraform planets could disperse life or its precursors across galactic distances, potentially seeding life in otherwise sterile regions. Advanced life forms might harness energy from phenomena such as rotating black holes through methods proposed by the Penrose process or other mechanisms, providing long-term energy sources. If cosmological models involving a metastable vacuum state are accurate, a sufficiently advanced civilization might develop methods to prevent catastrophic vacuum decay, thereby stabilizing the fundamental fabric of the universe. On shorter timescales, intelligent life could protect ecosystems by detecting and deflecting potentially catastrophic asteroids, thereby safeguarding planets from mass extinction events caused by impacts. Advanced engineering could develop to mitigate the effects of nearby supernova explosions, protecting biological life from deadly radiation. The spread of intelligent life beyond their home systems through generation ships, faster than light travel, or other means, would significantly impact the cosmic landscape, potentially altering the future evolutionary pathways of life and matter throughout the cosmos. Establishing extensive networks for communication across vast distances could foster a galactic society where civilizations share knowledge and coordinate large-scale projects. Given a profound understanding of dark energy, super-advanced civilizations might influence the rate of the universe's expansion, perhaps slowing or accelerating it according to certain aims, possibly averting scenarios like the Big Rip or fine-tuning conditions for a cyclic universe. In a universe facing eventual entropy maximization, intelligent life might find ways to preserve information far into the future, such as encoding it within black hole event horizons or using other advanced computational structures. Advanced civilizations might develop methods to harness quantum computation or even create simulated universes, spaces where consciousness could be preserved beyond certain physical limitations of the cosmos. Each of these speculative interventions requires an extraordinarily advanced understanding of physics, engineering, and potentially new dimensions of science that are currently beyond our reach. The concept of the Kardashev scale often categorizes civilizations based on their energy consumption capabilities, highlighting potential milestones from planetary, Type 1, through stellar, Type 2, to galactic and universal manipulations, Type 3. While the actual capabilities of future intelligent life remain uncertain, considering their potential influences provides valuable perspectives for guiding our technological aspirations and understanding our place in the universe. It emphasizes the transformative power of intelligence and the profound impacts that advanced civilizations might wield on both their local environments and the larger cosmic order.